Arrays are the simplest data structures which are random access. Random access means two-dimensional arrays are different to look at. The way we conceptually think of two-dimensional arrays is different, and the way they are physically stored in the memory are different. Malloc, CAlloc and realloc. These functions are actually defined, so structures are going to be a kind of grouping. If you want to group different elements, you are going to use structure. So depth of the tree is also going to tell you how big the stack is required. Generally, a single linked list will contain nodes, and if these nodes are generally structured. So one thing is, I want to push an element. I want to define push. The building binary strategy is to make the searching efficient. So arrays are the simplest data structures which are random access. Random access means in order to go to an element, you need not cross all the elements. You can directly go into that element. Okay. So how is this possible? It is possible that we could randomly access an element in the array, because when we are storing this array in the main memory, it will be stored contiguously, right? Since we are able to store the array contiguously in the main memory or in some memory, either hard disk or main memory, wherever you are going to store it, since you are going to store it contiguously, and since you know the size of each element and the starting address of the array, right, you can directly go into whatever memory location you want and you can access it. But the same thing is not possible with linked list, isn't it? So in linked list, what happens is they are not contiguous. So one element can be present there, one element can be present here, and it can be random, right? And only way to access these elements is to go through a chain or a list, isn't it? So in linked list, random access is not possible, but in array, random access is possible. You can go to whatever element you want very easily, right? So there is nothing much interesting about this single dimensional array. There is nothing interesting in the sense, if you have one dimensional array, that one dimensional array will be completely stored in the memory and you can go into any element you want. So there are two things whenever you talk about arrays. One thing is, what is the index starting with? Sometimes index might start with 0 and sometimes index might start with 1. So that is the only difference. That is the only point where you have to be very, very careful. So let us say the index is starting with 0. Okay. So this index is 0, this index is 1, this index is 2, this index is 3. Let us assume that each element is occupying 1 byte of memory. 1 byte, 1 byte, 1 byte, 1 byte, 1 byte, right? So in this case, in order to reach an element a of I, what is the address, right? Which means in the main memory, where should I go and look into? So if the array indexes are starting from 0, right, then just observe it. In order to reach the element 2, how many elements I should be crossing? Exactly 2 elements, which is equal to the array index, right? Therefore, whenever array indices are starting from 0, the number of elements that you have to cross in order to reach a particular element is equal to the index of the element, which means in this case the number of elements you need to cross is 2. Therefore, you can write it as 2 will be the address of the this particular element, assuming that the base of the array is 0. Right? In case if the base of the array is not 0, if it is something else, let us say if the array is starting at 100, the location address 100, then what will be the index? Index will be 100 plus 2, right? So in this case 100 plus I. Are you following it? See, I am saying that in case if the indices are going to start from 0, what is the location of the element 2 in case of one dimensional array? So if the array is going to start at some base, let's call it 100 here in this example, then in order to reach element 2, I have to cross 2 elements, isn't it? So similarly, in order to reach element I, how many elements I should be crossing? I elements. If the base of the array is 100, then 100 plus I is the starting location of the element I. That is what I mean to say, right? Now, what if the elements are starting with 1, which means indices 1, 1, 2, 3, 4, 5. Now in order to reach element 2, how many elements should I be crossing? Only one element, right? Which means I minus 1. So in case of in case if the indices are starting from 1, then in order to reach an element I, how many elements I should cross? 100 plus I minus 1. This will be the address. Got it? This will be the address of the element 2. Okay. Now this is entirely, now these formulas are when okay, don't remember them as formulas, you should be able to derive them on the go. Don't by heart it. Okay, it's very simple. Never by heart it. Now my question is, what if it is every element is not of size 1 byte. Here I am assuming that every address, every element is of size 1 byte. What if every element is of size 2 bytes? 2 bytes means, if this is the array, it will be stored in the memory using 2 bytes. So what happens is, the first element will occupy 2 bytes, 0 and 1. The second element will occupy 2 bytes, 2 and 3, right? 4 and 5, 6 and 7. Therefore, the element number 0 will be present, a of 0, in case if the indices are starting with 0, right? A of 0 will be present starting at 0, a of 1 will be present starting at 2, a of 2 will be present starting at 4, and a of 3 will be present starting at 6. In case if the indices are starting from 1, a of 1 will be present starting at 0, a of 2 will be present starting at 2, a of 3 will be present, a of 4 will be present here. Are you getting this? So now let's consider the case. See, most of the cases our arrays will start with indices 0, and sometimes as it is possible that they might give you even starting with 1. So assume that our array is starting with 0 first, and then let's see formula work. So now how many elements you should cross? Now watch it. In order to reach the element 2, how many elements you should cross? If the indices are starting from 0, the number of elements you should cross is the same, which is equal to the index. So in order to reach the element 2, the number of elements I should be crossing is 2, right? So in order to access a of I, the number of elements I should be crossing is equal to I elements, right? But then what is the size of each element? Size of each element is 2 bytes. Therefore, the total number of bytes I have to cross is I into 2. Got it? And then in case if it is stored at location 100, then this will be 100, this will be 101, the bytes. This will be 102, this will be 103, 104, 105, right? So not to scale, even take that into consideration, you can add the base. Got it? So what is it now? In order to access an element I, in case if the index was starting from index 0, then we have to multiply I into, this is nothing but the size of each element in bytes. Okay, size of each element in bytes, or if it is word addressable, if they are talking about words, then size of each element in words, and then this is the base address. That is how you could get what happens if it is starting from 0. Let's see what happens if it is starting from 1. See, in order to reach the element 2, how many elements should you cross? 1 element. Therefore, in order to reach a of I, how many elements I should cross? I minus 1 elements. Yes, I am going to cross I minus 1 elements. Okay, and then what is the size of each element here? 2. I minus 1 into 2, right? Plus, what is the base of it? 100. So in case addresses are starting with index 1 in the question, if they are using starting with 1 or 0, they'll clearly mention, they'll say that A is an array which is from 0 to n. It means that indices are starting from 0. They'll say that A is an array which is starting from 1 to n, which means indices are starting with 1, right? So in this case, whenever addresses are starting with 1, indices are starting with 1, then how many elements you should be crossing? I minus 1 elements, and size of each one is 2, right? And this one is base. So what is it here? This one is nothing but size of the element in words, right? Since it is byte addressable, I am in general what you should take is in words. Okay, they'll give you that each is many words. So multiply with the size of the element, okay, and then add the base. This is nothing but the base address. Got it? So coming to the binary, how does the binary work is, so the binary is nothing but when you are multiplying, first you find out the binary representation of this, okay, binary representation of 1, and then what you should do is you should multiply it with the base. I mean, let us say the size of the element is 2 and the binary representation of this, okay, in this case what is the binary representation of this? Binary representation of this number, how much? 2 is 1 0, and then size of this one is, before we append is element. Got it? And now 0 in binary is nothing but 4. So in case if we have a base, then I am going to write it as base and then this address. Base also I can convert it into this binary and I can write it with this, right? 100 base 2. Understood this? Convert this into binary and then append those many zeros, whichever is equal to this size, right? Getting this? So that is how we will find out what is the array address. So most of the times they might not give you even the base. So if they don't give you the base, assume that it is starting with 0. In case if they have given you the base, you can assume that it is starting with that base. Otherwise what you could do is, most of the times the A is a representation of the base. So you can write here as A, which means A represents the base of the array. You can write it as A plus this much, right? So there is nothing much interesting about this one-dimensional arrays. Two-dimensional arrays are generally interesting. The way you store the two-dimensional array, see, the way you store the one-dimensional array, there is nothing interesting. In the sense, you will take the entire array and save it as it is. There are no design decisions that have to be made here. So the only decision is you have to either you have to start with 0 or start with 1. Most of the programming languages, they start with 0 because our memory addresses, they start with 0 and it is logical to use 0. And there are some questions which starts with 1. Okay. Now let's look at the two-dimensional arrays, which will be interesting. Now let's see how to work with two-dimensional arrays. So the problem is two-dimensional arrays are different to look at. I mean, the way we conceptually think of two-dimensional arrays is different, and the way they are physically stored in the memory are different. So once you understand how they are stored, you can write better programs. Okay, so anyway, let's see the example, then you'll understand it better. Let us say A is a two-dimensional array of size 3 by 4. What does it mean? It is having 3 rows and 4 columns. And let us assume that, okay, there are two ways, you can generally talk about arrays. Sometimes you can think that arrays are starting with index 0, all the indices are starting with 0, and sometimes you can think that they are starting with 1. Let us take both of them. Initially I'll take the one with the indices 0 and next the one with indices 1. So now if I have 3 rows, the 3 rows can be row number 0, row number 1, row number 2, and 4 columns can be column number 0, column number 1, column number 2, column number 3. So these are 3 rows and 4 columns, right? Then now what is the index of each element is 0 0, 0 1, 0 2, 0 3, 1 0, 1 1, 1 2, 1 3, 2 0, 2 1, 2 2, 2 3. So these are the various indices of the elements, right? And now in case if it is indices are starting from 1, then how does it look like? So index 1, index 2, index 3, right? So these are 3 rows, and then columns are 1, 2, 3, 4 columns. Then how does each element index look? Each element looks like 1 1, 1 2, 1 3, 1 4, 2 1, 2 2, 2 3, 2 4, 3 1, 3 2, 3 3, 3 4, right? And now how to store it? See, even though if you are looking at the array like this, I cannot take this and then put it in the memory as it is, right? Then the random access will fail. Random access is possible only because the array is stored at contiguous locations. In case if you try to put it as it is in the main memory or anywhere in the secondary memory, what happens is from here to here it is contiguous, and then there is a lot of blank space, and then from here to here it is contiguous. Now what is the link between these two? Then you have to use a linked list or something. It is going to be complex. So in order to still have that random access, we have to put this entirely in a contiguous manner. How can I put it contiguous manner then? Then you have to convert this two-dimensional array into one-dimensional array. How can I convert it? There are two ways. One way says that you take each row and put it in the this memory, whatever, main memory or secondary disk or cache, wherever, and then you take the next row and you put it contiguous to the first row, like this. That is called as row major order. I'll just tell you. See this. So what is this row major order? Is row major order, which means we are going to store it row by row, first row, second row, third row, like that. Okay. Now assume that memory is going to start from here. I mean, from here the array is loaded, then 0 0 0 1 0 2 0 3, and then 1 0 1 1 1 2 1 3, and then 2 0 2 1 2 2 2 3, right? So if you watch it, we have placed it row after the row. This is the first row, and this is the second row, and this is the third row. We have three rows and we have placed it row after the row, right? Now if I have to reach any element, any particular element, let us say I have to reach the element 2 2, right? I have to reach the element 2 2. So whenever the programmer refers to the array A and the element 2 2, then we have to convert it the array reference in such a way that your the data bus will be able to go into this particular element in the memory and get it. So now the main challenge is, how are you going to convert the array references in two-dimensional array into this memory references, right? So how can you do it? So if you watch it, this element 2 2, in case if I have used the row major order, which means row after the row, if I place it, in order to reach this element, I have to cross all the rows before it. And after crossing all the rows before it, once I reach the particular row in which it is present, then I have to cross the elements which are inside the row, right? So in this case, if you are talking about 2 2, right, the element the indices 2 2, then you are supposed to cross two rows, and then in the particular row, then you are supposed to cross two elements, right? So that is how it should be happening. So what is that here is, if I have to reach 2 2, then I am supposed to cross two rows. So the number of rows I should cross is two rows. Then how many elements are present in each row? The number of columns are 4. The number of elements present is 2 into 4, which means 8 elements are present in each row, right? So what does it mean? In order to reach this particular element, we are supposed to cross 8 elements, right? This 4 plus 4 is 8 elements, and then after crossing these 8 elements, you are supposed to cross 2 elements in this row, isn't it? You are supposed to cross 2 elements. Then how can I get that 2 elements from the second array? Okay, so actually, instead of taking this one, this is 2 2, it will be confusing for you. I'll take 2 1, it will be easy, right? So now once I reach this, I'm talking about this element, okay? Now once I cross this particular 2 rows, then after reaching the required row, I am supposed to cross only one element. This second index is going to tell you how many elements you should cross in one row, right? Then this is the total number of elements that I should be crossing, isn't it? This is the total number of elements I should be crossing. So now one more thing you should consider is, how many words is each element occupying. In case if every element is occupying one word, you can directly say that this is the address if this array is starting from 0. In case if this array is starting from 100, the location 100, you can add 100 and you can say that this is the address of this element, right? 2 1. But then sometimes what happens is, each element can be of various sizes. Like they can say that each element is 2 bytes or each element is 2 words. In that case, you should even multiply with the number of words so that you can get the exact address, right? Are you following it? These many elements I should cross in order to reach my particular these many elements I should cross in order to reach the particular element, and after crossing these many elements, right, I have to even see how many words, in terms of words, how many words I should cross. So for that reason I should even multiply with the size of each element. Got it? And then let us say size of each element is 2 bytes here, right? And then add the base, then I'll get the appropriate answer, right? So in case if it is going to start with 100, then what should this entire number be? Check this, 100 plus how much is this entire number? If each element is having of size 2, 9 plus 2 is 18, so it is 118, right? 118 is supposed to be the address for 21. Let's check that. If every element is going to take two addresses, I mean 2 words, then if it is starting from 100, let's see what is the total size of it. 100, 102, 104, 106, 108, 110, 112, 114, 116, 118, isn't it? Therefore, address this element 21, the address is 118. Got it? So that is how you could find out the address or convert the array references into the main memory elements, right? So now it can be extended even for a of ij. Let's say I want to refer to the element a of ij when a is let us say the size of a is m by n, which means there are m rows and n columns, and now I want to refer the element a of ij. Is it visible? I want to refer the element a of ij, right, in an array A, and in this array the size of the array is m by n. M rows are there and n columns are there, and assume that it is row major order, right? Then how, in order to reach this particular element, how many rows I should be crossing? The number of rows I should be crossing here is equal to I. I have to cross I rows, right, which means how many elements in I rows? So how many elements will be in each row? If there are m by n is the size of A, it means that every row contains n elements, right? Therefore I have to cross n elements, I rows into n. This is nothing but total number of elements in rows, or total number of rows in terms of elements I should be crossing. Once I cross these many elements in all the rows, then I'll reach the required row. In that particular row, how many elements I should be crossing? J elements in order to reach the particular element, right? And now I should multiply with the size. So this multiplied with size. So this particular size is nothing but size of each word, and then I can add the base. Got it? So this is how you could represent it in terms of I and j. Let me write it like this again. It is I into n. This is nothing but the number of rows I should cross, and I into n will give me the number of rows I should be crossing in terms of elements, and after crossing these many rows I am supposed to cross some more elements in that particular row. So how many? J elements, right? And this is nothing but the total number of rows I should be crossing, total number of elements I should be crossing. And if the size of each element is let us say size, then this is the total number of words I should be crossing in order to reach that particular element. And if the element, if this array is starting from some base, then I add the base. So this one will give me starting with some base, right? If this is where the array is loaded, then this entire part is nothing but the address of the array. Now the same concept can be extended even for the case where indices are not starting with 0, indices are starting with 1. Watch it. Let us say I want to reach the same element here, right, 2 1, now which will be 3 2 here, right? Now how can I reach this one? In order to reach this in a row major order, I have to cross 2 rows, right? So how many rows I should be crossing? 3 minus 2, which means whatever is the first index, that number minus 1. Now the element 3 2, right? So the number of rows I should be crossing is 3 minus 1, the first index minus 1, right? So which is nothing but 2, and after reaching that particular row, the number of columns I should be the number of elements I should be crossing is 2 minus 1. Therefore here the first index minus 1 represents the number of rows I should be crossing, and the second index minus 1 represents the number of elements I should be crossing within that particular row, right? So if the same formula can be extended even for the case when indices are starting with non-zero, which is 1, but then you can directly write it as I minus 1 j minus 1. If you write like this, the same formula can be extended even to this case, right? So if you have indices starting with 0, you can directly write it as ij. If you have indices starting with 1, then you have to write it as I minus 1 j minus 1, and everything else remains same. Got it? Okay. Now this is how row measure order works. Let's talk about the column measure order. In column measure order, what happens is we are going to store the elements column by column. Okay. So the first column is 0 0, right? 0 0 1 0 and 2 0, and the second column is 0 1 1 1 2 1, and the third column is 0 2 1 2 2 2, and the fourth column is 0 3 1 3 and 2 3. Got it? So this is how you could represent all the columns, isn't it? So this is column number 1, this is column number 2, column number 3, and column number 4, right? So now in order to access an element, let us say I want to access the element again A21. So if I had to access the element A21, then how can I access it? First you have to cross some particular number of columns and then reach the particular column in which the element is present, and after reaching that column you have to reach that particular number of particular element, right? So watch this. First of all, you have to reach how many columns you should be crossing. In order to reach the element 21, I should cross one column, right? This because it is present in the second column. So the second index is going to represent how many columns I should be crossing, right? Therefore I should cross one column, right? And how many elements will be there in one column? That depends on the number of rows. If the number of rows here is 3, then the number of elements I should be crossing in order to cross one column is 3 elements. And after crossing these number of elements, I will be reaching the exact column in which this particular element is present, which means the second column, right? And once I reach that exact column, how many elements I should be crossing to reach the element? The required element, 2 elements, right? Therefore this is the total number of elements I should be crossing in order to reach the required element, right? And if the size of each element is s, let us say size of each element is 2 bytes, right? And if the memory is loaded from 100, then this is the address of this one, right? So how much is this? It is 3 plus 1 is 4, 3 into 1 is 3, 3 plus 2 5, it is 110. Okay, now check it. So if the address is loaded with 100, if the array is loaded from 100, and if the first index is every element is 2 bytes or 2 words, then where is this 21 going to be loaded? This is 100, this is 102, 104, 106, 108, 110. Watch it. So 21 is loaded at the address 110. You got it, right? So that formula works. Then okay, in exam also you can do the same thing. You can write them all down, and then given the options you can directly check them. If you don't know how to write it, you can check in the options and you can get it also, right? So now let's see A of ij. Let us say A is an array of size m by n, right? And I want to access the element A of ij. Then how can I reach it? You have to first, in case of column measure order, you have to cross these many columns. How many columns? J columns. You have to cross j columns. And what is the number of elements in each column? That depends on the number of rows. How many number of rows are there? M rows. Therefore, in order to cross j columns, you have to cross these many elements, j into m elements. Then you will reach the particular column in which your element is present. After reaching it, you have to even cross some number of elements to reach the particular element, right? So how can I cross it? By adding I. Now this entire number is nothing but the number of elements you should be crossing in order to reach the element a of ij, right? In case if each element is of size s, then this is the total number of bytes I should be crossing in order to reach some particular element, right? And then you have to add the base. Then what is the base here? Let us say base is b. This is the address of this element. Got it? So this is the total number of elements I should be crossing, and this is the total number of words I should be crossing. And since it is going to be loaded at some base b, this is the total address. So in case if you are applying this for indices starting from 1, in place of j you have to write j minus 1, in place of I you have to write I minus 1. You need not by heart it, you can just derive it on the go. Got it? So this is how row major and column major order works. So why is it so important that you should understand this row major and column major order is, if you know whether your array is stored in row major or column major order, then you can write your program in such a way that your program will take advantage of this representation. I'll tell you how does it work. Okay. Now this is the sizes or the formulas which are given you in decimal. Now how to get the address in binary? So this is somewhat difficult, and okay, I want you to pay full attention here. Whatever I am going to teach you is not that easy to understand. I'll try to make it as simple as possible, but then you please focus on this. Okay. So writing the addresses in binary and decimal is straightforward, but when I try to convert the same addresses into binary, then it is going to be a bit tough in a sense. Okay. So let's talk about this. What is the address of a particular element ij when the indices are starting from zeros? So most of the cases our computers are going to have indices starting from zeros, because the main memory is also starting with zeros, so it is natural to have indices starting from zeros. So I am going to take here, assume that the indices are starting with 0. Then what is this? See, in order to get into a of ij, right, where a is a m by n array, if the indices are starting with 0, then I told you that it is I into n plus j into s, where s is size of the element and plus base is anyway there. Okay, so this is the formula. Fine. Now I want to write this entire address in binary. That is what I want to get. Okay, then now one thing you should understand is, in computer science generally everything will be in the power of 2. So even let us assume that even the array sizes are also given in powers of 2. In case if the array size is also a power of 2, okay, what is n here? N is the number of columns, remember? So A is an m by n array, which means n is the number of columns. Let us say, then what is the relationship between j and n? If n is the number of columns, you can clearly understand one thing. The relationship between j and n is 0 is less than or equal to j is less than or equal to n minus 1, which means j will be definitely less than n, right? So the relationship between j and n is j will be less than n, right? Now assume that n is a power of 2 and assume that n is 2 power k, right? What does it mean? The number of columns we have is equal to 2 power k. Are you following it? The number of columns we have is 2 power k, right? And then now if j is a number less than 2 power k, okay, see, j is a number less than n, and I am assuming that n is a power of 2, and if j is a number less than 2 power k, then how many bits will be required in order to represent j? The number of bits that will be required to represent j will be definitely less than or equal to k, isn't it? If any number is less than, if any number j is less than n and n equal to 2 power k, what does it implies? This implies that j is less than 2 power k, right? Now what does it mean? In order to represent j in binary, we need less than or equal to k number of bits, isn't it? The number of bits which are used to represent j will be less than or equal to k. Keep that in mind. Okay. and you can even assume that the number of rows m is some 2 power l, right? Then what happens? Then I is also less than 2 power l, therefore the number of bits required to represent I will be l, right? So now you can write it like this: I into 2 power k plus j, isn't it, into, you can even assume that size of this size of the element is also a power of 2, let us say 2 power x plus base. I am writing everything in 2 parts, right? Now what you could do is, you could represent this I in binary. Let us say I have represented this I in binary, this is the number I, right? And when I multiply any number with 2 power k in binary, it is nothing but adding k zeros, isn't it, appending k zeros. So these are nothing but k zeros, which is nothing but I multiplied with 2 power k. And when I add j, right, I am going to add j here, isn't it? And you already know that j is going to take less than or equal to k bits, right? Therefore the entire representation can be represented using I can be represented in l bits and j can be represented in k bits. So the total number represented is l bits plus k bits, and then multiply with 2 power x, therefore x bits will be here. I don't know whether you understood this or not. Okay, I'll even take a numerical example and explain you, but anyway, just try to focus here one more time. See, what is that I'm trying to say is, okay, maybe I'll do it again. This is not very simple concept to follow, but then let's go step by step, maybe you might understand it then. Okay, so I'm talking about row major order. So in row major order I am talking about Aij. You already know that in order to reach Aij I have to cross I rows, right? So if I have to cross I rows, then how many elements I should cross? Number of columns, I into number of columns is n. These many elements I should cross in order to reach the particular row, and after reaching particular row I should cross j elements in order to reach that particular element, right? So this is the total number of elements I should be crossing, and if the size of each element is s in terms of words, this is the total number of words I should be crossing to reach the element Aij, and base is b. Got it? Now I want to find out the address, right? So what is that I am trying to do is, now I am assuming that m is 2 power l and n is 2 power k, which means the dimensions are, I am assuming that in the dimensions are represented using powers of 2 without loss of generality, right? And now what about I? The I is nothing but the row number. Row number will generally vary from, if you assume that it is starting with zeros, the row number, which means I, will vary from less than or equal to 2 power l minus 1, isn't it? And what about column number? The column number will also be less than or equal to 2 power k minus 1. 2 power k minus 1. So what do you understand? Either in order to represent I or to represent j, the number of bits required will be less than or equal to l, isn't it? See, what is the maximum number that could be represented using l bits? 2 power l minus 1, isn't it? What is the maximum number that can be represented using 2 bits? 3. What is the maximum number that could be represented using 3 bits? 7, right? 4 bits? 15. So 2 power l minus 1 is the maximum number that could be represented using l bits, right? Therefore, if you are never crossing the maximum number which could be represented using l bits, then how many bits are used to represent the number I? In worst case, l bits, right? Therefore, you can represent any number I if its range is 0 to 2 power l minus 1 using l bits. So l bits are enough to represent I. What about j? K bits are enough to represent j, isn't it? Now I'll write this entire address like this. The entire address can be written like this: I into 2 power, what is n? K, plus what is j? Let me leave it as j, and let me say the size of the each byte, size of each element is 2 power x words, right? Then it is 2 power x plus b. Got it? So this is the number of words for each element, right? And now see, how many bits are used to represent I in binary? L bits. So L bits are enough. So using L bits I can represent I. So I is represented using L bits, right? And now when I is multiplied with 2 power k, right, then how many, what does it mean? Whenever any binary number is represented multiplied with 2 power k, it is nothing but left shifting this number those many k times, right? Therefore I into 2 power k is nothing but appending it with k bits, and all k bits are zeros, right? So I is nothing but L bits, and L bits I is represented, and this entire number is this one, and now I have to add j, right? So what is adding j? Adding j is nothing but convert j into a binary number. How many bits are required to convert j into binary number? K bits, right? Therefore you can get j which is represented in k bits, and you can add it, right? Therefore now this entire number is actually represented using k plus L bits, isn't it? So now this entire number is going to be represented using, here there are L bits and here there are k bits, right? And what is this? This is I and this is j. So I is nothing but the first index, isn't it? I is nothing but the row number, and this is nothing but the column number, isn't it? See, if aij is given, I is nothing but the row number and j is nothing but the column number. So you can represent row number here and column number here using the L and K, right? And we got this entire number in how many bits? The number of bits required is L plus K bits, right? And then you have to finally multiply with 2 power x. So what is multiplying with 2 power x? Appending x number of zeros. Got it? So this is the entire address of this element in our in binary, right? And finally, anyway, you have one more binary number which is base. You convert this base into binary and you can add it, right? Anyway, that doesn't make any difference. So only important part is this. So what did you understand from this? In order to get any address, right, you have to do this. You have to take the take the address, and then the least significant x bits is going to be the size of the element. If the size of the element is 4, it is going to be 2 zeros. If the size of the element is 8, it is going to be 3 zeros. And then in case of row major order, here it is going to be column number and here it is going to be row number, right? Depending on how many ever bits you want to represent row and column, right? So this is how the address can be found out in case of row major order. What happens in column major order? The same thing, right? In column major order, same thing. You have to have this x number, where x is the size of the 2 power x is the size of each element, and then here you should have row and here you should have column. So why do you think that this way it is followed in row major order and column major order is, in row major order we have to cross first the rows, and then after crossing the rows you are supposed to go into this after crossing the rows, you are supposed to get into the row which is required, and you have to cross the elements to get to that element, right? That is why row number is here and column number is here. By writing row number here, this will make sure that you are going to cross all the rows before you get into the desired row, and after getting into the desired row, you have to cross these many elements, right? See, row and column doesn't mean that you have to put the number of rows and number of columns. Row and column means that what is the first index and what is the second index. In case of column major order, you are supposed to cross the columns, that is why the second index here and then the first index here, right? So which means, see this, instead of putting a row column and column row, if you are getting confused, you can even put like this. So if A of ij is required, what I mean to say is, this one is the first one, this one is the second one, right? So in case of row major order, put the first one here and the second one here. In place of column major order here, put the first one here, put the second one here, and then the first one here, right? This can be extended even to 3 dimensions. In case if you have 3-dimensional array, put the first one here, second one here, third one here, and finally the size of the element, right? So it can be extended to any number, right? Fine. And so this is how you can think of the array elements, right? So this is all about the row major representation and column major representation. So one thing is, why is this important that you should understand all these concepts is, depending on the way in which you have written your program, or depending on the way in which the memory is organized in the two-dimensional array is organized in the main memory, you can write the programs in such a way that they will take the advantage of this organization. See, in case if you think that row major order is used, then what happens? This entire part will be placed together, and then this entire part will be placed together, and then this entire part will be placed together, right? And then let us say the entire part happens to fall in, if this is the organization, then what happens is, in terms of paging, the entire row might fall in one page, right? Then if you try to load one element, or if you try to access one element, you will get all these elements in that page. Therefore, you can write your program in such a way that it will take advantage of this organization, and immediately when you get one element, you can try to access all the elements without any page fault. So in case of row major order, accessing the elements row by row is going to give you less number of page faults. In place of column major order, accessing the elements column by column is going to give less number of page faults. Why? Because whenever you try to load one element, in case of row major order, the entire row will be loaded in one page. Therefore, if you try to access them row by row, only for the first element there will be page fault, and for all the remaining elements there will be no page fault. Got it? So whatever the memory organization is, you could still write some kind of program which will take the best advantage of it and give the best performance. But then once the program is fixed, which means once you have written the program and once it is fixed, then the performance of the program depends on what kind of organization they have used. In case if they have used row major order, then the performance will be in one thing. In case of they have changed it to column major order, the performance will change, right? Therefore, knowing the organization well ahead and then writing the program will give you better performance than writing the program and then asking it to adapt to the organization. Are you getting this? See, what I am trying to say is, in case of paging, if it is row major order, there are chances that one row will fall in one page. Therefore, when you get the first element, you access all the elements of that row only. In case of column major order, then there are chances that one column will fall in one page. Therefore, when you get the page for the first reference, then you try to access all the elements of the first column. Are you understanding it? The same thing can be applied even for cache also. In case of blocks, and whenever you are using this row major order, whenever you load one block, there are chances that the corresponding elements which are in the entire row will be loaded. Therefore, you write the program in such a way that it will access all the elements row wise, not the column wise. See, if you are using row major order and if you are accessing the elements in the column wise, what happens is, whenever you load any program, whenever you load any word, then the entire row will be loaded, then immediately you will be asking for the next column instead of asking the next element in the row. That is why, depending on the organization of the two-dimensional array, either row major order or column major order, you choose the program, but not the other way around, which means you don't write the program and then you don't think that it will give the same performance in all kinds of organizations. Got it? So what I mean to say is, either it is row major order or column major order, you could still write the programs in such a way that it will run efficiently, but then only for one order. Let us say the given organization is row major order, then I'll write the program in such a way that I'll try to access the elements row wise, then that will give the best performance. If the program is column major order, then I'll try to write the program in such a way that the elements are accessed column wise, then that will give the best performance, right? So once you have fixed up the organization, either row major order or column major order, then it is up to you to write the correct program. Got it? Okay, we shall see some questions on that, you will understand it better. So especially in CO, we shall see how to combine the arrays, the concept of two-dimensional arrays and the memory organization along with the blocks. Then you will understand what is really going on. Okay, fine. Now let's see the C program. Determine whether two arrays A and B have an element in common, right? So let's say the name of the function is common, and now we are going to have it is going to take two arrays, one is A and other is B. It is nothing but, we are having first argument as a pointer to an integer and second argument as a pointer to an integer. generally address to the first element of the array which has to be processed will be passed to this, and that will be held in this pointer. Similarly here also the address to the first element of an array will be passed, and that will be held in this pointer, right? And then int n, int m. Okay, so what is int n and int m are? They are the sizes of the array A and sizes of the array B. Generally when we pass strings, we don't pass the size of the string. The reason is every string is null terminated, therefore the function which is processing it is supposed to find out the size by itself by going till the null. But coming to the integer arrays, we don't have null terminated concept here, right? So for that reason we are even sending the sizes. Whenever we send the pointer to the starting of an integer array, we also say they send the size. Okay, int I comma j, for I equal to 0, I less than n, I plus plus, for j equal to 0, j less than m, j plus plus. Now what it means is, the logic here is simple. Let us say the array which is being pointed by A is this, and the integer array which is being pointed by B is this. Okay, and the numbers in this array are like this. Assume that it is 1, 2, 3, 4, 5, and the numbers here are like this: 10, 5, 2, 4, some 6, something like this. Now what we are trying to do is, we will first consider for I equal to 0, which means we start indexing this one from 0, and we first consider for every element, for let us say for 0th element, we will get into the second loop, which means we take this element and we get into the second loop, which means we will start j from here. I will be pointing to this, indexed into this, and j will be used for indexing into this. Now for this element, I'll search the entire array by using j, whether this element is equal to any of the elements present here, right? So for j equal to 0, j less than m, j plus plus means all the elements here are being searched. How they are searched is, if a of I is equal to b of j, which means I'll check whether this element is equal to any of the elements here, right? Every time I take this element and I'll check with this. If it is not equal, I'll check with this. If it is not equal, I'll check with this. That is what is going to happen with j plus plus, right? The next element is going to be searched. Now whenever let us say we didn't find element number 1, right? And after this complete search is over, we come out of this for loop. Once we come out of the for loop, again we go to I plus plus, right? Now I is going to be the next element, which means I is equal to 1. So we take this element and now we start searching with all of them. Again I start searching from the beginning, which means I search with j equal to 0. This element will be searched with this. If it is not equal, then this condition will not execute. Therefore from here again I increment j. Next element will be searched. Next element will be searched. Let us say this element is now about to be searched. When will this hit? Whenever I equal to 1 and j equal to 2. Let's see what happens. I equal to 1 and j equal to 2. Now if it compares these two, a of I and b of j, which means a of 1 and b of 2, if it checks these two, it is going to see that they are actually equal. Now the question is, check whether they have an element in common. Even if there is one element in common, we stop executing the program there and we directly return to the calling function, right? The function which is calling this function will go there directly without doing anything. See, if you look at break, by using break we will be coming out of the enclosing for loop, right? By looking at continue, will not execute the statements which are after the continue, but will go into the increment or decrement phase. But if you have any return statement, we directly come out of the entire function, will not do anything. We stop everything and we go back to the calling function. Got it? Now if we didn't go back from this for loop, which means if this is never hit, it means that there is no element common at all. Then we are going to come out. If we have searched all the elements for all elements in A, if we have searched all the elements in B, and if we are not able to find the common element, then we come here and we simply return 0. 0 means we didn't find anything. Got it? So since the return type is an integer, successful is going to return 1. On failure, we are going to return 0. Got it? Okay. In C, in the library, string library, it has already provided us with a lot of functions. I'll just tell you what each function here means, okay, and later we shall see how to implement these functions ourselves. They are already provided in C. You can directly call them, just include include std string.h, and then after including it, you can use any of these functions in your program. Now I'll tell you, if we include these functions, what you can expect. Later we shall actually implement them by our own code, okay. Now let's see this. strcat s comma t, concatenate t to the end of s. Now what it means is, let us say we have two strings, s is there and t is there, alright. Let us assume that the string s is containing ravi, and at the end there is null is there, okay. And now string t is containing, let us say, babu, and at the end null is there, okay. So all these strings in general are null terminated, otherwise we don't know where this string is going to end, right. Now we want to concatenate s with t, that is the meaning of this. strcat sts comma t means our intention is to concatenate t to the end of s. That is what this function is going to do, concatenate t to the end of s. Now after this, what is supposed to happen is, t will remain as it is, but then s is going to change, right. So s is going to be ravi, and earlier wherever there was null, from that point on it will take t and it will append it, right, which means in place of null, now b will be copied, and then babu, everything will be copied, and at the end anyway we are going to have null, because every string has to be null terminated. That is the reason, right. Now strcat s comma t will work this way. Given two pointers, these are generally character pointers, okay. This is a character pointer and this is a character pointer. It will take the strings which are pointed by these pointers, and then it is going to append appropriately. Now what will it return is, it will return a pointer to the destination. Destination means in this case we are taking t and appending it to s, therefore this again the starting point at this s will be returned, which means the starting address of this one will be returned, okay. Now if you observe it, whenever you are declaring this string by using a character array, you should remember one thing, there should be space inside this character array to hold this, otherwise we will not be able to append it, got it. So there should be space here, otherwise this one cannot be accommodated there, right. Okay, and the next one is strcat s comma t comma n. It exactly acts like the strcat only difference is, we are not going to append entire string t to s, we are only going to append, concatenate only n characters, okay. Only n characters will be appended to the end of the string. Now it is char star, again it is also going to return the same thing, char star, and strcmp s comma t, right. So if you want to compare two strings, right, you can use this. Now how the comparison is done is, let us say the first string pointed by s is this and the second string pointed by t is this, right. Let us say the values present here are a, b, c, d, and a, b, let's say c, c, okay. Now what it will do is, it will, for every character here at the same position, which means it will take the character from the first position and here the first position, and it will do the subtraction. It will do s minus t, right. So this character minus this character, whenever I subtract one character from the other character, the ASCII values will be taken, and the result is going to be the difference between those two characters, right. Therefore if I do a minus a, it is going to be 0. As long as it is 0, it is going to keep on doing it, right. Now again these two will be compared. How will it be compared is, from this one, this character, it will decrease, it will delete this character, this one minus this one, again it is going to give 0. Now again 0. Now at the end, if you see it, when it does d minus c, it is going to have 1, because ASCII value of this one will be 1 greater than the ASCII value of this one, therefore you are going to get 1, right. And at the end anyway there is null here, got it. So finally when it gets 1, it is going to return that value. Now you see this, return negative 0 or positive value. When s is less than t, when s is less than t, we are going to return a negative number, right? Now what will that negative number be? This difference, right? So what do I mean by s is less than t is, while comparing, I came across a different character at the same positions in s and t, and the character which is present in s is less than the character which is present in t. That means s is less than t, right? In case if both are equal, it is going to return 0. Then it is going to return the difference, right? If all the characters are equal, then it is going to return 0. If s is greater than 3, which means out of all the characters, the first character which is different, then we are going to compare that, and if that character present in s is greater than t, then a positive number will be returned. Got it? And the next one is strncmp. It is going to act the same way, but only difference is, instead of comparing all the characters, we are going to compare only the first n characters. And the next one is strcpy s comma t. It will compare, it will copy entire t into s. Okay, so what do I mean by copy is, let us say you have a string like this, ravi null, and let's say one more string ba null. Okay, now if it is given that strcpy s comma t, and if s is pointing to this and if t is pointing to this, now what will happen is, it will copy the entire t into s starting from the beginning, which means this one will be replaced with b, and this one will be replaced with a, and null will be copied here. Therefore, even though you have other part here, that will never be read by anyone, because generally when we start reading the strings, we stop it only till the null. So that is how copying will be done. Got it? And again, if you observe it, there should be space for this one to copy here. If if the array here is smaller than this array, then there will not be space to copy entirely. Then it is going to return null, right? That is an error condition. Okay. And the next one, and what will be written by this? After copying all this to here, the s will be returned. I mean, the starting address of this array into which it has been copied will be returned. It is nothing but the destination, isn't it? So every time these functions are going to return the destination address. Next one is strcpy s comma t comma n. So it means that we are going to copy n characters from t into s. And the next one is strlen s, return length of s. So this is simply going to return the length of the string provided by you, s, right? And the next one is, okay, anyway we are going to look into particular exact details when we implement them. Okay? We are going to implement them one by one. I will show you that. And the next one is strchr s comma c. It returns the pointer to the first c in s, or null if it is not present. So it means that, let us say you have a string which is ravi n dra. Okay, now if I say strchr, if I pass to it the starting address of the string as the first argument, and as the second argument if I pass the character, let's say a, right, then what it will return is, in this entire string it will check for the first occurrence of this character, right? In this case this one, and it will return the address of this one, right? So that will be returned. See this, return the pointer to the first character c in this s, right? And if I want to see not the first character, first occurrence, but the last occurrence, then you can use the next one, strr chr s comma c. Now if I use that, it is going to say the last occurrence of this, right? So wherever it has occurred last, that particular address will be returned. In case this character, if it is not present in this string at all, then it is going to return null, right? If it is present, it is going to return that address. Okay. Now let's see this program which is written to reverse the string. In your library, in C library, it is already implemented as strrev. There is a function strrev, you can actually call this and use to reverse it, but then let's see how to reverse a string here, how the code is written in that. Okay, now see this one, void reverse. Reverse is the name of the function and it is returning nothing. Void means nothing, and it is taking as one of the argument char s array, so it is nothing but pointer to a character, right? So s, you can think of it as if it is a pointer to a character. It is as good as defining it as char star s. Okay, and now we are including string.h because in the function I am using strlen, that is the reason. Okay, now if you observe it, c, I and j are first initially defined. For I equal to 0, j equal to str length minus 1, which means both are initialized like that. So why is that initialized this way is, let us take an example. Let's say I have a string like this, r, a, v, I, and at the end let us say there is null. Okay, so I is equal to 0, let us say this is 0, this is 1, 2, 3, 4. Okay, now initially I equal to 0 means if I use I to subscript in this array, it will be pointing to the first character in the array. Now j equal to strlen minus 1 means if I use strlen, it will return 1, 2, 3, 4, 4 as the length. So strlen is not going to count the null, it is only going to return how many non-null characters are there in the string. Therefore strlen is going to return a value 4, and when you do minus 1, it is going to be 3. Therefore j is going to contain 3 in this case, and if you use it to subscript to this array, it will be pointing to the last character which is non-null in this array, right? It is the first character and is the last character. Therefore I am going to start I from here and j from here, right? And at every point I am going to check whether I is less than j, which means as long as I didn't cross j, right, I am going to continue I plus plus, which means I will be incremented 1 at a time, and j minus minus, j will be moved 1 to the left at a time. And once I enter the for loop, what I do is I'll take the character which is present, which is pointed by I, which is indexed by I. So s of I means this character, and I'll store it into C, and then I'll take the character which is present here and I'll move it here, right? And whatever was earlier stored in C, let us say in C it is stored or is stored here, now that will be moved here. So it is nothing but this logic is the swapping logic. So if you want to understand it simply, we are going to take two pointers. I am going to start from left and right. These two will be swapped first. Therefore I will be here and R will be here. After the swapping is done, I will increment I by 1 and decrement j by 1, which means I is incremented by 1 and j is decremented by 1, right? Again I will do the swapping logic. Then what happens is v will come here and a will come here, right? v will come here and a will come here, right? Now I will be here and j will be here. Whenever I increment I by 1 and decrement j by 1, they are actually going to cross over, right? So whenever they cross, I am going to stop it. Why? This condition is going to fail. I is less than j, this condition fails. Therefore I am going to come out of the for loop. Okay, now let's see a program where we convert a number into a string. So let us say we have a number like this, 123, right? Now I want to put it in a string like this, 1 here, 2 here and 3 here, right? So I want to take this number and I want to take each digit in this number and I want to put it in this string as if it is a character. Okay, so this number is an integer number. Now I am going to put it in a array of characters. Okay, so now how we could do this one is, see, simple thing is you take this last one. So how I could obtain the least significant digit of a number is, you just take modulus 10. It is going to give you the remainder when I divide this number with 10. When I divide this number with 10, the remainder is going to be 3, right? So you initially take that least significant digit and you place in the character array, and then you eliminate this from the integer. How can I eliminate it? By doing divide by 3. If I take this number and divide by 10, this is going to be eliminated. Okay, and now take the next least significant digit. How I could do it is again by taking modulus 10, then 2 is going to be here, right? And then you eliminate it by doing divide by 10, therefore it is going to be eliminated. And again you take the least significant digit by taking modulus 10, then I am going to get 1, right? So now if you observe it, if the given number is 123, I got the number here in the array in a reverse order. So once you get this reverse order, you simply reverse it, right? So how I can do the reversal is, as you have already seen the function that we have written to reverse a string in the earlier example, we are going to use the same function here, okay? Now in case if the number would have been a negative number, minus 123, then at the end, at the last, you put minus here, okay? So you just remember that the number is a negative number, and then at the end of this you put a minus, and now if you reverse it, it is going to be minus followed by 1 followed by 2 followed by 3, okay? And at the end you just put a null, okay? So now let's see how it is going to work. See this? Now assume that this is the function which we are going to write, I to a, and for this we are passing two parameters. One is what is the number you want to convert into a string, and the second one is where you want to place the string. This is a pointer to the that character array, right? So it is as good as char star s, therefore you can assume that s is a pointer. Now int I comma sign. So why do I need sign variable is, I want to find out the sign of the number, whether it is a positive number or negative number, so that I can do something with it later. See this, if sign is equal to n less than 0, so what does it mean? I am reading whatever number is given into the variable sign. The reason is, once I keep on modifying the number n, later the number will completely be gone. So for that reason I am just storing the number into this variable sign, and now I am checking whether the number is a negative number or not. See, what does it mean? Sign equal to n less than 0 means whatever value is present in n, I am putting in sign, and now I am comparing sign with 0. If sign is less than 0, it means that the given number is negative number, right? If the given number is negative number, then I am going to convert it into positive number. So see this, n equal to minus n means if the given number is negative number, then I am taking that number and multiplying with minus 1, therefore I am putting a positive number there, right? And after that I'll start doing this procedure. Do I equal to 0, I equal to 0, do s of I plus plus equal to n mod 10 plus 0 ASCII value. So the reason why we are doing this one is, so if I write like this 0, it means that it is going to be the ASCII value of this number, right? Now if I say the number is 3 which has to be stored here, right? Now if I write like this, it means that the ASCII value of 3 will be stored here. As you know, the ASCII value of 0 is 48. You need not remember it, some value, let us assume 48, and then 1 is 49, ASCII value of 2 is 50, ASCII value of 3 is 51. Now if you want to store the ASCII value of 3, you are supposed to get the ASCII value of 3. If you don't remember the ASCII value of 3, then better whatever you get the ASCII value of 0 and you simply add 3, you are going to get this. That is why I am doing this one, right? So if you observe this statement, what we are trying to do is, I am trying to get the least significant digit of the number n, and then I am trying to add it with the ASCII value of 0, therefore I will get the ASCII value of the least significant digit, right? Once I get this, I am going to store it in the array s, right? So I am going to store it in the array which is pointed by s at the index s of I. After I do it, I am going to go to the next location and wait there, right? Now once you are done, so when will you be coming out of this while loop is while n divided by, see this, so after every step n divided by equal to 10, which means this step is nothing but n equal to n by 10. So if you see this, I have taken the least significant digit, and if you see this step, after that I am eliminating the least significant digit. By doing so, if the number becomes 0, then it means that we need not continue further. The entire number has been already passed, right? So here if it is greater than 0, then I'll have to again go into this and do it. So the reason why we have written do while instead of writing while is we have to enter this loop at least once, because the number in worst case will at least be 0, right? In that case you will have to take that 0 and place it in the string and then come out of it. If it is not a 0, you keep on deleting the digits one by one till it becomes 0, right? So once it becomes 0, you can come out of it. Okay, finally let us say you have taken the entire number and you have stored it in this string, right? So this is what has happened, right? And now you just check the sign. In case if the sign is less than 0, which means if the given number, sign is nothing but given number is less than 0, then it means that it is a negative number. Then we are simply going to put minus here. This is the step. Okay, now after this everything is done, I am going to append null to the end of the string. Got it? Now once this is done, this entire number has to be reversed, right? Because the given number is minus 123, but here what we got is 321 minus. Now if I reverse it, I get the actual output which is required. Now you just call the reverse, right? Reverse of s. We have seen it earlier. Reverse with s, if you send it, then it is simply going to reverse this string. Got it? And now if you you can leave it there anyway, s is going to point here, right? Or if you want to return some pointer, you can return it. Here we are not returning anything, void. Okay, in case if you want to return s, you can return that. Okay, now let's see this function a to I, ASCII to integer. I mean, a to I is not ASCII to integer. This is a function name and it is used to convert a given string into an integer number. So what I mean to say is, if you have a character array and a number is given in this character array like this, 1 2 3, right, and then null. So this is actually an array, not a number. Now if I say this is a character array and if I have to use this number, I will not be able to use it, right? What I mean to say is, if you say int I equal to 123, okay, this is different and this is different, right? Now I have to convert this string present here into a number. That is the question. So how to do that is, we are going to use this function. Again, this a to I function is already present in the C library, so you can use it. Now we are going to implement it on our own. So the first thing is, the parameter it is going to take is, the argument is going to take is char s and then this array symbol. It is nothing but s is defined as a pointer to the character, and the return type of this one is int. Now int I comma n equal to 0. For I equal to 0, s of I greater than or equal to 0 and s of I less than or equal to 9 I plus plus. So what is that for loop is going to do is, it is going to start from here, it is going to start from beginning, right, and it is going to check whether the given character present here is between the characters 0 and 9. See, even though I'm saying that 1 is present here in this cell, it is not exactly 1. It is actually ASCII value of 1 will be present here. If this is a character array, then every cell indicates a character, and inside a character, whenever I say this 1, it is actually ASCII number of 1, which means in place of 1 what you have is actually 49. The bit pattern which is used to represent 49 will be present here. When you interpret it as a character, it will be 1, right? So what I mean to say is this: if I say char c equal to, let's say 0, right, and if you say printf %d %c, then what will be printed is, let us say %c %dc, right? Now what will be printed is, in C, the bit pattern that will be represented is equal to the ASCII code of 0. The ASCII code of 0 is 48. Now here you are trying to print the values or the bits present in this character C as a decimal number. When you convert the bit patterns present in this C into a decimal number, what you are going to get printed is 48. Right? If you want to print it as a character, then you have to see, you have to say %c, then you are going to get it as character. Okay, fine. So whatever it is, in a string, even though you want to store 1, the actual number stored there will be the bit pattern of 49. right? Now let's see this. First thing is we are checking whether the given character in this place, in the 0th place, is between 0 and 9 or not, right? Then only we are going to start conversion. If it is not between 0 and 9, if it is some other character, it is not actually representing a number at all. Okay, now in case if it is a number between 0 and 9, if the characters are between 0 and 9, then I'll take the character and I'll subtract it from the ASCII value of 0. So what is the actual ASCII value present here? 49. Now if I write like this, it means that it represents the ASCII value of 0. Now ASCII value of 0 is 48, right? So if you see this, the 0, 1, 2, 3, 4, 5, the ASCII values of these are 48, 49, 50, 51, like this. You need not remember these ASCII values, right? Now if I want to convert the ASCII value into the actual number 1, then you take the ASCII value of 1, and then from that you are going to subtract the ASCII value of 0, this one. If I do 49 minus 48, it is going to be 1. So that is how we are going to get 1. So that is what we are going to do here. S of I minus 0. So if I do this, it is going to give you 1 here, in case if the character present is 1. Now I'll take that, and initially n is initialized to 0, I'll multiply 10 with 0, it will be 0, 0 plus 1 is 1. Therefore, for the first character which is 1 here, we are going to see in the output 1 first. We are going to see that n is going to contain 1. Again we come here, and then again we do it. If again we check whether the next one, I plus plus means the next one, is again falling between this range. In case if it is falling between this range, find out what is the value represented by this. So even though 2 is represented as ASCII value 50, I'll take this and I'll subtract from this, then I'm going to get a value 2. Then I multiply it with 10, and again I add 2. That is what is being done, right? Whatever the value of n is formed, that is multiplied with 10, and we are going to add the next value, so which is 2. Now this is going to be 12, right? And the next one is again 51, right? So let us say 1, 2, 3 is present. So whenever I plus plus is done, we are going to point to this. Again we check that is present between these two. Yes, if it is present between 0 and 9, then again I am going to find out its value. So 51 minus 48, which is 3 minus 0 means 51 minus 48. It is going to give you 3. Then I am going to multiply the n so far formed with 10, and then I am going to add 3, so it is going to be 123. So finally you are going to get 123. Next time when you increment I plus plus, you are going to point to null, and when you check if null is present between 0 and 9, this condition will fail, right? So this condition is going to fail. Whenever this condition fails, we are going to come out of the for loop. Once we come out of the for loop, we are simply going to return the value of n. So what will be returned? 123 is returned, right? So we are going to take as input a pointer to the character, and we are going to return an integer value. So what will be returned here? 123. Okay, now let's see this program. Write a C program to remove all the occurrences of a character C from a string. So what it means is, if you have a string like this, which is a character array, let us assume that it is having characters AB, CB, DB, like this, and now I want to remove a particular character from it. Let us say I want to remove the character B. Now after removing B, this entire string or this character array should get transformed to something like this: A, C, D, null. This is how it is supposed to get transformed into, right? So that is how we should write this function as. Even though it is given as a program, you cannot execute it unless you have main. So if you want to execute it, you can add main and then execute it. So let's see this function as it is. Now this function is going to take, or I'll just explain the logic first. So what we do is, we shall start with 2 pointers or 2 indices, you can call them. Now both of them will be starting with the beginning, right? And whenever we get a character which has to be replaced, one of them is going to stop there, right? And the other one will go and search for the next character which is useful, right? Whenever we see the useless character that has to be deleted, we are going to stop there, and useful character we are going to, whenever we see that useful character, we copy it here, right, like this. okay, and then this one is going to be incremented like that. Okay, so we shall see the logic and we'll understand it better. So first thing is void, it is not returning anything, and squeeze is the name of the function, and one of the argument is char s array. So it is nothing but declaring s as a character pointer. Got it? So char s array, I mean this way of declaration is nothing but declaring s as a character pointer. In fact, is a definition as well, which means s is a variable and it is created in the space storage is allocated for s. And now int c. So as the second argument, we are passing an integer value which is nothing but the ASCII value of the character that we want to replace. Okay, int I comma j for I equal to j equal to 0, s of I not equal to null I plus plus. So initially we'll initialize I and j to 0. In case if we use I and j to index this array, it means that both of them are going to point to the same value here. These are the indices. Okay, let's say 6. Now both of them are initialized to 0, and I'll check whether s of I is equal to null or not, which means whether we have reached the end of the string or not. In case if we have not reached the end of the string, then I'll execute this statement. If s of I is not equal to c, which means I'll see whether this particular character has to be deleted or not, right? In case if it is not, if it is not to be deleted, right? Yes, it should not be deleted. Then in this case it is doing s of j plus plus equal to I. So if you have to understand this statement, it means that first use the value of j and store into s of j whatever value you want to store, in this case s of I, and after that is over you increment the value of j. So in this case when I equal to 0, j equal to 0, it means that it is as good as writing this way, right? S of j is equal to s of I, and after this is done, j plus plus. So this is as good as writing it this way if you are not able to understand it that way. Anyway, we have seen how the post increment is going to work. The value of j will be used, yes, the value of j is used, and after that incrementation is done, right? Okay, now see this, what will happen here? Simply s of j, which means s of 0 will be equal to s of again I is also 0, so nothing is going to happen there, right? But then j is going to be incremented, so j is going to the next one, right? And we come out of the for loop. For loop has only these two statements. We come out of the for loop, which means the body of the for loop is over. Again we go into the condition here, I plus plus, I will be incremented, so I is going to be here, right? And again we get into this for loop body because s of I is not equal to null, and now I'll check whether s of I is not equal to c, which means whether should I replace this c or not. So is s of I equal to c? So if you see this s of I, it is equal to the character that has to be deleted, isn't it? C is the character that has to be deleted. Its ASCII value is same. Now we are going to come out of it because it is not equal, and again I'll come out of the body and I do I plus plus, therefore I is going to be incremented. Now if you observe it, what has happened is clearly we have found out the character that has to be deleted and j will be pointing to it, and now I is incremented in such a way that it will find a useful character, and once it finds a useful character, next time this character will be replaced with this character. That is the logic behind it. Okay, now see this. Now what happened? I plus plus has been done, right? And again we enter it, s of I is not equal to null, and now I'll check whether this is useful character or not. I is pointing a useful character, isn't it? In case if it is pointing the useful character, then you copy this useful character into this useless place, right? So which means this useless character will be replaced by useful character C. After doing this replacement, j will be incremented. J will be incremented, and now what will happen to I? Again we come here and I will be incremented, right? Now again I'll test whether s of I is equal to null or not, whether we have reached the end or not. Yes, we have not yet reached the end, therefore again I'll enter it and I'll check whether I is pointing to a useless character, right? Yes, I is not pointing to useless character, right? S of I is not equal to C. Yes, S of I is not equal to C, isn't it? What is C here? If you are getting confused, I am writing this, right? Just check whether S of I is not equal to B, but S of I is equal to B, therefore we are not going to enter it, and again I am going to do I plus plus, therefore I will be incremented, so I will be here, right? And again I'll check whether S of I is not equal to null or not. S of I is not equal to null, and again I'll get into this and I'll check whether S of I is not equal to B. Yes, S of I is not equal to B, right? Why? Because it is not useless character. Now in that case, S of I, if it is not equal to B, now I'll just copy whatever is pointed in this I into J. So whatever is present here, it will be copied here. Okay, and after that J is incremented, which means J is going to point to this, right? And after this I is going to be incremented, so I is going to point to this. Now again we will see if S of I is equal to null or not. It is not equal to null. Again we will see S of I is not equal to B, but it is equal to B, it will not get executed. Again I'll go here, right? I plus plus. Now finally I is again incremented, right? So, and again I'll test whether S of I is not equal to null. Yes, S of I is not equal to, sorry, S of I is in this case is equal to null, therefore we come out of the for loop completely. After coming out of the for loop, now S of J is equal to null, which means this one is made null, right? Therefore the string is containing only A, C, D, null. Even though we have other characters here, we generally read only till the null, therefore the string is supposed to be terminated here, right? So if you observe it clearly, initial string is AB, CB, DB. Now after replacing this B, 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 whatever is remaining, only A, C, D is remaining, and after that null is there. Got it? Okay. Now let's see this function. Int main, register int I equal to 10, int star A equal to ampersand I, printf percentile D star A, return 0. And now if you observe it, we are using the storage class. So register and register, extern, and the other one is static. These are called as storage classes. Okay, so register is a keyword which is called as a storage class. When it is applied while defining a variable, it means that we are telling the compiler to store this variable in a register. Okay, now if that is, let us say, some compilers will follow your advice and they will store the integer not in the activation record. It will store it, let us say, in a register. Now once you have stored the I in a register, when you try to get the address of I, you are actually asking the address of a register. Generally memory elements will have the addresses, but registers might not have the addresses. Now you are trying to find out the address of the register and you are trying to put it in the variable A, right? But this is the problem, isn't it? So some compilers might have already stored the variable in a register and they will not be able to get out the address of a register, and so some compilers might give error and some compilers might give warning. Okay, so it is compiler dependent and you are not supposed to write the program like this. Some of them might execute it, some of them might give warnings. And the other one is, let's see the next one, similar type. Now int I, so it means that I is created inside the activation record, and so it is going to have an address. Let us say the address that I has is M, and this is the activation record created for main inside this stack. And since I is an automatic or local variable, it will be created inside this stack, and so it is going to have some address. Now we are going to have one more variable which is a pointer to an integer whose storage class is given as register, right? Which means we are telling the compiler to store the value, to store the variable A in the register and not here, right? Now depending on the compiler, it might either take your advice or it might not take the advice. If it takes your advice, it is going to store it in the register. Otherwise it is going to store this variable in the activation record of the main. Now it is going to accept the address of I. Now what is the address of I? 100. So if it is going to be stored in the activation record in the memory, 100 will be accepted, or if it is stored in the register, let us say inside the register, A is stored, this is the register, 100 will be there. So either A will be in the register or in here. So whatever it is, A is having some storage and it is capable of holding the value that you are trying to store there. Now printf %d star A means whatever value is present in A, that is the address of other variable, you go to that address and you print the value which is present there. Let us say here the value present is 1, then in this case 1 will be printed. Got it? So here you will not face any problem, right? Because you are not asking for the address of the variable which has to be stored in the register. In fact, you are storing the address of other variable inside a variable which is either stored in the register or here. Okay, now let's look at this program. Now int main int I equal to 10, register static int I equal to 10. Now static is a storage class, register is a storage class. Now by saying static, you are explicitly asking the compiler to store this variable in the data section. Now by putting register, you are again asking it to store it in the register. So you are asking it to store it at two places. You cannot say that, right? So this one will give you compiler error. Okay, fine. Now let's see an example where I want to call a function and then I want to call it many times, and after it is done I want to count number of times I have called it, right? So let us say example is here. Now int count function call. So this is the function which I will be calling many times, and then later I want to find out how many times I have called it exactly, right? So int count function call void, it is not going to take anything but it is going to return int count equal to 0. So initially we have a local variable which is going to be initialized to 0, and the only purpose of this function is it will simply increment the count and it will keep on sending us. Okay, now see this. Now int main, we have called the function once. So this function is called once, and then this function is called second time, and then the function is called third time. So 3 times it has been called, and 4th time I am again calling it. And see, whenever you are calling the function is actually returning something, but then we are not catching it in any variable. That is perfectly legal. You need not catch it in any variable, you can leave it. And printf %d %d times function is called, count function call, that is it. So return 0. Now if you observe it, what we can do here is, what is done here is, initially in this stack main will be done, right? This is the, let us say, activation record for the main. Now what are the local variables of this main? There are no local variables, right? So what will generally this activation record contain is, one is all the local variables as well as the return address, which means from here if it goes to any function call, once it comes back, what is the address it should execute, that is also going to be present there. Now let me write for just for the sake of simplicity, let us say the address of this one is 1 2 3 4, something like this. So now first this one will be called. Now when you call this function, activation record will be created for this function, right? Now what is the activation record? Here it is for count function call. Let us say this is the activation record for this one. Now what will happen here is, in this function whatever are the local variables, they all will be created here. So the local variable is given a copy here, count. Got it? Now count is initialized to 0. In case if you don't initialize it to 0, what happens is always the local variables will have garbage value, right? And the global variables and static variables will always be initialized to zeros. Okay, so now here, since you have initialized, you have initialized it, it is going to get a 0, and then it is going to increment it, right? Plus count means increment it, and it is going to return that number, right? So it is going to return whatever is incremented. So what will be returned? 1 will be returned, but you are not catching it here. Now this is over. So once this function is over, this activation record will be completely popped off, and from the next line your main is going to execute, right? So the main is again going to call the same function. Then again one more activation record will be created for the same one, right? and now one more copy, fresh copy of the variable count will be created, and that count will be given a value 0, and count plus plus means it will be incremented by 1, right, and it is done. Got it? Now once it is done, again this value will be popped off, right, and again you are going to call it third time. Now when you are going to call it third time, again the same thing is going to happen, right? So one more copy of count is going to be created and its value will be 0, and when you increment it, its value is going to be 1, and again this is going to be over. Now again you are calling it one more time here, right? Printf will be called, which means for printf also activation record will be done, and printf is going to call count. So again count is going to be done here, and which is going to contain its own copy, right? Fresh copy will be created. It will be initially 0 and it will be incremented by 1, and once it is done, it is over, right? So what will be written by this 1? So it will be written to the printf, and printf is going to print percentile d. If you observe it, printf is also a function call. That is why one activation record is created for printf as well, right? Now printf, this is going to print that one time. So percentile d means whatever it has written simply 1, therefore it is going to print 1 times function is called, right? 1 times the function is called, that is what is going to be printed. Even though we have counted, we have called it 4 times, finally we are going to get the answer as 1 time it is called. Why did this happen is, if you see this count, it is not able to retain the value. Every time it is going to create a new copy, and that new copy is actually used, right? So that is why it is not able to retain the value. If it has to retain the value, it is better that you declare it as some other variable, right? Instead of automatic or local variable, let us say we want to make it static variable, right? So if I make it static, then what happens is, instead of creating the count here, it will be, and static variables and global variables will already be initialized to 0, you need not initialize it, right? Now it will be created in the data part. It will not be created in the stack, it will be created in the data section, right? In the data section, count will be created, and initially when you do plus plus, 0 will be made 1, and for the second call this 1 will be made 2, which means there will be no local variable, it will be accessing this static variable, and the third time this 2 will be made 3, and the fourth time this 3 will be made 4, and 4 will be returned and 4 will be printed. Got it? So by using this static storage class, we are able to retain this variable because we are creating the copy, or we are allocating the memory for this variable in the data section and not in the stack. Got it? Okay. Now till now we have seen variables which are getting space allocated at various places in the process. Now we have seen something like this. If this is a process, assume that this is a process, let us say this is text section, and then there is data section in which global variables and static variables are going to be allocated space here, right? And now automatic variables or internal variables, which means the local variables, will be allocated space in the stack, right? And the stack grows like this. Now there is one more part called as heap, right? So exactly how big is heap, that depends on whether stack takes up more space or heaps takes up more space. Now this heap is used for, this is the space, right? And now this heap is used for dynamically created data structures. Sometimes you wish to create some variables dynamically and then you want to use it. So what are the various reasons for them to be created dynamically is, one is maybe before starting the program you don't know how much space is required. In that case we cannot have the arrays, that is why we go with dynamic memory allocation techniques. And other thing is, you might not need that variable throughout the execution of the program, and also you don't know the size. In that case also you go with the dynamically allocated memory, and once you are done with the usage you will be freeing it up, right? So now what I mean to say is, either local variables or global variables, you need not do anything specially to create the space for them. but then for the dynamically created variables or the data structures, you are supposed to create this space, right? So how is that space creation space is allocated, and how to manage that is by using these functions, right? And these functions, malloc, calloc and realloc. So these functions are actually defined in the stdlib standard library, stdlib, and then if you are going to use these functions without declaring them, you better include the file hash include stdlib.h. okay. Now let's see what is how each one is used and what is it trying to solve. Now if you see this malloc size underscore t n void star. Now it means that this is name of the function, okay, this is the name of the function. Now we are sending to it as a parameter a variable or a number which is unsigned, whose size is at least 16 bits. Now what is size underscore t is, it stands for any data type which is unsigned and whose size is at least 16 bits, okay. Now you can also send an integer. Now if I say malloc 10, then what will it give is, if I say malloc 10, then it is going to allocate in the heap a size of 10 bytes, okay, and now it is going to give you the pointer, which means the starting address of this space is going to be returned. Now if you look at the return type, it is returned as void star, which means you can use it to store any data type. Therefore, depending on what data types you are planning on storing there, you can just do the typecasting and then you can store it there. For example, if I write like this, int star I, then I equal to malloc size of, let's say, int, okay. Size of is an operator which is going to return any a variable of type, or which is going to return a number which is a positive and which is going to take at least 16 bits, which means of this type, size underscore t. Now it is going to give you the size of the int. Let us say the size of the int in your machine is 2. Now what does malloc do? It will create 2 bytes of 2 bytes in the heap, 2 byte space in heap. And now let us say the address of the first byte is 100. Now 100 will be returned. Therefore, what is returned to you? You are going to get a pointer, right? See, this one is nothing but the address. Now the address type actually returned here is a void star, isn't it? Void pointer. But then actually you are going to store in it an integer, and later you want to access this space as an integer, right? That is why you just use the typecasting and you convert it into integer star, right, integer pointer, and you store it here. Now why is this thing important is, later when you try to access the elements in this, now the elements in this will be a contiguous blocks of zeros and ones. Now how to interpret it, whether to interpret it as a character or an integer, that depends on how you have declared here and how you are going to access here, right? So if I say I plus plus, see why is it important is, you will understand here. If I say I plus plus, now should I increment the I by either 2 bytes or 1 byte or 4 bytes, depend on what is the size of I is, and that depends on what is the pointer that you have used here, whether it is an integer pointer or a character pointer. If it's a character pointer, it means that all the elements present here are characters, and when I do I plus plus, it has to be incremented by only 1. If it is an integer, right, let's say if it is integer, everything has to be incremented by 2 in case if the integer size is 2, right? Therefore, declaring some pointer and then converting this return type is important. And also if you observe it, it is going to give you this pointer of the address of the first byte of the memory dedicated or allocated to you. And in case if it is not able to allocate the memory, let's say because the heap is out of space, which means there is no space in the heap, that is why it is not able to allocate the memory. In that case, what it will return is simply null. Got it? So that is why after you use this malloc, you are supposed to check what it has returned. In case if it has returned null, then you should not go and access, or you should not store anything at that pointer. Got it? And the next one is calloc. Now CAlloc is exactly similar to malloc, but here we are going to say the size in a different way, right? So here you have directly given the size that you wanted, but here you are going to say how much space you want to allocate in a different way. Now you are going to say how many elements that you want to store and what is the each size of each element that you want to store there, right? For example, if I say 2 comma 2, it means that I want to store in this space 2 elements each of size 2, therefore totally you are asking for 4 bytes. Got it? If I say 10 comma 2, now it means that I want to store in this space 10 elements and the size of each element is 2 bytes, therefore you want 20 bytes, right? So this is one other way of specifying what you want to, how many bytes you want. Got it? Now what is the main difference between malloc and CAlloc is, if you use CAlloc, it is going to create this space and it is going to give you the pointer to the starting address of the space. Along with that, it is going to initialize all the all that space to 0, which means if you look at malloc, garbage values will be present there if you don't initialize it explicitly, but if you look at CAlloc, it will give you this space as well as it will initialize the entire space to zeros before it give you. That is the difference. Got it? And again the same thing, it is going to give you the pointer which is nothing but the address of the starting byte in the space allocated, right? And one more thing, either malloc or CAlloc will always give you the space in a contiguous manner. In case if the space is not present in one contiguous block, it is not going to give you the space, right? Let us say you want 20 bytes and assume that 10 bytes is free here and 10 bytes is free here. It is not going to give you these two blocks. It will actually give you 20 blocks if you have 20 bytes if available, or it will not say, or it will just simply give null, which means memory is not available. Got it? Okay. Now again, if you are going to use CAlloc, you have to do the typecasting as I told you here. So either you want to convert it to, you want to store it in an int pointer or char pointer depending on that. And the next one is realloc. Realloc means, let us say already you have been allocated some space. Assume that already you have been allocated some space which is 10 bytes, okay, using malloc, and now you have already used it and you have filled it with some values. Let us say all the values or data is filled. Now you want to extend it, okay, you want to change the size of it to 20 bytes. Then what you can do is void realloc. You just send the pointer which is pointing to the starting address of it to this function. Along with that, you just specify what is the size you want that space to grow. Let us say initially it is 10 bytes. Now you want it to grow to 20 bytes. Then you can say that I want to grow it to 20, right? Then what will your what will happen here is, it will try to expand it to 20 bytes in case if this space is freely available here. Otherwise, at some other location, it will create 20 bytes and it will copy the initial 10 bytes into this without losing the information. Got it? So that is what is going to be done with realloc. If it is not able to find that much space, it will simply return null, right? And the next one is free. Now free is used to free up the space once you are done using this, right? Let us say you have got some space using malloc and you are done with the usage. Then you can simply say free that space, right? Free with that pointer, if you call it, then it is going to free the space which is earlier allocated to you. Now one thing is, one problem here is, how will free know? See, what does this PTR contain? The starting address of the space that has to be freed up, isn't it? Now, how will this free function know where till what point it has to free up, right? So just to answer that, now either while using malloc or CAlloc, let us say you want to create 10 bytes, then instead of creating 10 bytes, actually one more location, which means 11 bytes, or it is system dependent, right? Some extra space will be created for you, and in this extra space which is allocated, it is going to store how many bytes has been allocated for this, when you call this malloc. Later free will read that information, and free will only free those many bytes initially allocated. Got it? So that is how free is going to be useful. Now if you don't free up this space regularly, what happens is, even if you are not using a space, that space will still be reserved for you, and it will not be given, it will not be reused later, right? That is called as memory leak problem. To avoid memory leak problem, you are going to use free. Okay, it is a kind of garbage collection. Okay, let's not look at that garbage collection now. You can understand that it is just used to free up the space which has been allocated earlier, right? Okay. Sometimes it so happens that we might have to group things of different types. Like in arrays, if you see an array is a group of more than one element, isn't it? If I have integers, let us say I want a group of 10 integers to be together, then I could write an array of 10 integers. But sometimes it so happens that the group of elements, or the elements which I want to keep in one group, organize in one group, might not be of same type, right? Then in that case, structures are going to be very, very useful. So structures are going to be a kind of grouping. I mean, if you want to group different elements, we are going to use structure. It is you can think of it this way. The classic example is, if you want to store an employee record. So if you want to store everything about an employee, he will have a name, so therefore we need a string which is a character array, and he will have an age, and maybe he will have a salary, right? So, and he will have an address. So there are various things that he might have. Therefore I want to put all these parameters in just one place, and I want to give it one name, and I want to keep it together, right? So that it will be meaningful for me to watch it, rather than declaring various types of data structures and keeping them at various places and then organizing with different names. If I have them at one place, it will be better, right? So, and if for this reason we have a special data structure which is called as structures, right? So the way we declare struct is like this. Let us say I want to put together a character and an integer. I want to put them together tightly. Okay, then what I do is I'll define something like this: struct, okay, int I, let's say, and char c, right? So this is the declaration, which means just like int, see, just like int, it is also a declaration of a data structure. Now we could create any variables of this data structure, just like int. So you know this, right? So I could create integer variables like this: int x comma y comma z, isn't it? Similarly, just like this, I could even create x comma y comma z. So what happens is, because of this definition, there will be three structures created with the name x, y and z, right? So what will these three structures will have is, x is now a structure which will have inside it an integer with name I and a character with name c. Similarly, y is now a structure which will have two elements. One will have name I and other will have name c. And z is now a structure which will have two variables. One is integer and other is character c, right? So this is how you can visualize it. So this entire part, see, this the name struct followed by the open brace and then close brace, this closed curly brace or the right brace, and inside this there are a list of declarations. Now this entire thing will define a structure. Now this definition, right, which means writing like this, is going to create three structures, and three structures will have all these members, right? And now you can access any member using the member operator. For example, if you want to write something in this, then you can call it like this: x dot I equal to 10, then this will be written, or x dot c equal to a, then a will be written here. Got it? So this is how you could access. So every structure is going to have some members inside it. These are called as structure members, right? And in order to access it, I am going to use the dot. This is called as member operator. Member operator. So member operator is used as a connection between structure name and the structure member. Why should you use it is because without using the structure member, if you observe it, see, I is there in three places, right? Integer I is there in three places. Now whenever you refer to I, which I are you referring to? So just to distinguish it, you are even supposed to have the name of the structure followed by a dot followed by the member name, right? And now let us say you, after writing this, at some point of time or later, if you want to do any again this kind of declaration, let us say you want to declare another variable, or you got to define another variable of type this structure, then again you have to write this entire thing and then write this, isn't it? Or let us say you want to define a structure which contains a structure, then what happens? Now you have to define, see, let us say you have to define one more structure, struct, which contains inside it this entire structure. Then what should I write? I should again write struct, and then I should write int c, and like this. So this entire writing, this is going to be tedious. Therefore what I try to do is, we shall write a name for this structure, which is actually optional. You need not write it, but then it helps if you write a name. Let us say struct, let us say example ex, struct ex. So if I write struct ex followed by this curly braces, then this is called as a tag. Okay, this is called as a tag, this particular thing, right? Now having a tag is going to be useful, because later when you try to refer this, or later if you try to declare any other variable, you can simply use struct followed by tag. Or I'll tell you this, see this, you need not declare all the variables here. What you could do is, you could just declare the structure. If I write like this, what happens is, this is called as template, right? Template or blueprint. So by writing like this, I'm just trying to declare that this structure is having this form, and this one is going to be the tag, right? By writing like this, no memory is actually created to any variable. Later the advantage is, I can write like this, struct, I can define structures using this tag without writing everything. Now I can write example x, y, z. Now by writing this declaration and then by using this kind of definition, what happens is, now x, y and z are the three variables, are the three structures for which actual memory will be allocated. So by writing like this, it will be useful to use the shortcut like this. Okay, you need not use the entire declarations again. So this is just a kind of shortcut. Okay, and anyway here no memory is allocated, that is why it is called as a blueprint or prototype. And this one is actually definition where space will be allocated. Got it? And again you can access the members like this. So anyway the tag is optional. Okay, and now let us say you want to declare nested structures. Then what happens is, you can directly use the tag and you can declare it. See this? Now I am writing one more tag, struct example1. Okay, this is again the tag, and I am declaring all the members of it. The members of a structure can even be other structures. Let us say the member of this is struct this one, and a. Okay, before going to this, let's talk about how to initialize them directly. Sometimes what happens is, you can even initialize them directly. So you need not, let us say I want to define a structure x, and even I want to initialize it. Then initializing is simple. You can write like this, and first member is integer. Okay, see, now structure example is this one. First member is integer and second member is character. Now I am going to write structure example, and in this I am going to define a variable which is of type structure, which contains these two variables inside, and so I am going to initialize them like this. So first one is integer and second one is character. So this is called as initialization. So you can even initialize it like that. Now I'm trying to declare one more structure which contains as members the structure of other type, right? Then struct example1, it contains two members A and B. Okay, by writing like this is again a declaration, just a prototype. No memory will be actually allocated. It is saying that example1 is a structure which contains inside it two structures, both are of type example only, right? Then what happens is you can create a variable for this. Next time, see, now I can create a structure of type x1 example1. Let us say the name is T, right? Then what happens is a structure will be created which contains T, and inside that there will be two structures, right? So one is A and other is B, and inside A there will be I and there will be C, right? And inside B there will be I and there will be C. Now how to access each one is, watch it. Now A is a member of T, therefore to first you have to access A, so T dot A, and now if you have to access I, then T dot A dot I. So if I write T dot A dot I equal to 10, it means that this value will be taken as 10, right? Or you can write T dot A dot C, which means this one. T dot A means this one and A dot C means this one. T dot A equal to small a, then you can go here, right? So like this you can define any number, any levels of nesting, right? This is called as nested structures, right? So this is how you can you can declare the structures, and then you can declare the variables, and maybe you can access them using the members. Got it? Fine. I formed this question combining this structures, arrays, pointers and this access members, access these operators like dot and this. Okay, so anyway, if you can answer this question, you will be able to answer any question in GATE. Combine questions combining structures and pointers. That way I formed it, and it is not very easy to understand. But what I suggest you is, you please, if you don't understand anything, you please rewind the video and watch it over and again. Okay. So before going ahead, before solving this difficult question, I'll just take some few small examples, and we shall practice on that. We shall understand the concept, then we shall solve this one. Okay. So before solving this, let's solve some small questions. See this. Now let us say I have a structure. Okay. Let me call it as node, some structure. Okay. And in this I have two members. This is the tag, this is the structure, this is the tag, and I am writing and I am declaring the members. Inside it I have two members, int I and int j. These two are integer members, right? And this is how I define the structure, right? So this is called declaration and or prototype or template, whatever, but then no memory will be allocated to this, right? And now I'll try to declare this is called definition. Okay, so definition is where, when say declaration generally memory will not be allocated, but definition is where memory will be allocated. Coming to structures. Okay, so struct node, let us say A is a structure and P is a pointer. Okay, so what is the meaning of this? So I think you remember how we associate the precedence. So A is nothing but the structure node, a structure of type node, right? So that is A is a structure of type node. And what is P? P is a pointer. Okay, so P is a pointer which points to a structure of type node. That is the meaning of it. Now whenever I write like this, what happens is a structure will be created. It is better you visualize the structure like this. Inside this structure, see, I'm just visualizing it. Actually in memory what happens is, in the contiguous array of cells, integer I will be created and integer j will be created. Okay, fine. So this is what happens in reality, but what I'm trying to do is I'm trying to visualize it in a different way. Okay, this is what happens in reality. Okay, so you just visualize the structure like this because it helps me later on for you to explain many things. I and j, let's visualize like this, right? And now so this is A and whenever I declare p is simply a pointer, that's it. So p is nothing but a pointer, nothing more, right? So both are, this is uninitialized and this is uninitialized, and they are not containing anything, right? And now if I say p equal to ampersand of a, right, it means that you take the address of a and you put it in p, and you can do it because p is a pointer which is capable of holding an address to a structure of type node, and a is a structure of type node, isn't it? P is already a pointer to a structure of type node, and a is a structure of type node, therefore I can put the address of a in p. So this particular move is going to take the address. Let us say address of this one is 100, starting address is 100. Now 100 will be kept here, which is nothing but p will be pointing to this. Got it? Now if I have to access I, how can I access I? Is one thing is directly I can write like this, a dot I, isn't it? A dot I is nothing but a is the structure and then I, this is the access operator, isn't member operator, therefore I can access I. Fine. If I want to use p and access I, that is bit tricky. See this? Now if I want to use p and access I, see, one way of accessing is a dot I, fine, it works. And now if I want to access this I using p, then what I'll try to do is, if I use the name p, see this, if I use the name p, right, it is nothing but 100, which means I'll be inside this. Whenever I use the name of a variable, I'll be inside the variable. Inside the variable means I'm having this, right, having the number 100. So having an address 100 is as good as standing here, right, standing outside the structure. Standing inside this pointer which is containing the address is as good as standing outside the structure. Now in order to access I should get into the structure, right? So that is why I should put a star. So when I put a star, I'll get into the structure, which means I'll be standing inside it, right? And after getting into it, I have to access I, therefore dot I. So this is going to access I. But then there is a small problem here. While writing, I know that I have to get into the pointer and then access I, fine. But then if you look at the associativity, the precedence of the operators, the first row contains the member operator, right? The member operator means this dot. Dot is present in the first row and star is present in the second row. Therefore, the implied parenthesization, which means our compiler will parenthesize it this way, which means it will take like this and then like this. This is what our compiler will do. Then what happens? Compiler will, by writing like this, compiler is thinking that p itself is not a pointer, p is a structure which is having a member I, which is actually wrong here, isn't it? P is not a structure, p is a pointer, therefore first thing that has to be evaluated is star p, not p dot I, right? So if you directly declare it and leave it, then it is going to be a mistake. So what you are supposed to do is, even though star p dot I according to you means that p is a pointer, now by putting star p, jump into the structure pointed by p and then access I. You should not write like this. You should even give the parenthesis, which means you are supposed to write like this. By writing like this, what happens is, initially you will be taking p, which means you will be inside p, and inside inside the p as good as standing outside the structure, which means you will be here, right? And now you try to jump into it by putting a star. So you are inside it, and after jumping into the structure, you can access the member, which means dot I. This way it is fine. Understood this? So star p dot I has to be used in order to access this. So maybe you might now think that accessing a member of a structure using the pointer is complex. Using the name is simple, isn't it? So a dot I is simple, right? And these two are equivalent actually. So both are actually accessing the same member I. Now you might feel that, why are we using a pointer and then star and then this? I could have used this, right? But still, using the pointers is very, very popular and very frequent in C programming language. The reason is, most of the times these structures are dynamically created, and whenever a structure is dynamically created or anything is dynamically created by using malloc, they will not get the name. What they get is the address. So whenever you want to access any element through address, we have to go through pointers only. Therefore, even though it looks so tedious, it is very popular and very frequent in C programming language. then what the designers thought is, no, when this is going to be used so many times, why should we burden the people, the programmers with this? So they have introduced one more operator like this, right? So they have said that if you write with a minus and greater than symbol, if you write this operator, right, it is equivalent to this, which means it will be easier to type and it will be easier to read also, right? So p arrow I is nothing but, if p is a pointer, then we can access the element I inside the structure pointed by p, right, without bothering about all this. So from now on, if there is a pointer, then I am going to use this operator without any parenthesis, right? And then one thing you should observe is, now either dot or this arrow, right, both are defined in the first row, right? Therefore they are having highest precedence compared to any other operator. So in the first row, if you remember, what are all the operators in the first row? One is function calling or parenthesis, and other is array subscripting, and the other is dot, member of operator, and the other is this shorthand, right? So this shorthand operator, right? So these are all in the first row, right? Therefore they are supposed to get the highest priority. And next thing is, since they are all having the highest priority, and moreover they are having left to right associativity, which means if in a single row or in a single statement, if you find all these operators, then you are supposed to evaluate them left to right. Got it? So now just remember it. We can assign a pointer, we can take the address of a structure using ampersand. Therefore applying ampersand to a structure name is perfectly legal, and which is going to give you the address of the structure. And then we can assign this address of the structure to a pointer. It is also illegal, and then it is also legal, okay? And next thing is, once you have the pointer, right, you can access the elements of the structure by using like this star p dot I, or if you feel that it is too long and boring and tedious, then you can obviously use this one. Got it? Or if you have the name, it is better that you go with the name, and most of the cases we don't have the name, right? So I hope that you understood this example. That is how we access the members, right? And everything else is same. So now if you understood this, let's solve this question. So what I'll try to do is, okay, fine, so let's solve this one first. Now what I'll do is, okay, before that, structures can be passed to a function as well as it can be returned by a function. So whenever you are passing a structure, so what happens is the entire structure will be copied. So say this. So let us say this is a structure is a node, and this says that fun is a function which is taking two arguments, and both the arguments are structures of type node, and moreover fun is returning a function, a structure of type node. That is the meaning of it. Are you understanding it? Fun is a function which is taking two arguments, and both the arguments are structures of type node, and moreover it is returning a function, it is returning a structure of type node. So what is the meaning of it is, how does this happen is, whenever you call this this function with two nodes, all the values of that particular actual arguments will be copied onto these formal arguments. So in case if your structure is very big, then just this function call is going to be very costly, because the entire two structures have to be copied from the calling function to the called function inside this function. So because of this reason, yes, copying is a legal operation on structures. Copying can be done, and moreover when it is returning the function, see this, whenever you return a function, it will be assigned to some other function, that is called assigning. So you can assign a structure to other structure. So in that case also everything will be copied. So whenever your structures are too big, then passing it to a function and returning it by a function is going to be costly, because lot of copying is involved. So it is suggestible that, generally people suggest that you go with the pointers. So if you want to send a function, if you want to send a structure, don't send the entire structure, because it is going to take a lot of copying. You just send the pointers to the structure. That is what many people will do. Okay. So anyway, that is what my intention is in writing this line is. This line has nothing to do with this program. This line says this syntax which is used to send the structures and then receive the structures, and really no good programmer will use it. Everyone will use the pointers to the structures. Okay, so now let's see this one. So now what I want to explain from this is I'll try to see this entire program, right, this one, and I'll show you what will happen by the end of this all these lines, and then I'll take each line and then I'll show you what is the effect of that line if this is the context. Okay, so now from here to here I'll just declare all the variables and then assign the pointers and everything, and later I'll take the lines one by one and then I'll show you what happens. Okay, so as an exercise what you do is you can pause the video here and you copy the program and you try it on your own, and later we shall verify what happens. Okay, that way you can even practice it. So first of all, struct node, it is a declaration. See, struct node, it is saying that a node is a structure which is this is the tag and is containing two declarations, which means it is having two members. One is integer and other is pointer to an integer. These are the two members present in this structure. And next thing is they are defining some variables. So struct node a of 2. So it means that a is an array. Okay, so how can you know that a is an array or not? Because there is subscription, right? So it is saying that a is an array of two elements and both are array. These two elements are of type struct node. So which is nothing but what they mean to say is this a is defined as an array of structures and there are two members in it. So each member is a structure. And the next one is star p. Star p says that p is a pointer to a structure of type node. Okay, so a is an array of structures of type node, and moreover p is a pointer to a structure of node a. So let's see how it works. Now you can think of a like this. A is an array of two structures, right, and each structure is going to contain two elements, right? So one is I and the other is C, and similarly here also this is A and this is A of 0 and A of 1, isn't it? So this is A of 0 and this is A of 1 and I and C. So this is how you could declare a array of structures. A is an array of structures, right? And what about this? P is a pointer to a structure. So which means P is a pointer to a structure of type node. That's it. And now what about the next one? Integer B. So there is an array B of two elements, which means there is an array B of two integers. That's it. So two integers, and it is already initialized to 30 and 40. So this one is 30 and this one is 40. And next one is P equal to ampersand A of 0, which is nothing but P is now assigned with the address of A of 0. So let us assume that the address of this one is, okay, now let us say this one is 2 bytes and this one is 2 bytes, this one is 2 bytes and this one is 2 bytes. If that is the case, what is the size of each structure? Each structure is 4 bytes. And assume that this is starting with 100, then what is the address of this one? 104, isn't it? So there will be 4 bytes here and 4 bytes here, right? And now this line is saying that P equal to ampersand A of 0, which means you take the array A, right, A of 0, and you take the address of this, which is 100, and you put it in P. So P is going to contain 100, right, and it is going to point to this P equal to ampersand A of 0. And next one is A of 0 dot I equal to 10. It is interesting. Watch it. A of 0, right, dot I equal to 10. So what is the meaning of it? Actually, how many operators are there? There are two operators. One is array subscripting and other is dot. Isn't it? There are two operators. One is array subscripting right here and the other one is dot. So out of these two operators, which one is having higher priority? So you know that both the operators are having the same priority, isn't it? In the first row, this function calling, array subscript, dot, and this all are in the first row. Therefore, all of them have the same priority. Now, when they have the same priority, which one should I execute first? Then you go in left to right, right? Because associativity says left to right. Therefore, this one has to be executed first, and then this one. So what is the meaning of it? Go to a of 0, right? So when I go to a of 0, I'll be here, a of 0, and then you go into I, which means I'll be here. It is initialized to 10. This one is initialized to 10. That is the meaning of this. And the next one is a of 1 dot I equal to 20, which means this is initialized to 20, right? And the next one is a of I dot C equal to B, okay, which means, sorry, a of 0 means this one, dot C means this one, equal to B. What is B? B is an array. So whenever B is an array, what do we get from its name? From its name we get the starting address of the array, isn't it? Therefore this one is going to point to this. Got it? So this is the entire declaration. So till this line, this is the chain of links we got. What happened? See, now P is a pointer which points to a structure of type node, and then there is an array of two structures, and then one of the structure member is a pointer to a integer which is pointing to an array of integers. So this is the chain we got till here. Now what I want you to do is, or what I'll do is, I'll take this, all these lines one by one, and I'll try to execute and then show what happens. I don't want to do all that at once. I'll take them one by one, and I just want to show you what happens. Okay? What? Okay. Okay. So now what I'll try to do is, I'll take these lines one by one, right, and I execute them. And after executing a line, I'll just I'll just have erase all the effects, and I'll act as if that line has never happened. Okay, so now I want to see what is the effect of this one on this entire context. Okay, so the first one is plus plus p I. So whenever any such complex expression is given, so one thing you should observe is how many operators are there and what is their priority, right, precedence. So now there are two operators. One is plus plus, which is unary operator, which is present in the second row, and the other one is this array accessing, this structure accessing, right, with a pointer. Now this one is in the first row, this one is in the second row in the table which I have given. Therefore this one has to be evaluated first. So the implied parenthesis is like this. Even though you didn't do anything, you don't say anything, this is already implied, right? Then what is the meaning of it? Go into the structure pointed by P and then get the element I. So which means you will be standing inside I, which is pointed by P. So P is pointing this, therefore you will be standing here, and then they are doing plus plus, which means you increment it. So because of this line, this particular element will be incremented. From 10 it will be made 11. I think it is clear, right? So what I mean to say, what happened is, this line is nothing but P, whatever P is pointing to, P arrow means get into the structure and then get into that particular variable. So it is nothing but I am getting here, and now plus plus, which means I am incrementing it. Initially it was 10, I incremented it to 11. That is the meaning of the first statement. Fine. Again let's restore it. Let's say it is 10 only. Now let's take the second. See, it's not a program. I just wanted to explain you what is the effect of each line. So first line has produced an effect that I value, which is pointed by P, has incremented by 1. Now I want to see the second line. What is the second line? Watch it. X equal to plus plus P and then I, right? Okay. So what is the meaning of it? So earlier what happened was, there was no parenthesis, right? When there was no parenthesis, then which got actual, say earlier I have given this, the earlier line, right? Then we parenthesized, the implicit parenthesis says that you have to go into this P and then do it, but now there is parenthesis, which means you are not supposed to perform this operation, you are supposed to perform this operation. And moreover, this is a pre-increment. So whenever we have pre-increment, first you increment it and do the remaining. Whenever you have post-increment, first you do everything and then you increment it. So now here plus plus P, which means P has to be incremented. Now P is actually a pointer to the structure. So whenever you increment P, it will actually point to the next structure, isn't it? So when I increment P, it will not get incremented by 1, it will get incremented by the size of the structure. What is the size of the structure? 4. Therefore it will get incremented to 104, and so it will point here, not here. Got it? Okay. And now it is pointing to this, right? Now after this you have to evaluate this. So what is it? Whatever P is now pointing to, you go into that structure and get the value of I. So what is the value of I? 20. Therefore x value will be 20 now, right? So if there is a variable x, now it will get the value 20 from here. That is the meaning of this. Understood this? Okay, now again let's restore everything. So P is actually 100 and it was actually pointing here, and this is the scenario. Okay, now let's see the next line. So this statement is over. Next statement, let's see what happens if I would have executed that statement. X equal to P plus plus and then I. So what is the meaning of it? P has to be incremented and then I has to be accessed, but then here it is a post increment. Post increment says that you perform everything else, then at the end you perform the increment. So which means even though P has to be incremented, don't increment it now. So first you perform P of I. P of I means you go into that whatever is being pointed by P, get that value, and then you see, which means x will get P of I first. So which means x will get 10 and then I increment P plus plus. When I increment P plus plus, this will be the scenario. It will be 104. So after that line is executed, x will get 10 and P will point to this one. What is the difference between earlier line and this one? In earlier line, x was directly getting the value, P was initially incremented and then we are fetching the value of I. But here we are fetching the value of I and then we are incrementing P. That is the difference. So earlier x value was 20, but now x value is 10. Got it? Okay. Again, let's undo it. 100 and let's see the next line. So this one, and let's see what happens with that because of that. Okay, x equal to star P, I'll write it here, x equal to star P and then C. Okay, now how many operators are there? Actually there are three operators. One is assignment, other is star, and other is this member, structure member operator, right? Then which one is going to be higher precedence? This one has to be higher precedence, which means first this one has to get executed and next this is in the second row. Next this one has to be executed and finally assignment. Assignment is at the end. If you remember it, I think I told you, you ask blah, BLA, right? So BLAC, black, you ask black, and A is at the end. So assignment will happen at the end. Okay, now first thing is what will happen? P of C will happen, right? So which means whatever P is pointing to, you get into that and you get into C. So whenever you see P of C, this is nothing but you get into that pointer and you get into that variable. So you are standing here. Standing here is as good as standing here, isn't it? So now you are just standing outside B of 0. Then you are putting a star. So when you put a star, you will be jumping inside it, right? Therefore this entire sequence, that expression represents 30, the value 30. Therefore x has to be, in x we get the value 30. That is the meaning of it. Got it? No incrementation is done, therefore nothing will alter, only xing is done. So how is it done? See, P of C means this, P is pointing to this, therefore you get into C, which means you will be here. Get into P and get into C. That is the meaning of it. P of C means get into whatever is pointed by P and then get into C. Now standing here is as good as standing here. Now when I put a star, I'll be jumping inside. Therefore the entire expression value is 30. So what do I get? X equal to 30. Got it? Okay. Now let's see this one, the next line. So it is x equal to star P C plus plus. Okay. So what is the meaning of it? How many operators are there? You can see that there are 4 operators, 1, 2, 3, 4, right? And out of this, what is the highest priority? Which one is having highest priority? The highest priority is given to this, isn't it? and next which one is having higher priority? These two are having same priority, but then they are right to left. And if you look at it, these two are unary operators, and both the operators are actually from right to left associated, right? Therefore the parenthesis, implied parenthesis, is this. You have to perform this and then this. Got it? So what does it mean? P of C, which means you have to get into this, which means you will be standing here, and now this has to be incremented, but it is a post increment, which means this one. So what will be incremented? This particular C has to be incremented, but not now. See, this parenthesis will show you what should be incremented, right? And then pre or post will tell you either it should be incremented now or later. So P of C means you are here, and now you are standing here. This is the meaning of this, right? And now these two, this plus is showing that you have to increment this particular value, not anything else. You have to increment this particular C, right? But then it is not now, so leave it. So remember that this particular C has to be incremented, mark it, but don't do it now. And if you forget it, then what is next one? Star P of C, which means whatever is pointed by C, which see standing inside here is nothing but you are standing here, right? Which means you are taking this. So star P of C means again 30. So X will get again the value 30. That's fine. But then what will be incremented? C will be incremented. That is why this parenthesis is important. You don't know whether you should increment the value pointed by C or C. But once you parenthesize, it is clear that this C has to be incremented, because this entire expression is representing that you are standing inside C. Therefore, what should be incremented? Whatever is inside the C, that has to be incremented. Now we know that C is pointing to an array of integers. So when we increment it, it will point to the next integer, right? This is what happens. So what happened? So X has got the value 30, and C has changed its pointing. Now C is pointing to the next element. That is the meaning of it. Got it? Again undo everything, and let's take the next statement. Okay, so now let's do this next statement. X equal to star P C plus plus. Okay, so again, how many operators are there? So 1, 2, 3, 4 operators are there. Then which one should be evaluated first? If you look at this, parenthesis, inside the parenthesis it should be evaluated first. Now inside this there are 2 operators. Which one should be evaluated first? This arrow is having the first highest precedence. Therefore this one has to be evaluated first, and then this one has to be evaluated, and then this one has to be evaluated. Now you'll understand the difference. See, you please keep on rewinding the video and just keep on seeing what is the difference between all this. All these are actually looks like same, but then the interior, internally they will be somewhat different. See this. Now we have to evaluate this one. So P of C means go into the structure pointed by P, which means you'll be inside this, and then go into C, which means I'll be standing here. So I'm actually standing here. When I'm standing here, it is as good as I'm standing here, right? Why? Because it is pointing to this. Then what should be the next operation? When you are standing here, you are supposed to apply the star. So when I apply the star, I'll be jumping inside. So this entire sequence, right, is representing this value, this particular cell, which means I am finally here. I am finally inside, and then plus plus is done. So now when I apply plus plus, which is increment, what has to be incremented? This particular cell has to be incremented. Earlier this was incremented, but now this particular cell is incremented. Okay, but then this is a post increment. Therefore whenever you mark what has to be incremented, so which means we know that this particular cell has to be incremented, but then not now, after everything else is over. What is everything else? Even assignment is there. So first you assign it. So what will be assigned? Now X will get the value of 30. After that, this value will be incremented to 31. Got it? That is the difference between the earlier one and this one. Understood this? See, I am going in the order of precedence, right? And then after evaluating the precedence, then I'm seeing which one has to be incremented? See, whenever you have plus plus minus minus, this pre-increment, post-increment, the main thing is in the expression you should find out what has to be incremented, then you mark it. If it is pre-increment, then you increment it then itself. If it is post-increment, you finish everything else and again come back and then you increment it. So here, even though the fetched value is 30, the actual value here will be changed to 31. So x will get the old value itself. Got it? Okay. Let's restore it back. It is 30. And let's see the next one, the next line, this one, the last one. X equal to star p plus plus c. Okay. Now what is the meaning of it? How many operators are there? 1, 2, 3, 4. So which one is highest precedence? You know that highest precedence is this arrow, right? So this one is the highest precedence. And after this, what is the next highest precedence? Both of these are highest precedence only, but then you are going to come from right to left. Therefore, you know, this one will get highest precedence next. Got it? And then this one, right? So p has to be incremented. So what has to be incremented? P has to be incremented. This is the meaning of it. Plus plus applies to p. Now p has to be incremented, therefore mark that p has to be incremented, and it is a post increment. So whenever it is post increment, act as if it is not there, but then you mark that it has to be incremented later, but act as if it is not there. Okay, I'm acting as if it is not there. Then what is it? P of c. So that is the next one, right? P of c. So when I go for p of c, then what happens? P of c means I'll be here, right? And it is as good as standing here, and then you apply a star, which means I'll be inside this. So what should I get? So x will be 30. So x value will be here 30. Inside x we get the 30, and later you have to increment p. When I increment p, it will be pointing to this. This is the meaning of it. See, whenever you are talking about this pre-increment or post-increment, if you are not able to know how to do it, then you could remove it from there. First find out what has to be incremented, and once you find it out, you mark it, and you know, below it you can write that p equal to p plus 1. Generally what programmers will do is, if you have an expression and then below the line is p equal to p plus plus or some increment line is there, then see, let us say it is not there. No, it is some expression and below it is p equal to p plus 1 is there. Then while writing the program, you know, they can cut this line and they can put a plus plus here. That will be simple and easy to write. Okay, so understood this? If you have understood all this, okay, first of all, if you didn't understand all this, my suggestion is you please you know, watch it once again from the beginning. You'll definitely understand it. And if you didn't understand also, you know, it is not a problem, because they will not ask you so complex things. I cannot say that they might ask you this. So, but it is very rare event. If you didn't understand it, you can skip it if you like. But I really suggest that if you watch it 3-4 times, you'll definitely understand it. If you can understand this question, you can answer any question involving pointers, structures, incrementation, arrays, everything will be easy. Okay, fine. Now in general, in any programming language, why do you write a program is to process something, right? So generally a program needs two things. One is it needs the input, and then it will process the input, and then it will give you the output, right? So every programming language should have a means by which it could read the input, and then it could process it, and then it could write the output. So processing all that we shall see later. First let's try to understand how to read a input into the program, and then how to write the output out of the program. Okay, let's see these things first. Now, as I told you that any program does three things. One is taking the input, processing the data, and giving the output. Now the input operation involves moving of data from an input device. So generally, if your program is interactive, then we assume that we have to read certain values from the user, where user will be inputting some values at this keyboard, and then we are going to read it from the keyboard, right? And we read it from the keyboard and then we pass it to the memory, and from that memory our program is going to read the values. Okay, this is one way. And the other way is, if you have already stored the data in the files, then our program could read the data from the files. So for now we shall see how to read the input from the keyboard. Later we shall see, at the end we shall see how to open a file and read the input from a file. Okay, similarly, while in the input or output operation, the data moves from computer memory to the output device. Okay, fine. So how to do this, now we shall see. So C language does not provide any facility for input output. The basic C language, it does not provide anything, but if you want to use it, you will have to import the libraries. Okay, which means along with the compilers you can download the libraries, and the library is going to have the code using which you can read the data as well as write the data out of a program for input output. Now the set of library functions that generally perform input up to output operations are known as are present in standard IO library. Okay, so if you have to use any input output functionality in your program, you are going to use #include stdio.h, right? So that is a header file. Now what is a header file and why do we need to use this directive, we shall see later, but for now remember that if you don't have this, you are going to get some error. Okay, I'll just try to explain you in simple words. If you can understand it, okay. So generally in C there is a rule that before you make use of any function, you are supposed to declare it. Okay, first you declare it and then use it. Now if you use suddenly a function without declaring it, you will get an error. Now header files are the files which contain all these declarations. Okay, and when you say #include stdio.h, then it means that you want to include all the declarations which are present in this header file in your program before you start compiling, so that you don't get any compiler error. Okay, so later we shall get into details of what is this #include directive. For now you can understand that if you have to use scanf and printf, you need to write #include stdio.h. Okay, gradually as we get into details, you'll understand why to use it and where to use it, what happens if you use it. Okay, for now let's not complicate it. And #include studio.h means you want to include all the declarations from the standard IO into your C program. Okay, now similarly there are other header files like math.h, string.h and stdlib.h, right? So these are used. If you use math.h, then it contains all the declarations necessary in order to make use of any functions related to mathematics. Like for example, if you want to find out 2 power 10, then there is a function there. Okay, so like that there are certain mathematics functions like sine, cos, all those. If you want all those functions, you can include this math.h and you can use those functions. Later we shall see all the other libraries whenever we need them. Okay, so now there are various other libraries which you could include, and now the main input functions are scanf and getchar. So there are various functions using which you can read the input into your program, but mainly the most frequently used functions are, one is scanf and the other one is getchar. And similarly the main functions which we use for output are, one is printf and the other one is putchar. A simple method of providing value to variables is by assigning assignment statement, which means in a program, if you don't want to provide any input from the outside, you can directly provide the input inside the program itself while writing it, but it is a static way. Static way means if you write like this, int b equal to 2000, char c equal to s, then once you write it like this, and if you are not going to read anything from the user using either scanf or getchar, then your program is always going to be static, which means it can never read from outside. Now the other way of giving the input to your program is, this is one way, the other way of giving the input to your program is by using the scan method. Now by using the scan method, if you if you use scan method in your program, then it can dynamically read the input from the user. It can ask the user to enter some input and he can input it from the keyboard and it will read it. Okay, that is the second method. And for output we generally use printf, right? So printf and also putchar is also popular, and also there are other methods, but first let's start off with scanf and printf. Later gradually we shall see what are all the other methods available. Okay, fine. Now let's see how to read using the formatted input. So what is a formatted input is, let us say user is entering some input and you want to read many values into many variables. For example, let us assume that you want to read in a single statement, you are trying to write in a single scanf, you are trying to read, one is employee name and the other is, let us say, employee age and employee salary and maybe employee address. All this you want to read in just one scanf, and so you are using, let us say, 10 variable addresses in order to read. Now how do you specify that which part of the input that is entered by the user will go into which variable, right? So for that reason we can use format specifiers. Okay, so this formatted input. Now format for integer input. So if you are trying to read the integer numbers, then you can use %d. So this conversion specifier, you already know it, right? And now if you write W, it means that is going to tell you the width, which means out of all the things that are entered by the user, for that particular width we want to read into this variable. So I'll just tell you with an example. Here D is the conversion specification. This one you already know. It means that whatever user has entered, you want to read it as a decimal number. That is the meaning of it, right? So here D is the conversion specification character for integer value, and W is an integer number specifying the maximum field width of the input data, which means how long the user can enter. For example, if you write here as %3d, it means that the user can enter the input for this particular variable using a maximum of 3 digits. And if he enters anything more than that, if you write 3 here, it means that 3 digits. If he enters anything more than that, that will be truncated, right? Now if the length of the input, which means whatever the user has entered, if it is more than this maximum field width, maximum field means whatever is specified here, then the values are not stored correctly, right? So it is just an optional, so you need not specify it all the time, so it is just used to restrict. Okay, it is an optional, W is optional, you need not specify all the time. Now for example, if you write, let's see this, scanf %2d, %3d, %a and %b, it means that whatever user has entered, treat it as a decimal number and read it into first one, read it into A, and the second one read it into B. But then in the first one you read just the 2 digits, and after that the next 3 digits should go into B. So if a user has entered consequently 5 digits, then 2 digits are going to get into A and the remaining 3 digits are going to get into B, right? Now when the input data length is less than or equal to the given field width, which means if the user has entered less than this W, then there will be no problem. The input values are unaltered and stored in the given variables, then that is not an issue. For example, if for this statement, let us say user has typed 7 space 495. Now what happens is, so this 7 is going to get into A, right, and then 495 is going to get into B without any problem. The reason is, you have said that A can take a maximum of 2 digits and there is only 1 digit here, therefore that is not a problem. And the remaining after space there is 495, so whatever is present that is supposed to get into B, and here we are giving 3 digits and here also we are specifying a maximum of 3 digits, that is why there is no problem. So A is taking 7 and B is taking 495, and that is how A has taken 7 and B has taken 495. When the input data length is more than the given field width, which means, let us take this example, the input values are altered and stored as so they are not stored properly. For example, if for the same statement, if we give the input as 369 and 495, now A is going to get into it, or it is going to read into A just the 2 digits, a maximum of 2 digits. Why? You have 2 here, right? Therefore 36 is going to get into A, right, and then into B it is going to take the remaining thing. Now what is remaining? Just 9 is remaining in this, and so even though it can take 3, since you have a space here, it will think that okay, input has ended here, and so it will just take 9. So 36 will go into A and 9 will go into B. In case if you would have not given this space here, then 36 would have been gone into A, would have been taken by A, and 949 would have been taken by B, right? So again, with examples you will be able to understand it. Okay, for now this is all about theory. When we look into examples, you will understand how all this works. Or you can also try out all the possibilities, just play with it, you will learn more. Okay, fine. Now you can format the output using again percentile WD, where D is used to represent the integer numbers. Okay, so later we shall see about other formats. What about floating point number and what about strings, but for now we shall focus on only the integers. So here it means that we want to write integer, so if you are going to use it with printf, that is what I am saying, and W means the width. So here W is an integer number specifying the field width of the output data. So if I write percentile WD, it means that the output data should have at least minimum width of W, right? That is the meaning of it. So even if the size of the variable or the size or the number of digits in that particular variable is less than W, still the width as assigned or allocated to that particular variable should be at least W. That is the meaning of it. Okay, if the length of the variable is less than the specified field width, which means let us say the variable is 12, which means 1 2, and you have written 3 here, which means you want to allocate 3 digits to 12, the number 12, which requires only 2 digits. Then the most significant digit will be left blank and everything will be moved to the right. So that is why the variable is right justified with leading blank spaces. Now we shall just see this example. Let us say you have written a statement like this: printf A equal to percentile 3D and B equal to percentile 4D, A comma B. This statement means that whatever is present in A, you want to print it. Now how many width, what width you want to have for A? Minimum is 3. That is the meaning of it. Okay, now in case if A is containing less than 3 digits, then they will be right justified and they will be stored in a field containing 3 spaces. And in case if the number of characters present or the number of digits present in A is greater than 3, then all those letters will be displayed there, or all those digits will be displayed. With example, I will show you this. Let us say this is the statement we have used: A equal to percentile 3D, B equal to percentile 4D, A comma B. Right, now what will be printed in the output is A equal to symbol is there, percentile 3D is there, which means 1 2 3. So that is why, since you have written 3 spaces are used, and in these 3 spaces it will try to place the value of A if it is going to fit, right? So since A is containing a value 98, since it is going to fit there, so 98 is kept there right justified in these 3 spaces. So since it is percentile 3 spaces are there, and now the number of digits in A is just 2, that is why it is just right justified and then a space is left in the beginning. Similarly, if you see B equal to percentile 4D, which means it has to be placed in 4 digits, and now it is going, since B is containing only 1 digit, it is going to be right justified, so it is kept here, and all the other spaces are left as blank. Got it? Now the width specifier of the first data is 3. So here the width specifier of the first data is 3, while there are only 2 digits in it. So there are only 2 digits, that is why it is right justified, right? And here it is 4, that is why it is again right justified. Let's see one more example, you will understand it. Now let us say A equal to 3D is given, B equal to 4D is given. Here A is equal to 374, which means exactly equal to 3 digits, but then B is equal to 2842, exactly equal to 4 digits. In this case we got 374 and 2842 without any problem. Let us assume that A is 2641 and B is 28426. In this case, both the A is containing more digits than specified here, as well as B is containing more digits than specified here, but still they are not truncated and they are completely printed. So that is the difference between scan and print. In scanf, if user tries to enter more than the width that is specified by the program, then it is going to truncate the extra digits. But coming to this printf, even if user specifies some width, program specifies some width, and if the number of digits present in that particular variable are greater than that, still it is going to print everything without losing any data. Okay, fine. Now let's see how to write output from a program, which means our program has read the input and then done some computations on it and finally produce the output. Now where do you want to see this output from? Now there are various ways. So one way is you can ask the program to write it onto a file and later you can open the file and see it, or you can directly ask the program to write it on the screen, right? So now if you use printf, it will directly write it onto the screen. So in Linux, the screen is also the monitor, that is what I am talking. This monitor or screen is also a file, and printf is configured in such a way that it writes into a file which is actually a keyboard here in this case. Okay, so output data can be written from a computer memory to the standard output device, which means the monitor, using printf library function. With this function, all the types of the values, which means either numeric or character or string, can be written as output. The printf function can be written as, now if you want to see how the printf function is written, so this is the syntax. So printf followed by the parameters, so control string, variable 1, variable 2, right? So I told you that in scanf there has to be at least 2 parameters, but in printf 1 is enough, right? And if you need, you can add more parameters, right? And also this control string is going to contain the conversion specification characters like percentile %d, percentile u, all those, as well as text. For example, you can write here the value of x is percentile d, and that percentile d will be filled up by the value of the variable that you are going to place as the immediate following parameter of the control string, right? Now it should be enclosed within a double quotes, so this one should be enclosed in double quotes. The name of the variables should not be preceded by ampersand. So in this case, the name of the variable should not be preceded by ampersand, but then in scanf they have to be preceded by ampersand. That is the difference. Okay, and then if the control string does not contain any conversion specifications, the variable names are not specified. If it does not contain any conversion specifications, then you need not put any variables. So when is that used is, let us say you want to ask the user to enter some input, then you can say enter an input and you need not write any variables. Later you can write scanf percentile di, something like that. So we shall see a program on that, you will understand it. So this is how you are going to write printf. So int marks equal to 100, printf percentile d marks. So it is nothing but marks is set to 100, and now you are trying to print the value present in this marks as a decimal value on the screen. So you know what this is, we have already discussed, right? So now if you see the difference between scanf and printf, the same program here. So scanf percentile d ampersand marks is used, which means you are reading a value from the keyboard as a decimal value and you are trying to write it into the variable marks. But here percentile d marks is used, so here there is no ampersand, so that is the difference. Okay, fine. Now let's see the conversion specifications. So here I'll explain you the theory. Later with examples I'll explain you all the concepts. So what is conversion specification? What it means is, whenever you try to store data in a computer, it will be converted into bits and it will be stored. Now when you show it to the user, you have to show it in a form that he wants to see. Now if you look at the number, all ones, let us say 8 ones are there. Now if you interpret it as a unsigned integer, that represents 255. If you interpret it as a signed integer in 2's complement, it represents -1. Now if you interpret it as a character, that represents a different character altogether. Therefore there is a possibility that many values will have the same binary representation, and so when you use this conversion specifications, there will be a opportunity or a means provided to the user in order to specify what he actually means, right? For example, if you write, if you say 255, if you store it later, if you reads it as a signed number, it is -1. So that is why you should always take what actually the user means, right? So the user, he has a facility here to specify what actually he means. So I'll just tell you with examples what it all means, right? So the functions scanf and printf make use of conversion specifications to specify the type and size of the data. So scanf and printf are the functions which are used to read and print something onto the screen, right? Now where do you read something from? You read from the user or from a file. Scanf is generally used to read something from the user. Now how the user will enter the data? Through a keyboard. Now when he enters the data in a keyboard, whatever is the bit representation for that key, that all will be converted into registers, that all will be stored in a register. Now in that register, again it is in the bit format. Now how many bits should you read in a go? That can be determined by, that is what you want to specify by the type and the size of the data. So that is where these conversion specifications are going to be useful. Each conversion specification must begin with a percentile sign, which means before you start, in order to specify that this character represents a conversion specification, we are going to use the sign percentile. Now let's see this. So whenever you write this, so these are all the conversion specifications for printf. Let us say you want to print the information present in a variable. Now how do you want to print it? Do you want to print it as a number or do you want to print it as a character? That you can specify using this, right? So by using examples, I'll show you again this point. For now, let's go to this theory. Now percentile C means whatever value you want to print, you want to print it as a character. That is the meaning of it. Now percentile D or percentile I means whatever you want to print, that value in a variable, you want to print it as a decimal integer. Percentile U means the value present in that integer has to be interpreted or printed as a unsigned decimal number, right? So now if you observe it, the difference between this one and this one is, let us say you have a variable, and in that variable, if it is a 8 bits and you have all ones in it. Now if you use percentile U, it is going to show a value of 255. Now if you use percentile D or percentile I, it is going to show you -1, right? And if you use percentile C to print the same value, then it is going to show you a character, right? And that character will depend on what is the mapping that we have used or encoding that we have used. And then percentile U, we are done with it. So percentile O, print an unsigned octal integer. So this is used to print octal number, which means whatever is in the binary form, we will convert it into octal number, right? So what is octal integer is, I am not going to explain that in this course, but I'll just give you a brief introduction. Now if you have, let us say, few bits, you take 333 bits and you try to convert each 3 bits into some number, integer number, and you represent it. That is nothing but the octal representation, which means, let us say you have 30 bits. Now you take you join 333 bits, and therefore you are going to get 10 digits. All those 10 digits is going to be that octal integer, okay? But anyway, you can read about it in detail in the number system topic in the digital course, or some other course you can read about it. And coming to percentile X, it means that we want to print an unsigned hexadecimal integer using A, B, C, D, E, F. So what it means is, percentile X, it is small x, okay? So we want to interpret the information present in bits as a hexadecimal number, and when you use hexadecimal number, we are going to have all the numbers from 0 to 9, and also we are going to use the letters A, B, C, D, E, F, right? Now by using small x, we are clearly saying that we don't want to use capital A, capital B, capital C like this. We want to use only small letters. That is the meaning of it. And then percentile capital X, it is same as the previous one, this one, but only difference is, instead of using small letters, we want to use capital letters. And percentile F, So it means that the information stored that has to be interpreted as a floating point number, which means you take that entire data, let us say 32 bits. Now in that 32 bits there is going to be mantissa, so there is IEEE representation. Again, about IEEE representation of a floating point number we are not going to discuss in the C course, that is discussed in the number system of computer organization. Okay, so the brief essence of this one means whatever information we have in that particular variable in terms of bits, we want to interpret it in terms of mantissa and exponent, and then finally print that value as a floating point number. That is the meaning of this. Okay, and percentile small e, so it is also the same thing. So print a floating point number, but it has to be printed in exponential format. So what is exponential format is, now we know 1.5 is a floating point number and 1e5 is also a floating point number, which means in order to represent floating point number you can use a decimal point or you can also use small e. So that is the meaning of this one. And percentile capital E, it is same as percentile small e, but instead of using small e it is going to use capital E. That's it. Okay, and then percentile G. So the percentile G is, it is going to print the floating point number in either percentile F or percentile E form, whichever is shorter. So sometimes some numbers can be written in a short manner, which means using few characters in percentile F format, and sometimes in percentile E format. Therefore whichever is shorter it is going to use it, so that we can save some space in documents. And then percentile capital G, so it is also same as percentile small g, only difference is instead of using this small e representation it is going to use capital E representation. Okay, and then percentile S, it is used for printing a string. Now what is a string? In C we don't have the concept of a string directly, but a character array can be considered as a string. But if you look at other programming languages like Java, there is string available directly, but here we don't have string available in C. So we have only arrays available, and when you have an array of characters we call it as a string. And then percentile P, so it is used to print a pointer in hexadecimal format. So what is a pointer? Pointer is nothing but a variable which contains some address. So as of now you don't know anything about it, later we shall see about it, but for now if you have a variable which is called as a pointer, which generally contains address of some memory location, now percentile capital P says that you want to print the value of that particular address in hexadecimal format. Generally when we come to the addresses, we generally use hexadecimal representation. In computers, when you talk about the addresses, we generally use hexadecimal format to represent them or talk about them. And then now let's see about the scanf, the specific conversion specifications for scanf. So till now we have seen the printf. So printf is used for printing onto the screen. So what it means is, now if you have some data available in the memory as a variable, if you want to print it, you are going to use printf. Now you are going to say, or you have specified how you want to print it on the screen. Similarly, scanf is somewhat different. Scanf says that when you are trying to read the bits from the user, how many bits you need to read and how to interpret that. Got it? For example, if it is a character, you might have to read only 8 bits. Now if someone types on the, let us say, keyboard, all the data is going to be converted into bits and it is going to be stored in registers. Now from those registers or buffers, how does our program have to interpret it, right? So which means, should it interpret it like a only 8-bit chunks, or should it interpret like a 16-bit chunk? So that is all depending on the that is all about scanf. Now if you say percentile C, it means that you read from the user, let him input any number of characters, but then you read from him only 8 bits and you interpret it as a character. Okay, so which means it is just going to say how many characters you have to read, how many bits you have to read. Okay, and percentile D means you are going to read a decimal integer. Now depending on the size of the decimal integer in this particular machine, it is going to read either 2 bytes or 4 bytes. Okay, so what is the size of an integer, that we shall discuss later. And then percentile I. Percentile I means it reads a signed integer and base is decided by the prefix of the input number, which means here percentile I we are going to read the signed integer. So what is signed integer? -1, -2, +1, +2, like that, okay? But then you can also have any base in this. It could be either a decimal number, or it could be a hexadecimal, or it could be octal, right? Now if you are going to use 0x, it means that he has given the input as a hexadecimal number, right? And if it is having 0, so 0 means he has given the input as a octal number, right? And otherwise it is simply a decimal number. Are you getting this? For example, let us say you want to input maybe 16 plus 10 is 26. So 26 is 1a, right? So in hexadecimal you want to input it, then you can say 0x1a. Now if you write like this, then the machine will understand that he is trying to input a hexadecimal number, and so it will read whatever is entered after it as a sequence of bits, and it is going to store it in the computer. But then when we again get it back, it is going to be interpreted by the same way that you want. Okay, so with examples this point will be clear, don't worry about it as of now. And coming to, let us say this one, octal. So octal, if you look at this in 26 in octal, it is going to be 32, right? So 032, it actually means in octal you want to represent the decimal number 26, right? So if you write 032, then this scanf method is going to read that and convert it into the decimal number, and it is going to store it in that particular variable. Later again, if you want to convert it into the let us say octal, then you might have to use the percentile conversions in printf, right? So while reading we are converting, and while printing we are converting. Finally we are going to store everything in bits, right? And then, so if you don't specify any prefix, it is going to be a decimal number, okay? And coming to this percentile u, it reads an unsigned decimal integer, which means, as it is saying that we don't want to worry about signs, we are talking about only unsigned numbers here. And percentile o, it is used for reading unsigned octal integers. Percentile small x or capital X, it is for unsigned hexadecimal integers. Percentile f, it is used for reading floating point number. Percentile small e or capital E, again for floating point number. And small e or capital G, it is also for floating point number. So small e or capital G says that he might enter the input either in form of 1.5 or 1e5, right? So this says that he might enter a input in form of 1e5 or 2e5, something like this. And percentile s means we want to input a string, okay? So about strings, don't worry about it as of now. Later we shall see about strings in detail. Pointers and strings, don't worry about it. And along with this percentile u or this, we can also have a prefix here, lu, like that, okay? Now see this, that is called as modifier. See, we have percentile I like this, percentile I, right, percentile d, all this. Along with this, we can also have before d or before I even more prefixes, right? They are called as modifiers. Now the modifier capital small h can be used before the conversion specifications d, I, o, u, small x, capital X to specify short integer, and the modifier l can be used before them to specify a long integer, right? Which means here, if you want to specify let us say a small integer. So what is the difference? Okay, before that you should understand what is the difference between a short integer and a long integer. Generally, depending on the architecture, short integer might be 2 bytes and long integer might be 4 bytes. Let us say a user has entered something through the keyboard, and now that has been converted into bits, and now that is stored in the buffer. Now from the buffer, how many bytes should be read and stored into this particular variable? So that you can specify by saying h or l. In case if you specify h, it means that you are specifying the program that you need to read may be 2 bytes in case if in that machine short integer is represented by 2 bytes. Right, let us take a machine where short integer is represented by 2 bytes and long integer is represented by 4 bytes, and these sizes are variable. I mean, they can change from machine to machine, implementation to implementation. Right, now we are working on a machine where short integer is 2 bytes and long integer is 4 bytes. In that case, if you give percentile HD, it means that you want to read only 2 bytes into that particular variable. If you give percentile LD, it means that you want to read 4 bytes into that particular variable, and also that particular variable should have been already declared as a long or short. Okay, otherwise there will be type errors. So later we shall see that conversions and all this. So here let's see only the basics which are required to print and read. Okay, the rules we shall see later. Now the modifier small l can be used before the conversion specification f, small e, small g, capital G to specify double, while capital L is used to specify the long double. Now just like short int and long int in case of integers, in case of floating point numbers we have double and long double, right? So double is generally 32 bits and long double is generally 64 bits. It is also called as floating point representation, IEEE, single precision and double precision, right? So about the representation exactly we need not get into those details in C programming language. If you are interested, you can look at the computer organization topic. There we have this floating point representations, right? But what you can understand is, if you give small l, you mean to say that I want to read 32 bits. If you give capital L, you are saying that I want to read 64 bits, provided that the space in that variable should be that long, right? And also if you use small l or capital L, it means that you want to print 32 bits as a floating point number and you want to print 64 bits as a floating point number, depending on the context you have used it. If you are using it in scanf, you are talking about reading. If you are using it in printf, you are talking about writing. Okay, and for example, if you see this percentile LD, percentile HD, percentile LF, percentile HF, so which means you can prefix D with L and D with H like this, right? So that is why they are called as modifiers, right? So these are the conversion specifiers. D is the conversion specifier and L is the modifier. But anyway, you need not by heart this terminology. Okay, no one is going to ask you anywhere. Don't by heart the terminology, and also don't by heart all these things. Anyway, you can Google them out whenever they are required. And in practice, we generally don't use all these things. We generally use either percentile F or percentile I or percentile D or U. And as we practice, you will get used to it. No need of by hearting all this. Okay, fine. Hi, till now we have seen the fun programs which are actually reading from the keyboard from the user and they are writing something onto the screen. But in real world, I mean, when you work in software industry and if you are trying to develop a product, generally they don't print onto the screen and they don't read from the users, right? So there the input will be taken from a file and the output will be written to a file, right? For example, if you see a log file, right, whatever happens while during the execution of a program, everything will be noted in a log file, right? It will not be printed onto the screen all the time, right? And whenever a user wants to see what has happened, he is going to open the log file and he is going to read it, right? Or some other program might open that log file and read it. Therefore, input and output to a program in real world should come from the file and should go into a file, right? It is not that we are always going to involve user to print to type the input and and then a screen to read it from. Therefore, it is very important that you understand how to open a file, read from it, write into it, or create a file, or append something to the end of a file. Now let's see what C has provided us in the standard libraries in order to handle files. So first thing is, C has provided a structure by name file in the standard library. Now the declaration of this structure is present in stdio.h. So before you start the program, you include stdio.h so that all the functionalities of the structure are already declared, right? And then before you open any file, you just define this structure and you define a pointer to that structure. Let us here call it as FP, right? So what does it mean? FP is a pointer to the file structure which is already predefined. You are not actually going to declare it, okay? So no declaration of file is required. It is already done in stdio.h. Just include it. Now after it is done, once you have defined this FP, you are supposed to open the file for using it. Now what are the various ways you can use a file? Either you might open it to read some information from the file, or you want to write some information into file, or you want to append some information to already existing file, right? Therefore you can open a file by using this function call, right? fopen. Now you just give what is the name of the file that you want to open in the string, okay, and then what is the mode in which you want to use the file. So what is mode here means that how are you going to use the file, that is it. So either are you going to open the file for reading, or are you opening the file for writing, or are you opening the file for appending. Generally 3 modes are there. For example, you might want to open a file /home/ravi, something like this, okay. Now you give this entire name here, you put it in a string, and then you pass it here, or you can directly give it as this, as a string, okay. And then let us say you want to open it for reading. Now you give that in the reading mode, and then you can just pass these 2 parameters to fopen. Now fopen is going to return a pointer to the file structure, and you can catch it in the file pointer which is already defined, right? So you can simply write fp equal to this. Then what will happen is this file will be opened, and that pointer will be caught there. And then after opening the file, you can do various operations on the file depending on this one. So one thing you should be careful about is you cannot read from a file which does not exist. So if you are trying to open a file in a reading mode which does not exist, it is going to give an error. Therefore this function might return null in case if it is unsuccessful. And second thing is, when you are going to open a file which is already existing for writing, then what happens is all the information in the file will be deleted, and you are again going to start writing from the beginning. In case if you want to have the data inside the file as it is, and if you just want to append it, you have to open it in the append mode, right? Now in case if you are going to open a file for writing which is not existing, then a new file will be created, and you are going to get the pointer for accessing. Okay, now let's see what are the operations or what are the functions that are provided in the library to perform various actions on the file. These are the various functions which are provided in the library. Now let's see them one by one. fopen, as you have seen, it is going to open the file. We shall see fclose later. Next one is getC. It reads a character from the file. By giving this, okay, what is the exact syntax? We shall see it with an example. Here just understand that there is a function with this name. Now how to use it? We shall see for every function some example. Later we shall see that. Now it reads a character from the file. Now putC, it writes a character to a file. Now fscanf, it reads a set of data from a file. It is similar to scanf, but then it is going to read it from the file, okay. And fprintf, it is exactly similar to printf, but it is going to print the data onto the file instead of printing it onto the screen. Getw reads an integer from a file, and putw, it writes an integer to a file. fseek, so what happens is every time when you have opened a file and when you are, let us say, reading the file using getC, or when you are trying to write something onto the file using putC, we'll just remember till what part in the file we have read so far or written so far, which means we'll always remember using a pointer till what part we are done in the file. Let us say this is the file, and till this part you have read, and the next character to be read is, let us say, here, okay. Then you are going to have a pointer which is going to say that till this part your reading or writing action is done. Now if you want to move this either back or front, you can use fseek, right? So now fseek sets the position to the desired point, which means this pointer you can set it to either beginning or ending or anywhere, right? That is called as fseek. It is, you can compare it as if you are moving the read write head on a file. And then ftell gives the current position in the file, which means it will just tell you which position you are standing in. Rewind, set the position to the beginning point. Okay, rewind means you are again going, you will be setting from the, you will be going back to the starting point and you will be starting all over again. Got it? Now if you see this, after this is done, after everything is done, let us say you have opened the file and you have read from it or you have written to it. Now it is always advisable that you close it. So why closing a file is important is, there will be some resources which will be allocated for this structure while processing the file. Now it is better you close it so that all those resources will be freed. Generally, what are the resources is, some buffers will be allocated for that particular file in the heap, right, in the heap section of the process. Now when you do this close, all the buffers allocated will be freed so that you will have the memory back, right? So fclose is simply going to give you what is the resources, and they are all going to be closed. So once it is successfully closed, then you are going to get a status of this function. A negative -1 means it is the status is failure, some error has occurred while closing a file, you are not able to close it properly. Otherwise, if you get a non-negative number, it means that it is success. Okay. Now let's see some more reasons why you should close a file using fclose once your work is done. So one thing is, whenever you open a file using fopen, whenever you cache that pointer, the pointer returned in fp, it means that there's some kind of relationship is established between the file you have opened and this file pointer. Later, if you want to use the same pointer to point to the other file, then it is better you close that, you terminate that relationship, right? So when I close it, then there is no longer a relationship between the file opened and this pointer, and so you can use the same pointer to open some other file, right? That is one reason. And second reason is, there are there is something called as system calls. We are not actually going to get into it. See, we are trying to make as simple as it is possible without going into the system calls. Now what happens is, every library function here, we have seen let us say put C, right, or get C. Now every library function, it is supposed to call a system call in order to execute its work, right? Now in order to optimize the code, or in order to optimize the time, so okay, I'll just go into some details here. If you are not able to understand it, leave it completely, right? So what I mean to say is, for every function call here related to the files, there will be a system call, right? And every time when I call this function, if the system call has to be called, then we have to go from user mode to kernel mode, and then again kernel mode to user mode, and it is going to take a lot of time. Therefore, what our C library has done is, instead of calling this system calls all the time, it is going to locally maintain a buffer, and it will just keep on accumulating the data, right? And once this buffer is full, then for all the characters at once it might call the system call, right? Now what happens, because of that, you need not waste a lot of time by calling the system call for every character. You will be calling the system call once and you will be getting the work done very fast, right? Now when you are using such a mechanism, what happens is, sometimes the buffer might still contain the valid data, and you might have to you might have only filled some part of the buffer, and so the system call is not yet called, and this data is not yet stored in the file. Now whenever you call this fclose, then this entire data which is collected so far, even though the buffer is not full, will be flushed. Got it? So there are certain things which are done for optimization. We are not going to get into the details, you might get confused. So just understand that by doing fclose, you are actually not losing any data. Okay, so always try to use fclose. And in case if you don't use fclose, what happens is when the program completely terminates, when the program is over, automatically fclose will be called on all the functions which are on all the files which are open, right? Anyway, this will be flushed at the end of the program, not in the middle. Okay, fine. Now let's see this program. In this program we shall see what is the purpose of fseek and ftell. So these two we shall concentrate on these two functions. So let's see the program, how it is working here. Void main. So first thing is we are defining a pointer to the structure file, and then one variable is defined here, int length, fp equal to fopen file.txt comma r. So what it means is we want to open this file.txt in the reading mode using this fopen function. Now as usual, fopen is going to return a pointer to the file structure which is going to be held by this, which is going to be taken into this variable, right? This is a pointer. Now every time, even though we didn't show you in some examples, you should always do this. Whenever you open the file, you should always check if fp equal to null or not, right? And this is the best practice. So why we should do this is, sometimes whenever you are going to do this one, sometimes what happens is, because of some error, either if this file doesn't exist or because of the lack of permissions for you to open a file, this is going to return null. Now if you don't test that condition, and if you go ahead with using this pointer, then you might see segmentation fault if you are going to use a pointer which is pointing to a garbage value. Some errors will be there while you run the program. That is why always test it. In some of the examples we missed it out, but then you should do it. So what is it? If fp equal to null, then printf error opening file. And the next one is fseek. Now we shall see why fseek is used. As I told you, whenever any file is opened, let us say for reading, let us assume that in this file we have a, b, c, d, some data, and then end of the file character. So character 1, character 2, character 3, character 4 and character 5. We have 5 characters, out of which 4 characters are a, b, c, d, right? Now whenever you open the file for reading, initially the read write head or the read write pointer is going to point here, which means inside this structure there is going to be various pointers. One of the pointer will be holding the current position that you are at. Initially when you open it for reading, it will be at the beginning. Okay, now by saying this fseek, by passing this pointer to this function and by sending these parameters, so 2 parameters are being sent. So one parameter is 0 and the other parameter is seek end. So what it means is we have 3 constants actually which are defined in that file, the header file, using hash define. So secant is actually an integer constant which will be defined by hash define secant, I think number 3. Now let's see what are other constants we have and what their purpose is. So we have all these 3 constants, okay, all these 3 constants. So seek underscore set, it means that we want to start from beginning of the file. Seek underscore current, it means that we want to start from the current position in the file. And seek underscore end, it means that we want to start from the end of the file, right? So these 3 are the integer constants which are being passed, and they will be defined as if it is 0, it is 1, it is 2, right? So just to increase the readability of the program, we generally use these integer constants. Now whenever we send 0 here to fseek, it means that you start from the beginning of the file and you move the cursor or you move that read write head these many bytes and you position the read write pointer there, right? For example, I'll just show you what it means. Let us say our file is a, b, c, d, and then end of the file is there, right? Now if I call the function like this, fseek fp, let us say fp is the file pointer which is linked to this file, fseek fp comma, let us say 2, okay, and now let us say it is 0. right? If I call the function like this, here 0 actually means indicates that you have to start from the beginning. Okay, so from the beginning you move the read write head 2 characters to the right, which means initially if it is at 0, location 0, it will move to 2. That is the meaning of it. Okay, now if you say, let's say 1, which means assume that the current position of the read write head is at 2, which means you are starting from the current position, that is why this number is 1. And if I write, let us say 1, it means that you have to move 1 position to the right. Therefore it is going to move 1 position to the right, and we are going to place it. So why is it useful is, we want to skip some characters either while reading or either while writing. So how many characters we want to skip and how to move the cursor, that is all decided by this function, right? I mean, cursor means that read write head. Okay, and the next one is, let us say at the end. So if you give it 2 means we are starting from the end, so it will be pointing here. And if you want to move 2 characters to the left, here you give -2. When I do -2, it will move 2 characters to the left and it will point to here, right? Therefore you can tell this function where to start the initial position from, and from there how many characters to move. You can also say you want to move to the left or you want to move to the right, depending on positive value or negative value. Generally if you give a positive value, it means that you have to move to the right. Negative value means you have to move to the left, right? Now if you look at the syntax of fseek, now fseek is going to take, one is the pointer to the file structure. Now this one is going to say, or it is going to give all the information related to the file, and the second one is how many bytes you want to move the read write head, and the third one is whence means from where you want it to start. So either you can give 0 or 1 or 2 here. Generally, to make the program more readable, instead of directly giving these integer constants, we generally use these macros, right? So now if you see this name, seek set will be, if you give seek set, it means that we want to start from the beginning. Seek cursor means we want to start from the current position. Seek end means we want to move till the end. Now this function, after taking these parameters, it will do the appropriate moving, right? So inside it, the logic will be written in such a way that this particular pointer will be moved to the beginning, and from there how many characters you want to move, or it will move it to the end, and from there how many characters you want to move left or right. Got it? And what about the return type? Now fseek is going to return 2 values. Either it is going to return a 0 or it is going to return a non-zero, right? Now in case if it returns a 0, it means it is successful. In case if it returns a non-zero, it means something wrong has occurred there, and that that means it is a failure, right? The function has failed to perform the task that it is given. Now in case if you get a 0, it means that it is successful, right? Now let's see here. If you observe this fseek, fp comma 0 comma secant. So what is that we are trying to say is, go to the end of it and you don't move it, right? 0 means don't move either to the left or right, you just stand there. That is the meaning of it. Got it? And now if you start the character from 0, 1, 2, 3, 4, our current pointer is being positioned at 4, right? Now the integer length is equal to ftel of fp. Now what it means is, this function ftel is going to take this as input. Again, if you look at the syntax of this, the way we have to write it, see this. Now ftel is going to take as input one pointer to the function file structure, and it is going to return int, long int, right? Now what does this long int represent is the current position in the file that you are standing at, that your read write head is standing at. In case if there is some error, it is going to return -1, right? So now if you observe it, in this case, if this is the file, if my current position is here, at this point if I call ftel giving it the input as fp, then it is going to return 4, right? That is where our current position is. Now if you observe it, 4 is nothing but the number of characters which are present in the file, which means it is also giving us, we are finding out the file size indirectly by using this method, right? Now fp close, so fclose fp, so it is nothing, it is just a statement which is used to close the file. Printf, the total size of the file text equal to %d bytes length. which means we are finally printing that the length of the file is so and so, right? Here in this case it is 4. Okay. Now there are two more functions which are defined in stdio library. Apart from printf and scanf, even printf and scanf are also in the stdio library. Similar to that, we have getS and putS. These are especially to read unformatted data. So earlier we have seen how to read the formatted data using scanf, right? So if you see this, using scanf, what we did was, now if I say I want to read %d, two numbers, then generally we are going to enter in the input, let us say 10 comma 20. So our scanf will read the data till it finds a blank space, and once it finds the blank space, it will take this part as the first one, and then it will take this part as the second number, and it will convert this one into a decimal number and store it into the address given here, right? Therefore your scanf will not read the spaces given in between, right? So while you enter the data, whenever you give the spaces, it will think that that is the end. Therefore scanf will read only until it finds a space. But if you want to write something like this, let us say my space name, if you want to write something like this, and if you want scanf to read it, because of this space present here, it might not read it, right? Or if you want to give numbers, a lot of numbers, let us say you want to give 10, 20, 30, so on, and if you want to read them all, once it sees this space, it will stop reading. Okay, that is the problem with scanf. Now if you want to read the entire string as it is without stopping when it sees this space, then the best thing is you go with getS. Now getS, to the input we are going to give a pointer to the character pointer, which means a string. Let us say char *s. It means that if you give to getS an argument which is a character pointer which points to an array of characters, then it is going to read the whatever string you have printed, and it is going to read it, and it is going to store it in the character array which is pointed by s, right? See this getS function, it reads a line from stdin means standard input, which is nothing but the keyboard, into the buffer pointed by s. What is the buffer pointed by s? A character array, right? A character array which is pointed by s until either a terminating new line or end of the file. So when will it stop reading is either if it finds a end of the file or if it finds a new line. So these are the two characters which will be used to stop reading. But in case of scanf, by looking at a space also it will stop. Okay, now it is going to read, it is going to take as an argument a character pointer, and it is going to return a character pointer. Now what will be returned in case of successful reading? It is going to return the pointer to s itself, right? Which means it is simply going to return s itself. If you want to know the status of the function. Now in case if some error has occurred, it is going to return null. Okay. Now the next one is putS. This function writes the string s and a trailing new line to the standard output. So now if you see this function putS, it is going to write whatever is present in this, let us say this is a character pointer. Okay. Now let us assume that this one s is pointing to an array of characters, then this function is going to write whatever is present in the s onto the output. Okay. At the end of it, it is going to write a new line. Alright. Now this one is going to return an int. In case if it is successful, then it is going to return a positive number. In case if it is a failure, if something has occurred, some error has occurred while executing this, it is going to return -1. So that is the status of this. Now let's see this example. Void, so hash include studio.h, because since this is in library stdio, I have to include all the header files corresponding to that library, so that declarations of these two functions will be taken care. Now char str100, which means we are having an array of 100, size 100. Now printf, enter a character string. Now getS string, which means into this str we are going to read whatever the user has entered, right? and then put as str. So whatever has been read into this str, that will be printed. Okay, so that is the example of it. Let us say if you have entered a name Ravi, that will be read into this str, and later when you try to print, it is going to be printed, right? Okay, now how can you stop reading it is, see this. So let us say you have Ravi space Ravula, Ravula. Now you are going to see this display enter a string, and in the next line if you have entered Ravi space Ravula, the entire string is going to be read till this part, right? So when is it going to stop? It is whenever it sees the new line. Therefore after entering this, if you print a new line, which means if you print enter, that is nothing but a new line, then definitely this entire thing will be read, including this space. If you have done the same thing with a scanf, by looking at this space, it would have stopped reading the remaining part. Okay, now this entire part is going to be stored in this str, right? And next thing is when puts, so when you use this puts and when you try to print it, this entire part is going to be printed on the output. Okay, fine. In Linux programming environment, whenever you run a C program, operating system is automatically going to provide you with 3 file pointers. So one is stdin, and the other is stdout, and the other is stderr, right? So just to explain you in simple words, you can assume that stdin is a file which is related to the input stream, and so you can think of it as if it is related to the keyboard or associated with the keyboard, right? So what you can do is whatever you are going to type in the type on the keyboard, that will be streamed onto this file stdin, and that file will be displayed to you on the screen. And similarly stdout means this is the stream which is related, or which is related to the output screen, right? Which means whatever you write onto this file, right, you are going to see it on the output screen, right? So whatever you read from this file is what you are going to read from the keyboard, and whatever you write onto this file, you are going to see it onto the output screen, right? And stdr, we shall see it later. Okay, and stdr is also related to the output only, I mean the screen. So whatever you write onto this file, it will be given to the file, it will be displayed onto the screen. Now if you want to use the functions which are provided by the stdio without using printf and scanf, if you want to use the file pointer and if you want to read and write the data, you can use these two. What I mean to say is, see this. Now if you observe this, getChar is used without giving any parameters to it, and by default it is going to read from the keyboard, right? Now you can, if you want to use it along with a file pointer, you can use this function getC. I mean it is going to give the same functionality, getC, and where are you going to read it from? From the input, and the input keyboard is already associated with the file pointer stdin. Got it? So you could have replaced this statement with this statement and the program will work just fine. And similarly, if you want to display onto the screen, you could have, instead of using printf, you could have used putC, right? So you could have used putC, right, ch, comma, what is the file pointer? You want to write it onto the output screen, and the output screen is associated with the file pointer stdout, right? By writing this here, you are going to see everything on the output. Got it? Okay. Now let's see a small C program which will open a file, read, and it will open a file for writing, and first we write some content into the file, and later we open the same file and we read the content and print it onto the screen. Okay, now let's see this program. Hash include studio.h, void main, file pointer. Okay, so we are creating a file pointer. This is a pointer to the structure file. Now where is this structure declared? It is declared in the this library, I mean .h. So when you include it, that declaration is going to be present there. And now char ch, it is a variable. Now first I want to open the file, right? Now let us say fopen I'm opening the file whose name is test.txt. It will be created in the same directory in which you are working in, right? And comma w means we are opening this file in the write mode. Now in case if this file is already present, then whatever contents are there, they all will be deleted, and again we start writing from the beginning, right? In case if it is not present, then this file will be newly created. Remember it, whenever I use write mode, if it is not already present, it will be created. In case if it is already present, the entire contents will be wiped out, and again we are going to start writing from the beginning. Okay, fine. Now, okay, once it is done, this fp is now associated with this file, right? So now now we are just writing printf, enter the data. Now we are asking the user to enter the data. Now let us say user has started entering the data. Now what we are going to do is while ch equal to get char, which means we are going to read the data which is entered by the user character by character, and we are going to read it into the variable ch every time. Now, and also we are going to test whether we have reached end of the file or not. Okay, now how will we know end of the file? Either you can put control C while you are entering, you can print control C, then it is going to give end of the file. Okay, now let us say ch equal to get char, we are going to get characters one by one, and every time we get a character which is not equal to end of the file, we are calling put C. Now what will this put C do is, it will take the character and it is going to print it into the file, which means it is going to write it into the file pointed by this pointer, which means whatever user has entered, that will through the keyboard it will come into the variable ch, and then through ch it is going into the file. So if you want to see what is actually happening, now let us say this is the file. When you open it, will initially be pointing to the first location of the file, and somewhere there is ch, right? And let us say this is the standard input, which means whatever user is entering from the keyboard. From the keyboard, the character will come into ch, and here we will check whether this one is equal to end of the file. In case if it is not equal to end of the file, we are going to send it into the file and we are going to print it there, right? Write it into the file. Now again this read write head will move to the next point, and again we do the same thing, right? So for every character which is entered, it will come into this variable and it will go here. Now how are we reading from the standard input to this variable ch is by using this get char. So here we are using get char. Okay, now how are we placing this character into the file? By using this put C, right? So here we are using put C to place it here and get char to place it here, right? Fine. Now what is the syntax of this one is, if you observe it, put C, please look at the syntax here, int put C int C comma file pointer. Now if you observe it, put C is going to take as an argument, first argument is int C and the second one is the file pointer, right? So that is what we are doing here. We are sending ch and then fp. Even though ch is a char, there will be a typecasting. It will be converted into the integer and that will be placed there. Okay, and after this is done, now I want to open the same file and I want to read the contents. Already the file is opened for writing, right? But then now I want to read, right? So the problem with this one is, by the time you finish the writing, let us say you have written file till here, your pointer will be pointing to the last character which is present here. Got it? The pointer will be pointing to the last character. But then once you start reading, it will start reading from here onwards, but then there is nothing after this, right? Therefore you have to go to the beginning and start reading. For this you can use that fseek, which will tell the pointer to go to the beginning. You can use the fseek and start reading, or you can use rewind and then you can start reading, but then we shall see those mechanisms later. For now, one simple mechanism is, you simply close the file, which means you simply when you close the file, everything will be flushed, and now FP will be free to be used again. Now again you can open the file in the reading mode, right? So if I again open the file in the reading mode, then automatically the pointer will be set to the beginning of the file here, right? And now I can start reading. Now how can I read it? By using getC. Now getC FP, see this. Now if I use getC, the syntax is like this. If I pass a pointer to the file structure, then getC at every time is going to read one character and it is going to return it as an integer, right? And now I am going to catch it in char, right? Again the typecasting will be done. Don't worry about this typecasting. Even though we have declared it as a character and even though there we are working with integer, it doesn't matter, right? The character's ASCII value will be given and that will be stored there and appropriate conversions will be done, okay? Now if you observe this, while ch is equal to getchar not equal to end of the file. So till we reach end of the file, we are going to do this printf %c ch. So we are going to take each character one by one and we are going to print it onto the screen. Now once it is done, I am simply closing it, okay? In order to understand recursion, what I'll try to do is, I'll take the smallest recursive programs possible, and then I'll show you how to trace out the recursion. Then we shall actually do the big recursion programs while we get them, okay? So my intention here is to explain you how the recursion works, how to trace it out, and later when the problems we face the problems where we need recursion with big problems, we shall again do it anyway there, okay? So now I'll take small problems and explain you how it works. So let me take the simplest recursion. Let us say a is a function, right, and a is going to take an argument n, integer. If n is greater than 0, then let us say I want to printf %d n minus 1, and then again I want to call a of n minus 1, right? So this is a small recursive program, isn't it? Why? Because the function a is again calling a. Now let's trace it out. So there are two ways to trace it out. I'll tell you the actual way, I mean how it works at practice, how the stack is going to be used. Here stack is the data structure which is going to be used for recursion. I'll show you how stack is going to be used in order to trace out the recursion, first thing, and next thing is without stack we shall use the tree method. So when to choose what, that depends on the type of the question. Okay, let me just explain you this first. Now I'll take a stack, and in the stack someone has to call this function, right? So initially assume that main is calling the function, and inside the main, let's say there is this main, okay, and inside the main somewhere a of 3 is called, which means a has called, a is called with the argument 3. Now main will be created here, right, and while its execution at this point a will be called. So whenever any function is called, an activation record will be created, right? This is the activation record for a of 3. A will be called with 3. So inside n the value will be 3, right? Why? Because a of 3 is nothing but the actual argument you are passing is 3 and the formal argument is n. So it is a pass by value in C. So what is pass by value? Whenever a function is being called, whatever is the value of the actual argument, that will be passed to the formal argument, formal parameter, right? It is actual parameter, that is formal parameter. Now n is going to take the value 3. So n has the value 3, then it will check if n is greater than 0. Is it greater than 0? Yes. Therefore, what is the step? Printf printf %d n minus 1, and then you are again going to call n minus 1. What will be printed? N minus 1 will be printed. Therefore, output will be 2, and again we are going to call a of n minus 1. So one thing here you should remember is, whenever we are when we keep on calling the functions again and again, and when we keep on pushing the activation records, you should always remember that while we return, or when we return from the function calling, you should know where to resume the function from. You should know where to resume it all from, right? then what we do is, that is the reason, so because of that reason what we do is, we have something called as instruction pointer IP. So whenever you call a new function, then for this particular function, the calling function will save in its own activation record what is the instruction that it has to carry out next once it returns, right? So for that reason, let me just number them. So this is a small example that we have to number it and then do it. It doesn't explain you, but then still we shall see. Let us say this is line number 1, line number 2, line number 3, line number 4, and even though it is not a line, I am putting line number 6, so that you'll understand that it's the end of the function. Now at this point, see, a of 3 has done with its printing, and then it is calling a of 2, isn't it? And once it returns from a of 2, the next statement it has to execute is 5. That is the reason I'll even remember this. This is called as instruction pointer, right? Instruction pointer is nothing but the next statement that has to be executed once you get back from the recursion. So you have to remember this. So what will be present inside the stack of a function? Its local variables and the instruction pointer. Got it? Now what about the next one? Yeah, a of 2 will be called. At this point, a of 2 will be called, right? So when a of 2 is called, what will be sent to n? N is equal to 2, right? Then what is, then is n greater than 0? Yes. Then what is it? Printf %d n minus 1, right? Then how much is this? Printf %d n minus 1 means if n is 2, what is n minus 1? 1. And then a of 1 will be called, which means this one will be called. Therefore we shall leave this activation record and push one more activation record on the top. So when we come back, what is the line we have to execute? Line number 5. So remember this in the IP, instruction pointer, right? And what is the next one? A of 1 is called. When a of 1 is called, what will be passed to n? N will receive 1, isn't it? N will receive 1 now. And this one is going to be n is greater than 0, therefore printf n minus 1. So what will be printed? 0 will be printed. And now a of n minus 1. So what is a of n minus 1? So now again, a of n minus 1 means a of 0 has to be called, right? So while I return, I'll go to line number 5. A of 0 will be called, right? And what happens to the a of 0? Check this. A of 0 is nothing but n is greater than 0? No, therefore it is going to stop. So a of 0 will simply return without doing anything, right? When a of 0 has returned, where should we come back? We should go to the calling function. Where is the calling function? It will be immediately below the called function, isn't it? Therefore I have to go to a of 1 and I have to start from line number 5. Line number 5 is saying that it is the end of the function. Therefore this will also be over. When this is over, where should we go? The calling function a of 2. And a of 2 is also saying that we have to go to line number 5, which means it is also over, right? And after this, again we have to go to a of 3. A of 3 is also saying that line number 5, which means it is over, right? And after this, we have to go to main. So where should we go to main? Main also should remember it. Let us say this is ith, right? Then main also should have IP. Now main will continue from here. Therefore output is 210. And how many activation records are pushed, or how long is the, how much big the stack is required? 1, 2, 3, 4, 5. So totally 5. For this entire function, 5 activation records are pushed. Generally they will not be interested in asking exact number of the records pushed on the stack. They will be interested in asking the order, right? So what is it? Order of n, isn't it? If we are calling a function on a of n, right? In this case a of 3, then how many stacks are required? 1, 2, 3, 4, right? 4 stack elements are required to compute a of 3, isn't it? Therefore in order to compute a of n, how many stack elements will be required? Stack records will be required n plus 1, which is nothing but order of n. So the size of stack required is order of n, that is the space complexity. Then what about the time complexity? Time complexity, you can anyway do it, right? So t of n, let us assume that the time taken to compute a of n is t of n, that equal to how much? So this is a constant time printing and checking, which means let's say c plus, and what about this? It is t of n minus 1, right? This is the time complexity required. Got it? And if you solve it, right, you are going to get how much? I think you will get around n order of n. time complexity and space complexity both are going to be order of n. Anyway, computing the complexity is not my intention here. Explaining you how this recursion works is my intention. Okay, so anyway, doing this tracing out the recursion this is the actual way how the recursion works. But if the question, if they ask you just to trace out a recursion, then depending on the number of lines, you can do it in a better way. You can use the tree method. So using the tree method, how you could do it is, these are all not important. What are the most important lines here? Printf and then this one. So let us say this is printf is this and this is a of n minus 1. Okay, so only 2 lines are required. Then we shall go in the tree method. So tree method says that a of 3, in order to solve a of 3, what do you need? You need to call printf first. So printf, what will be printed? N minus 1, and then call 2. And in order to solve a of 2, again printf 1 and then call 1. In order to solve this, printf 1, printf 0 and then call 0, right? And what about a of 0? A of 0 will die here. The reason is a of 0 is not going to call this again because n is not greater than 0, right? So your recursion will stop here. So see this, what is the depth of the tree? Depth of the tree is n, that is n plus 1, 1 2 3 4. So that is why here we needed 4. Therefore depth of the tree is also going to tell you how big the stack is required, isn't it? Now how to trace it out? See this way. So first one is, you traverse it top down, left to right, and whenever you encounter anything printf, you print it. Now what do we encounter? Printf2, therefore print 2. And again what do you encounter? Print 1. And again what do you encounter? Print 0. Yes. And now this is how this one is done, right? So if you want to see the order in which the function calls are made, a of 3 is called, and then a of 2, and then a of 1, and then a of 0. This is the order in which function calls are made. And at any time, how many maximum stack records will be present? That will be equal to the depth of the tree. This is the maximum length. Therefore, how big this stack do we need? At least you should be able to hold this entire chain. Got it? Otherwise, your program will not be finished. So anyway, if the program is small, so small like this, only few statements, then you go with this method. Okay, you go with tree method. If the program is very big, then anyway you cannot write all these statements like this. If the program is having lots of lines, you cannot write all these statements and then you cannot trace them out like this, right? In that way, in that case, it is better that you go in this method. Okay, stack method. So depending on your convenience and whatever you like, you can go with that. Fine. And let me take one more example and let me show you how it works. Let us say I want to use the tree method only. So the program is a of n. If n is greater than 0, I want to printf n and then call n minus 1, and again I want to printf n, right? This is the program that I want to work on. Okay, now how can we trace it out? So let us say, see how many lines are there? Just 3 important lines are there, right? Then I told you that when we have only 3 lines, it is better that we go with tree method. Let's go with tree method. Let's go with tree method and see how it works. Let's call this with a of 3. Then a of 3 is going to have 3 lines, right? So one line is printf 3 and then call a of 2 and then printf 3. And now again a of 2 is going to call 3 lines. One is printf 2. See why? N means it is calling printf n. Are you following it? A of n is calling printf n. A of n is calling printf n. That is why a of n is calling printf n. And a of n is calling a of n minus 1. That is why a of 3 is calling a of 2. And again at the end a of n. That is why this, right? And a of 1 and printf 2. And what about this? A of 1 is calling printf 1 and then a of 0 and then printf 1. Now what about a of 0? It will stop, isn't it? Now here also, what is the size of the stack required? Just see the depth of the tree. Don't worry about the nature of the tree, either binary or ternary tree. that depends on how many lines we have. The number of children of the tree depends on how many lines we have, because that is the way I designed it, right? Now what about the depth of the tree? 1 2 3 4. Therefore what about the height? What about the stack required? Four elements in order to do this, isn't it? So space complexity is again going to be order of n, and time complexity also you can just guess it. So what is time complexity? T of n equal to, for this one constant time is required, and for this one T of n minus 1, anyway it is again going to be order of n time, right? So now let's see what will be printed. So in order to see what will be printed, watch it. So now here we came across printf3, therefore 3 will be printed first, and now a of 2 will be called, and don't worry about what is called, we shall only see what is printed. Printf2, so 2 will be printed, and then printf1, 1 will be printed, and then 0 it will be written, and again printf1, 1 will be printed, and again printf2, 2 will be printed, and again printf3, 3 will be printed. This is how you could trace it out, alright? Okay, now let's see one more example which is bit bigger. Let's do that. Let us say I want to construct this, I want to trace out this function a of n if n is greater than 0, then I am going to call a of n minus 1, again printf n, and again a of n minus 1, right? Don't worry about this syntax. So now how many lines are there? 3 lines are there, okay? Now I want to see what will be printed as the output. Fine. So now in order to check this, so let's call this with a of 2. When I call it with a of 2, I want to see what happens with a of 2, right? So just see, a of 2 is calling a of 1, right, and again printf2, and again a of 1. And what about a of 1? A of 1 is calling a of 0 and printf1 and a of 0, right? And what about a of 1? A of 1 is calling a of 0, printf1, and again a of 0, right? So now watch it. What will be printed initially? 1 will be printed, and then what will be printed? 2 will be printed, and then what will be printed? 1 will be printed. That's it, okay? Now these are the only printing. Now how many function calls are made? 1 2 3 4 5 6 7. So do we need a stack which has 7 elements? Not required. The number of records which are required, which will be in the stack at any time, will depend on the height of the tree, not in the number of function calls. I already told you in algorithm, so but then let me repeat it here. Even though we have 7 function calls, all the function calls are not present inside the stack at the same time, all the activation records. The number of activation records that will be present in the stack will be equal to the depth of the tree at any time, the worst case number of elements. So what I mean to say is, see this, now even if you assume that this is the stack, okay, now initially what will be there? A of 2 will be present in the stack, fine, and then a of 2 will call a of 1, right? See, the order in which the functions will be called is depending on the traversal only, top down, left to right. A of 2 will call a of 1, and a of 1 will call a of 0. A of 1 will call a of 0, right? And now by this time, whenever you visit the function for the first time, function node for the first time, function call for the first time, you can push a record, and whenever you visit the function node for the last time, you can pop it off. That is how it happens. Which means you have seen it for the first time, push it, seen it for the first time, push it, seen it for the first time, push it, and seen it for the last time, pop it, right? Which means we are going to pop it off, okay? And then what about this one? Again we are seeing a of 0 for the first time. Therefore earlier wherever a of 0 was there, the second a of 0 will be placed in the same place where the first a of 0 was earlier there, right? And now this is the last time it is going to be visited, therefore it has to be popped off. So how many are required? Only only 3 stack records are required, and only they are used here. The reason is 1, 2, 3. 3 is the depth of the tree, right? And now next one, we are visiting a of 1 for the last time here, right? So when you are visiting a of 1 for the last time, that will be popped off, right? And again a of 1 will be visited, this a of 1 will be visited for the first time, which means it has to be pushed. A of 1 will be pushed, right? And now a of 0 is again visited. So where will this be pushed? See, this is full, this is full, this is empty, right? A of 0 will be pushed here, right? And this is the first time a of 0 is visited, so I pushed it, and this is the last time a of 0 is visited, therefore it has to be popped off, right? And printf 1 is printed, and again a of 0 is visited, therefore a of 0 will be pushed, right? And what about this? This is the last time a of 0 is visited, therefore popped off, right? And what about this? Last time a of 1 is visited, popped off. Last time a of 2 is visited, popped off, right? So even though there are a total of 7 function calls, 1, 2, 3, 4, 5, 6, 7, but all the 7 function calls are never present in the stack record at the same time. How many are present at any time? Only 3. Therefore, what is the maximum depth of the, or how many records are required in the stack in order to complete this execution? 3 records, right? So anyway, what is important here is to trace out, not about this stack. Till now, no question has been asked depending on how many stack records are required or how many function calls are required. That is very unimportant. But what you should really understand is how to trace it and what is the output printed. That is what you should understand. And one more thing is, in dynamic programming we have already seen it. So whenever there is this excessive recursion, which means a of 1 is being called so many times, dynamic programming says that you see what is being done one time, and then you don't call it. If the same function is being called the next time, you don't make that function call. You store it in the table and use that table and then see the result. So in case if you use dynamic programming, you can save some function calls. That is how dynamic programming will be able to help us in reducing the time and the time, okay, the time and the execution time required to finish it. But then here my intention is not in introducing or saving some time. I just want to tell you how it is executed. I want to trace out a recursion function and explain you. Okay, so this is how a recursion can be done. In case if there are less number of statements, you go with the tree method. If there are more number of statements, then we shall go with the stack method. And along with the examples, whenever I take up the example, I'll just explain you again the recursion. So recursion in this video, I'm just introducing it, but then don't think that it is over. As and when any program comes, I'm again going to take the recursion. I'll again trace out the recursion and show you how it works. We shall do lots of examples. Okay, fine. As we have seen how to analyze or trace the recursion using two methods. One is using the stack and another one is using the tree method. See, whenever the size of the function is too large, then go with the stack method. If the size of the function is too small and the main things in the function is only about function calls. For example, if you take a program like merge sort, not the merge procedure, merge sort. And similarly, if you take the quick sort, there most of the main body of the program that just contains the recursive calls to the original function. In that case, it is always better to go with tree method. And if you have a very big program and you are being called about this sorting at the end, something like this, the recursion at the end or in the beginning, only one line of recursion and lot of other code is present, then go with the stack method. Now apart from these questions, how to trace the recursion, some other questions which might be asked is, see, most frequently asked questions on recursion is trace it and find out the output. That has been asked many times. And the second type of questions which can be asked is, only one time it has been asked. The question is like this: how many times a function has been called? Or one other kind of question is, what is the time complexity? And coming to time complexity, I have already given you how to analyze the time complexity of iterative functions and recursive functions in algorithms. But here I'll just touch that topic because we are already discussing about recursion. I just want to touch it, but the detailed analysis I did it in algorithms part. So let me just show you how to find out the number of function calls in recursion. Let us say, I'll just take a small example. Let us say f is a function and f of n, right? So don't worry about the syntax. So f of n if n equal to 0, let's say return, otherwise let's say f of n minus 1 is called, and then printf n is done, and again f of n minus 1 is called. Okay, so if you observe this function, this program is containing mainly the recursive calls, right, rather than having any other code. So in this method, in this case, it is better that you go with the tree method. So let's go with the tree method and try to analyze this, and then I'll come back and show you how to find out the time complexity and the number of function calls. So let's see what happens for f of 2. If you are calling for f of 2, say this f of 2, if n equal to 1 return, sorry, n equal to 0 return, but it is not equal to 0. Therefore, what are we supposed to do? We are supposed to execute the 3 lines. What are the 3 lines? F of n minus 1, which means f of 1, and then printf n, which means printf 2, and then f of n minus 1, which means f of 1, right? And again this one, see, n is not equal to 0, therefore again 3 calls. So what are the 3 calls? F of 0, f of n minus 1 is f of 0, and then printf 1, and then f of 0, and again 3 calls. What are they? F of 0, printf 1, and then f of 0, right? And now if you see this, n is equal to 0, therefore it will simply return, simply return. So that is how we can draw the tree. And after that, how to know which one is executed first? Traverse it. Traverse the tree top down, left to right. Then you will find out which statement is executed in what order. Therefore, initially this statement will be executed, f of 2. Now f of 2 is going to call f of 1. F of 1 is going to call f of 0, and f of 0 will return. And after that, the second statement of this f of 1 will be executed. What is that? Printf n. Are you getting this? See, now when n equal to 2, f of n minus 1 is called and f of n minus 1 is called. When n equal to 2, f of printf n is called, isn't it? That is why it is printf 2. When f is 1, printf is 1, and here it is 0. F is 1, printf is 1, and here it is 0. Are you following it? Okay. Now what will be printed? Printf 1, which means 1 will be printed, and after that f of 0 of this function, which means this line of this function is called. So one beauty about this analyzing with the tree method is you need not remember which function you are in and which line, because it is already clear there. Even without knowing that information, you can directly do it, right? Therefore f of 0 and it will be returned, and f of 1 it will be returned. Now printf 2, therefore print 2 will be printed. Okay, and again f of 1 is called, and now f of 0 will return, and now printf 1, which means 1 will be printed. F of 0 will return. That's it. Therefore what is printed? 1, 2, 1 is printed. That is okay, we already know that how to trace it, but my main question is how many function calls have happened here. In order to analyze f of 2, how many function calls, or how many times the function f has been invocated. So if you see that the number of times the function has been invocated is 1, 2, 3, 4, 5, 6, 7. 7 times the function has been invocated. Therefore, they might ask you, if we call f of 10, how many times the function is invocated. So if you have to solve it, it is a bit difficult. So one thing is, maybe one small thing you can follow is, see this, if f of 1 is called, it is 1, 2, 3. 3 times it is invocated, and f of 2 is called, it is 7 times, right? And similarly, if you find out for f of 3, it will be 15 times. Then you can directly say that it is 2 power n plus 1 minus 1. Are you getting this? One method of solving it is simple. See this, for f of 1, it is 3 times. How did I get this 3 times? Because you see this, f of 1 is called here, and in order to execute this, 1, 2, 3, 3 function calls are made. And when f of 2 is called, right, now see this, 7, 1, 2, 3, 4, 5, 6, 7 calls are made. And now when f of 3 is called, you want to know how many calls are being made. See this, f of 3 is going to call here f of 2, and here printf, and here f of 2, right? And we know that this part is going to have 7, and this part is going to have 7, and this part is 1. Therefore 7 plus 7 plus 1 is nothing but 15. So how do I know that this part and this part are 7? Because we have just computed it, isn't it? Therefore, by looking at it, you can easily guess that maybe f of n is going to have 2 power n plus 1 minus 1 function calls, isn't it? Therefore, if you want to guess to know this one, 2 power 10, it is nothing but f of 10 is going to have 2 power 11 minus 1 function calls, straightforward. So using this method you can find it out, that is one way, or you can even form the recursive equations and you can try to solve them. So what is the recursive equation is, now let us assume that the number of times the function f is called is f of n. Okay, so the number of times the function small f of n is being called, let us assume that we are representing it with capital F of n. So what does capital F of n means? It is the number of times the function f is called. Now what happens in function f of n? We are going to call f of n one time, and inside it we are going to call f of n minus 1 and f of n minus 1, which means in order to complete the function f of n, we are going to call this function once and then this function and this function. Now if number of times the function f of n is called is capital F of n, then how many number of times will how many number of invocations are required in order to complete f of n minus 1? See, again let me frame it clearly without any confusion. What I am trying to say is, if the number of times the number of invocations required to execute function f of n, small f of n, is equal to capital F of n, then how many invocations are required in order to execute the function f of n minus 1? It is capital F of n minus 1, isn't it? Therefore, the number of invocations required to finish the function f of n is equal, if it is equal to capital F of n, then the number of invocations required to finish this, these two is 2 into capital F of n minus 1 plus 1. Why this plus 1? Because one time already we are calling this function, for that 1, and then for these two this function. Now if you solve it, you can easily find out that the equation. Okay, let's solve it. So how can we solve that recursive equation? That is an equation, right? Recursive equation. How can we solve it? We cannot apply Master's theorem because it is not in that format. So let's use some other function. So what is it? Back substitution. This is some other method, not the function. It is back substitution. So now f of n equal to 2 into, in place of f of n minus 1, I want to substitute it. So before that, let me write two more equations here. If f of n equal to 2 into f of n minus 1 plus 1, in place of n, if I substitute n minus 1, then what do I get? F of n minus 1 equal to 2 into f of n minus 2 plus 1. Similarly, f of n minus 2 equal to 2 into f of n minus 3 plus 1. Got it? Fine. Now what I want to do is, I want to keep on back substituting. So what happens to f of n? Let's call this one as equation 1, equation 2, equation 3. Now I want to substitute equation 2 in equation 1, which means in place of this one I want to substitute this entire equation. Then let's see what we get. Then 2 into f of n minus 2 plus 1 plus 1, which is nothing but 2 power 2 into f of n minus 2 plus 2 plus 1. Got it? Now we have to substitute f of n minus 2. So in place of f of n minus 2, I am going to substitute this part from the third equation, which is nothing but 2 square into 2 into f of n minus 3 plus 1. Already we have plus 2 plus 1 here. So which is equal to 2 cube into f of n minus 3 plus 2 square plus 2 plus 1, right? Now in general we can just generalize this way. F of n is equal to 2 power I into f of n minus I plus 2 power I minus 1 plus 2 power I minus 2 plus so on plus 1, right? Now I have to get rid of this f of n minus 1. So when can I get rid of f of n minus 1? Only case is, we know that from this function, whenever n is equal to 0, there is constant time, isn't it? Whenever n is equal to 0, there is constant time. Therefore I can write that f of n is equal to 1 when n equal to 0, right? Therefore whenever n equal to 0, we are going to get 1 constant time. Constant time you can write with c or 1, not an issue. Let's go with 1, that way it will be simple. Now uh, f of this one, if this one can be 1, then it will be easy for me. If this one is 0, then it will be easy for me. Which one? N minus I, which means if n minus I equal to 0, it will be easy for me. Then what does it mean? I equal to n, isn't it? So assuming that I equal to n, then if you substitute it here, we get 2 power n into f of 0 plus 2 power n minus 1 plus 2 power n minus 2 plus so on plus 1, which is nothing but f of 0 is already 1, 2 power n plus 2 power n minus 1 plus 2 power n minus 2 plus so on plus 1. Therefore, this is nothing but sum of n plus 1 terms. From 2 power 0 to 2 power n, there are n plus 1 terms, and the common ratio is 2. It is nothing but in GP. If you start from here, it is nothing but in GP, and the number of terms is n plus 1. Therefore, what is this? The sum is going to be a is nothing but 1, a is nothing but this one, right? A into r power, r is nothing but 2, total number of terms n plus 1 minus 1 divided by r minus 1, which is nothing but 2 power n plus 1 minus 1. Got it? So just be careful. Sometimes what happens is, in this case, if n equal to 1, they will say return. Instead of 0, they will say n equal to 1, they will say return. Then what should we do? Whenever n equal to 1, the time is constant, which means we have to try to make this one as 1. When we have to make this one as 1, what happens? N minus I should be equal to 1, which means I equal to n minus 1. Then here we get n minus 1, which means we get from 1 to 2 power n minus 1, which are just n terms. In that case, we get 2 power n minus 1. So in this case, in this particular case, we got 2 power n plus 1 minus 1. Therefore, the total number of function calls which are required is nothing but 2 power n plus 1 minus 1. Now what about the time complexity? So luckily, time complexity can also be analyzed in the same way. So see this, in order to execute this, you can write the time complexity as if it is, so 1 plus 2 into time required for this, right? F of n equal to 2 into time required for f of n minus 1 plus 1. Instead of f, you put t, just to represent it as time. Then you will find out that time is in order of n. Finally, you will get this factor which is in the order of n. Therefore, the number of order of 2 power n. Therefore, the number of function calls required or the time complexity is both going to be order of 2 power n in this case. But then what about the space complexity for this? Space complexity will simply be order of n, because see this, the depth of the tree is always order of n. That is the space complexity, because in the stack we are never going to grow beyond this. So there will be 2 will be called here, 1 will be called here, and 0 will be called here. After 1 0 is finished, next 0 will be called here. After that, next 0. After that, next 0, like this, right? And after 1 1 is finished, 1 will be called here, like this, right? Therefore, many functions are going to take place in the same record, which are all of function 0, right? Which are all having the argument 0, and all the functions which are having argument 1 will take place here. That is why space complexity is order of n, right? It is not going to be beyond n. So this is how you can find out the number of function calls as well. Okay, so now keep this analysis in mind. Later when we discuss about some other examples, I'm not going to do all this analysis. I'll try to simply get the answer. Okay, fine. Now let me explain you about single linked list. Generally, a single linked list will contain nodes, and these nodes are generally structures and which are self-referential. Self-referential means every structure will have a pointer inside it, and that pointer will point to the structure of same type. So watch it. See, struct node, which means there is a structure which is having the tag node and which has inside it two declarations. One is char data. Some data is present as a character, and along with it struct node star link, which means we have a pointer which is pointing to the structure of same type. Okay, and generally we declare we try to dynamically create many structures, and then we link them with one another like this. So we can create many structures like this, like here I have shown you 6 structures, and then we can see that there is a pointer or there is a link between one to the other, which means if you can reach this, from here you can reach this, from here you can reach this, right? So generally this is called as single linked list. It is called single linked list because every structure is having only one link, right? So one link, single link, single link, single link, and we can only move in one direction, not we cannot come back, and it is called as single linked list. So what is the advantage of having a structure as a data structure is, one other alternative which you can go for is arrays. So arrays and structures are the two popular data structures which are used to save the information. Either it's the input or you want to take it as the output. Then what is the main advantage of structures is, coming to C, arrays cannot be created dynamically. We don't have dynamic array creation in C programming language. Therefore, if you don't know well ahead what is your requirement, then you leave it to the structures. So using structures, the advantage is we can create the data structure dynamically, but using arrays we cannot create it dynamically. Your need has to be static. Got it? So now what I mean to say is here, so on the go, if you feel like you need one more element, you can create the element and add it in the link. And on the go, if you find out that you don't need some of the links, some of the nodes, you can anyway free them up, right? Let's watch it. First one is, see, this is the structure which is used to create that, and in general there will be a pointer head which will be created initially, which means like this: struct node star head. So every link will have a pointer which is going to point to where the link is starting from, where the linked list is starting from. So without this pointer, you will not be able to keep track of everything. Got it? And if you watch this, this is a pointer to the structure of type node, right? And what about this head? Head is a pointer to this, right? Generally, always we have a handle. Handle means this pointer which will give you the access to the first element, and once the first element is given, you can go on searching the link and we can get into any element. Unlike arrays, the linked list are sequential access structures. Sequential access means in order to reach an element, we have to start from beginning and we have to go to that element. That is called sequential access. Coming to arrays, arrays are dynamic access. Dynamic access means if you know the base address, right, you can directly go to whichever element you want. How is it possible in arrays? Because it is possible because arrays are contiguously allocated. Therefore, if I know the base of the array, I can get into any element by adding the offset, right, which is given as the index. So it is very easy to get into any array directly. But then if you know the head pointer of the linked list, you cannot go into any element by adding some distance, by adding some offset. The reason is there is no guarantee that every element is at equally spaced from the head. So they are dynamically created and they can be randomly present anywhere. But here we know that all the elements are present at a distance of size of the element into number of elements, right? They are all contiguous. Here it is not the case. So the one disadvantage of linked list is, even though it is possible to allocate it dynamically, the access is sequential. Therefore, searching for an element might take a long time. If you want to search for an element in this array, this structure, it might take order of n time in order to find it out. Even though you know that the location of the element, let us say you want to find out the third element, even then you have to search, traverse it from first, second, third. But then if you have to go to the third element in array, you can directly go to third element in one step. So going to any particular element number in array is order of one time, but going to any particular element number, element number means the first element, second element, third element, like that. Going to any particular element number in structure is going to take, in this linked list is going to take order of n time. Okay, and searching anyway is going to take order of n time either in array or in the linked list, provided that array is unordered. If the array is ordered, binary search can be applied, but then if the all elements are not ordered, it is going to take same time. Okay, so anyway, let's observe this question, and this question is all about this indirect selectors, these arrows, right? And you know that arrows have the highest precedence, which means they'll be in the top row, and they are left to right associative, which means when you have many arrows, many indirect selectors in the same expression, then we have to evaluate it left to right. Okay, so whenever see they have given these lines 1 2 3 4 5 lines, and in the fifth line they are talking about the printf, so you are supposed to implement all this and then you have to print it, right? Whenever such a question is given, it really helps if we can write some numbers in the pointers, which means it is better that you imagine every node is having a location, some number, and it is better that you put that number inside the pointers, so that we can use the numbers while we are trying to evaluate this. So assume that the starting address of A is 10, starting address of B is 20, like this, 30, 40, 50, 60. These are the starting addresses. Okay, the addresses of the structures. So this structure is stored starting at 10. This structure is stored starting at 20. It is just an assumption. Okay, and now what will head contain? Then the pointer head will contain 10. What will this node contain? This will contain 20, isn't it? What will this one contain? 30, which means it will be pointing to this. What will this one contain? It will contain 40. What will this one contain? It will contain 50, contain 60. Got it? So that is how you can you can place all of them. So now let's watch it. P equal to, which means they have created a new pointer P, which can point to any of these nodes. P is a pointer to the structure of type node. P equal to head. So what is head? Head value is 10, right? Head of link. Head of link means whatever head is pointing to, we are inside that. So inside that is 20. This head of link is 20. Are you following it? Now 20 means now this 20 of link means whatever 20 is pointing inside that, right? So this entire value is now 30. See, try to understand this. What is head value? Head is 10 initially. Now head of link is 20. Head of link means whatever head is pointing to, in that the link value is 20, and then head of link, which means 20 of link, whatever 20 is pointing, in that the link is 30. Now P will be equal to 30. So when you write P equal to 30, it is as good as P is pointing to this. Got it? Next one. Now watch it. So what is this one? P. So again P is 30, right? Then what about P of link? So P of link is 40. This entire thing is 40. And what about 40 of link? 40 of link is whatever 40 is pointing to, in that the link value is 50, right? And what about 50 of link? 50 of link is 60, right? So whenever you are talking about the left side, in the left side we are not worried about the value, we are worried about the location, which means in the left side, what is this completely pointing to? This is pointing to this particular element, isn't it? Okay, and one more thing, how did I evaluate it? I evaluated left to right, which means I evaluated this one first, right? And then this one, and then this one. That is how I evaluated. See, what is P? P is 30, right? 30. And what is P of link? P of link is whatever P is pointing to, in that the link value, which means 40. Now this entire value is 40. Now what is 40 of link? 40 of link is whatever 40 is pointing to, and in that link, which is 50. And what is 50 of link? 50 of link is 60, but I am not worried about the value because it is present as the left hand side. Whenever you are present in the left hand side, you are worried about the location, not as the value, which means we are talking about this location. That's it, right? And now this location should be equal to P, which means we should set this particular location equal to P. What is P? 30. So we are going to place 30 here. Now what happened? Because of this, it is going to point to C, right? This link is no more, so this is permanently lost. That 60 is permanently lost. There is no way we can recover it. Okay, and now look at next one. So head of link. So what is what is head? Head is 10, right? So head is 10. Head of link. Head of link means, again we are talking about the left hand side. So whenever we are talking about the left hand side, we don't want the value of that, we want the location, right? Head is 10. Head of link is whatever head is pointing to, in that the link value, which means this one, head of link. This one equal to, right? Let's evaluate this. So this one has to be initialized to something here. P of link. What is P? P is 30, right? And what is P of link? P of link is 40, which means head of link should be equal to 40. Are you getting this? P is 30, therefore I'll be here, and P of link means I'll be inside whatever P is pointing to in the link, which means 40. I want the value. Therefore here 40 will be placed, right? Therefore this one is going to point to this. Got it? Okay, which means this one is no more. Now this is how it is altered. So because of these three lines, the entire linked list has been altered like this, right? And now what we want is, we want to print the print something. So see what we want to print here. Print head. So what is head? Head is 10. Okay, head of link. So what is head of link? So head of link is 40 here, right? So this entire thing is going to give me 40, and next one is 40 of link. So what is 40 of link? Whatever 40 is pointing to in that link, so which is 50, right? And this one is 50 of link. What is 50 of link? Whatever 50 is pointing to. So yeah, where is 50? Yes, 50 is pointing to in that link. Link is 30, right? And now 30 of link. So whatever 30 is pointing to, 30 is pointing to this. 30 of link is 40, right? And 40 of data, whatever 40 is pointing to, which means 40 of data is D. Therefore D will be printed. Okay, did you understand this? I'll do it one more time, this last one. Observe this. See, with practice it will be very easy. Maybe you have to watch it 2-3 times. It will be easy only, don't worry. So what I mean to say is, see, what is head? Head is 10. Therefore 10 means this one. And what is 10 of link, which means whatever is present at the address 10 in that whatever is in the link, so which is 40, right? And now we are in 40 means we are here, right? So 40 of link, so 40 of link means in this 40 node whatever is link, which is 50 means we are here, right? And again 50 of link means 30, right? And now we are at 30, so 30, right? And now 30 of link is 40, and now 40 of data. So 40 means here, right? 40 of data is D. So finally what they wanted is D. What will be printed as output? D. Got it? D is the answer. Fine. On any linked list, we generally perform 3 basic operations. So one is traversing. So traversing means we want to traverse the entire list, and maybe one example is print all the elements of the list, right? And the second one is we create a new node and we insert it. So inserting. And the third one is maybe we feel that some nodes are not required and we try to delete it, right? So these are the 3 basic operations which we try to perform on any linked list. Let's take an example of linked list and then we shall see how to do it. Let's say linked list is made of the nodes like this, structures like this. Struct node, inside it there is an integer I, and then struct node star, let's say link. So it means that our nodes are going to contain 2 elements. One is an integer and other is a link to the structure of same type. And let's say we already have created a link, and the link is looking like this. It has 4 elements, okay, and then I made the appropriate initializations so that they will point like this. The first one points to this, and then I have a head. So always we are going to have a head which is going to point to the starting one. If we don't have this, there is no way we can find it out. See, one more thing, if we don't have this head, then also we could access them given that they are created using the names, which means if you create them as a local variable, not as a dynamic data structure, not using MLOp, then you can anyway have this names, and names can be used. If they are having names, you have the handle, you can access them. But most of the cases, wherever you go with these structures and linked list, we create them dynamically, and whenever we create them dynamically, there is no way they have the names. Only way is you should have the these addresses, and you should save the address somewhere. If you lose that address, it is as good as losing that node. Okay, so now let's see how to traverse it. So the last node will always contain null. So null means 0. It is not any new value, it is generally null means 0. Okay, and let us say the value present here is 1, the value is 2, 3, 4. Now I want to traverse this entire list, and then I want to see what is the value, what are all the values present in this. So how can I traverse it is, so watch it. See, one thing is you can have this head, and you can take this first and then print it, and then take this printed, and then take this printed, which means you can keep on moving the head and you can print it. But moving the head pointer is really dangerous, because once you move the head pointer to point to this node, then this node is permanently lost. In case if it is not having any name, and if you have created it dynamically using malloc, once you move this pointer, this one is lost. That is why you create a temporary pointer. So we can have like this: struct node star some temporary pointer t. It means that it is a pointer to a structure of type node, and now using this temporary pointer I can move, which means I can take t equal to head. What does it mean? It means that initially I have a t, a temporary variable t, and t is also pointing to whatever head was pointing to, right? And now using this I can keep on moving, and then I can keep on printing. Now what I'll do is I'll try to print t of, what is it, t data, which means whatever is going to be in the data I'm going to print. So don't worry about the syntax. So let us say this is printing, right? So I'm trying to print whatever is present in t, right? Okay, let me write it perfectly then. I'm trying to print printf %d, right, new line, whatever is present in this data pointed by t. So t is pointing to something, some node, in that whatever is present in I want to print. So what will be printed because of this? 1 will be printed. Then I should go to the next one and I should print it, right? So that is the reason I'll move t to the next node. So what I do is t equal to t link. So what does it mean? So now t value will be whatever is present in the t link. So let me just number them. So I told you numbering is going to be helpful here. Let us say 10 is the address, 20 is the address, 30 is the address, and 40 is the address of all this. And initially this one will contain 10, this one will contain 10, this one will contain 20, this one will contain 30, this one will contain 40, right? So now t equal to t of link. So whatever is pointed by t, go into that link and now take that value. T of link is 20. Now initialize t equal to t of link, which means this one will be pointing to, this one will get 20. Therefore now this one will point to 20, right? And again I have to print it, and then again I have to increment it. That is why I am going to put it in the while loop. I am going to put this printing and incrementing in the while loop, right? So while what? So till what point can I go? Till while t is not equal to null, right? T is not equal to null. Null means this 0 value, right? So as long as I don't reach the end, I'll keep on going, right? Now just see this, how it works. Now initially it has been, 1 has been printed, right? And then t equal to t of next means, t of link means it has taken this. And now what will be printed again? 2 will be printed, right? And after this t equal to t of link. T equal to t of link means whatever t is pointing to, it will take the link from that, which is 30, and will put it in this. So which means we get 30 here, right? So it is again pointing to this, right? And again printf this data, that i3 will be printed, and again t equal to t of link. So what happens? T of link is 40, and that 40 will be placed in this t. So which means 40, right? And now we'll be pointing to this, right? And what happens again? T is not equal to null, therefore again printf this. So what will be printed? 4, and again t equal to t of link. So what is t of link? T of link is null, therefore inside t we are going to put null, right? So finally it is going to have null. Then watch it, while t is not equal to null, but t is equal to null now, therefore it will break the loop, right? So this is how you can print the entire linked list, right? So one other way of writing this is, right, see, whenever you write any loop like this, while t not equal to null, then where is that you are stopping? You will stop we'll go to this node and then we'll take this and we'll stop there. So we are not pointing to anything at the end. Okay. So anyway, one other way of writing the same statement is while t is not equal to null is equivalent to, isn't it? This one is equivalent to while t, right? This one also has the same meaning. Why? As long as t is not equal to 0, we get into this, and whenever t is 0, which means whenever t is equal to null, we break the loop and we come out. So these two are going to have the same meaning, while t not equal to null and while t, both of them have the same meaning. Got it? So this is how we can traverse the entire list. So traversing the list can be done using this loop. And one thing you should remember is never take the head and keep traversing the list. What happens is you can traverse the list, but by the end of it, the list head will become null and the entire thing will disappear, right? So don't do that. You take a temporary variable and you can traverse it. Fine. Now let's try to insert an element in the single linked list. So before you insert any element, you are supposed to create it. How do we create a single element in a node, a structure, using malloc? So let me show you how to create this. I already shown you using this malloc how much what is the size of the node that we want. What is that we want to create? We want to create a structure by name node, isn't it? Therefore first you try to find out the size of the structure in your platform, in your operating system and in your hardware, right? Then that is called platform. So in your account to your operating system and platform, let us say there is some size fixed. So that one you can get it by using the operator size of. Size of is not a function call, it is an operator. Okay. So size of struct node y, because I want to create this, right? And now this one I will send it to the malloc. So malloc will take as the argument this one, right? Then what will malloc do? Malloc will create memory of size of this structure, right? And malloc will generally return you void star. So whenever it returns you void star, you are supposed to typecast it. Typecast it to what? You have typecast it to the pointer of type the node, structure node. Therefore I am going to typecast it. Struct node star. I'm going to typecast it, right? And now this typecasted one has to be captured and stored somewhere, right? So let's say I create a pointer struct struct node star new. So what happened because of this? A pointer called new is created. Okay, a pointer called new is created, and this new will point to a structure of type node. And because of this malloc call, a new structure will be created, isn't it? That structure will contain the I and link, two values, two members. Two members are present in this structure. And now inside this one is going to point to this. That is what has happened till now, right? So whatever address is written by this malloc, that address is captured here. Let us say the address is 50, then it will contain 50, which means we are holding that handle, which means we are having a grip over where that particular element is present. Now I want to insert this new element somewhere in this. Let us say I want to insert at the beginning. Case 1 is A, insert it in the beginning. Insert it at the beginning. So which means I want to insert it before this value, right? Now how can I do it? So one thing is, if I have to insert it here, then head has to point to this node, right? So which means if I have to insert it here, so let us say it is created here. I mean, the placement doesn't matter, but then it looks good if I write there, isn't it? And now new is pointing to this. New is pointing to this, and its address is 50, right? And now if I want to insert it here, then what I should do is I should make sure that head should point to this. But if I directly write this code, if I directly write it as head equal to new, which means whatever new was pointing to, if I directly write head equal to new, what happens is this will take the value 50 and suddenly this will point to this. Now this head will point to this one and this entire one is lost, isn't it? the entire linked list is lost. So you should not do that. So in order to see that this information will not be lost, you should be very careful here. Whenever you try to modify the head pointer, you should be careful. So initially it is pointing to this, right? Now before writing this step, what are you supposed to write is, you are supposed to link this one with this one, and then you can link this one with this one, then that will be fine. So in order to do that, so what is this value? This value is new link, isn't it? So first step should be new link, isn't it? New link, which means new link, this value should be equal to head, which means I should get a 10 here, right? So new link should be equal to head. So if I write like this, new link equal to head, then what happens is, this one got linked to this, and after that you could say head equal to new, head equal to new. So therefore this one will point to this, right? So that is how you have made the first node to be this, and you can even initialize some value. That is okay, you can put any value. Did you understand this? So inserting is, first you make the new node to point to whatever is the beginning of the list, and then you make the head to point to that. Then only this entire thing will work. The other way will not work. That is where you should be careful about, right? And next one is, let's see, let us say we want to insert the same node, that new node, not at the beginning but at the ending. Okay, which means this is going to point to this itself, right? And there is no link as of now. I want to place it at the end. So case B is, insert this at the end. Okay, now how can we insert it at the end? So one thing is, in order to insert it at the end, we should know where the end is, right? So if we have to insert it at the end, we should place it in such a way that this particular pointer will point to that node, right? So we have to go till the end and we have to get it. Now how can I go till the end? I told you, so I can write a while loop, right? So while t not equal to null. What is t? T is a temporary variable. You can create it. Struct node star t, and you can initialize t equal to head, which means t is going to start from the first node, and then while t not equal to null, which means it will go till the end, right? While t not equal to null, if I write t equal to t of next, only one line in the this loop, then what happens is, this t will be initialized with head, right? There will be a new node t, and t will be initialized to this, and it will continuously move like this, move like this, move like this, and finally it will become null. So by the time you break out, there will be null, so which means t will not point to anyone. Therefore you should not write like this. Where should you exactly stop? You should exactly stop, if you are starting from here, if you are starting pointing to this, you should exactly stop when you point to the last node. So only when you point to the last node, you can make this node point to the new node, right? Then you can add the required element at the end. How can I make sure that I'll make this t stop exactly at the last node? I do write a different while loop here, right? In the while loop, I should not say while t not equal to null. What I should do is, while this element, if I am pointing here, then what will be the next? T of next, isn't it? While t of next not equal to null. If I write like this, this t will keep on incrementing till the point where this t of next is not equal to null, which means if I write like this and if I keep on incrementing, we'll exactly stop at this point. If you want to see how it is happening, just watch it. I'll just show you. See, now initially t equal to head, isn't it? Now while t of next is not equal to null, initially t equal to 10. Watch it. While t of next not equal to null, is t of next equal to null? No. Therefore we get into it, t equal to t of next, which means whatever is here, t equal to t of next, which means 20. T of next is 20, so this will be made 20, and now you are here. Now again you will check the while loop. While t of next not equal to null, is 20 of next equal to null? No, it is not equal to null. Therefore t equal to t of next, which means this t equal to 20 of next, which means 30. 30 will be here. Again we will come into the while loop, right? While t of next not equal to null, is 30 of next not equal to null? Not equal to null. Therefore we get into it, and again t equal to t of next. So what is t equal to t of next? This 30 of next is 40, which means this will be made 40, and again we check it, right? While t of next not equal to null, is 40 of next equal to null? Yes, it is equal to null. Therefore it is where we are going to break. So finally when t equal to 40, we break this. Therefore we will be standing exactly at this point, or we got the access of the lost element. So by the end of this loop, the temporary variable t will contain the value 40, which means it will point to this. Got it? That is the meaning of it. Now what are we supposed to do? We are supposed to add the newly created value after this end. So how can we add it? Now we can take this t is the end one, right? So t of next equal to new. If I write like this, then what happens? This t of next will now contain new value. New value is 50, which means this one is going to point to this one. Therefore now look at the linked list. Now the linked list has been added with the one more element at the end. Now we can make sure that this last one is null. So in order to make sure that one, whenever you create it, it is better that you do it immediately, right? New of next. Oh, I think I have been using next, right? So here it is link. Let's say this is next, which means the link is next. So new of next. So what is new of next? Yeah. So new of next means this one. New of next should be equal to null always, right? Got it? So either you can write null or this one. It is okay, right? So now this is how you would actually add an element at the end. So what is that you should remember in this? You should never go beyond that last node. If you try to write in this code while t not equal to null, you will end up at a place where t will give you null, right? So you should not go till that point. You should stop exactly at the last node. How can you distinguish in the last node? You can distinguish it only when by using this condition. What? All the other nodes will not have t of next is as null. Only the last node will have t of next equal to null. Therefore you are supposed to go till the point where t of next equal to null. That is why this while loop is written in such a way that as long as t of next is not equal to null, we keep on going forward, and whenever we hit a point where t of next equal to null, we stop there, which means we are stopping at the last node. Got it? And one other way of writing this is equivalent to this, while this is equivalent to this while t of next. You can write like this, right? Now what is the meaning of it? Both are same. T of next is not equal to null, or t of next, both are same, isn't it? So whenever t of next becomes null, this while loop is going to break, and here also whenever t of next becomes null, this while loop is going to break. As long as t of next is not equal to null, which means as long as the element is not the last one, we keep on moving forward. Got it? So once we go there, we can add it. Understood this? Fine. Now let's try to insert insert the node after the node which we want. Okay. So first thing is, maybe if they have already provided you the link. So let us say we have created a new node, and assume that the new node is this newly created node, and then we assign the value of the newly created node to 5, and this is null, okay, as of now, and this is being pointed by new, the pointer new, right? Let us say its address is 50 and here it is present as 50. Now we want to insert this new node after the node which is pointed by this t. There is one more pointer t which is pointing to this node, and now we want to insert this new node not at the beginning or not at the ending, but then we want, okay, so ending is this, we don't want to put it not either at the ending or at the beginning. We want to place it in the middle, right, after some intermediate node. So let's assume that this intermediate node point is already given, or sometimes maybe if they might ask you to insert it after the node whichever you want. Let us say they are saying that introduce it after the newly created node is this, you have to introduce it after the node 2. Then you are supposed to traverse the link and then find out where the node 2 is present, and you are supposed to stop there, right? So how can you stop there? See this. Now you can say, you can create the new, let us say that this is not given. Now the question is, insert this newly created node after the node which is having a value 2. Now we are supposed to traverse and then stop at the node whose value is 2, and after that 2 you can insert it. Assume that all the values are distinct here, right? Then struct node star t, which means a temporary pointer is created which is going to contain initially the value head, which means I have created a new temporary variable t, and which is going to point this one to this one, right? And now I am supposed to traverse and find out a node which is going to contain a value t. Therefore, how long should I go? How far should I go? I should go as long as I don't find a node whose value is t. Therefore, while t of I, isn't it, integer I, t of I not equal to 2, which means as long as I don't find the value 2 as the data, I'll keep on moving forward, right? T equal to t of next. Since I have only one line in the while loop, I need not put the braces, right? So what is the meaning of it? I'll keep on moving this t as long as that value, the integer value of that particular node is not equal to 2. And then when will I break, when will I stop? I'll stop this loop and come out only when t of I is equal to 2. As long as t of I is not equal to 2, I keep on moving forward. Then what is the meaning of it? Initially t will be pointing to this, then t equal to t of next, which means see this. Okay, the condition is while t is not equal to 2. Is t of I equal to 2? No, t of I equal to 1, right? Therefore, t equal to t of next, which means this will be incremented. T equal to t of next means in this value, this t of next 20 will be placed, right? Which means I'll be pointing to this, right? And again, this will be tested. While t of I not equal to 2. Is t of I equal to 2? Yes. 20 of I is equal to 2. Therefore, at this point we break. We don't increase, we break and we come out of the while loop, right? And after coming out of the while loop, t is pointing to the node exactly whichever is needed, whichever is required. Therefore, I want to insert the newly created node after this particular node. Then how can I insert it? See, now t is pointing to the node after which we have to put the node which is pointed by new. Now, what are the sequence of actions that you have to think about? So think about it. So till this point we reach the node after which we have to insert it. You think about it. First of all, if this node has to be inserted in the middle, this particular pointer has to point this, and this particular pointer has to point this, isn't it? That is what we really think. I mean, we generally think it that way. This one has to point this and this one has to point this. Then what will you try? You'll try to do that t of next, which means whatever is pointed by t of next, you will try to make it equal to new, which means you try to make this one as 50. Therefore, this one will be 50, and so this one will point to this, right? And now you will try to point this one to this. But then even if you try to do that, by this time this entire thing is gone. There is no way, there is nowhere you have saved the value 30 in this entire thing. See, what are all the handles you have, what are all the variables you have? You have t, you have new, you have head, but all of them together, they don't contain anything pointing to 30. So if you try to do this, this entire list will be gone. So don't do that. Even though this one has to point to this and this one has to point to this, first you see that this one will point to this, and then you make sure that this one will point to this. So that is why writing like this is wrong, completely wrong. So what are you supposed to do? Leave it like this, 30 itself, and leave it like this, right? Now you see that this one first points to this and then this one points to this. How can I make sure that this one points to this? So this is new of link, isn't it? New link. It should point to 30. What is 30? T link. new link equal to T link. So if I write like this, if I write like new link equal to T link, then what happened is this particular new link here, this is going to point to this. Got it? Which means 30 will be here, right? And now next line, you make sure that this one will point to this. So how can I make it sure? Then T link. So this one is nothing but T link, isn't it? T link should be equal to new, right? So if I write like this, T link should be equal to new, which means this link will be equal to new. New is 50, right? Which means this one. Got it? So this is how we have inserted this newly created element in the middle, right? So you can insert it anywhere. You can insert it at the beginning, or you can insert it at the end, or you can insert an element in the middle, right? Okay. This function is the iterative version to reverse a linked list, single linked list. It is not just printing, it is reversing. So reversing is different, which means the entire structure of the linked list is going to be changed. It is not what we see in the output, it is how it is actually stored, right? Everything has to be changed, and the assumption is that, or it is given that the nodes of each list, the nodes of the list are actually made of these structures, right? Which means they have integer field, and then they have a pointer which is called next, which is pointing to which is going to act as the pointer in the structure. Okay. So every structure is having a member called next, which is a pointer to the struct node star, right? And then this particular function is written. So reverse. See, don't by heart this, because they might change the code. There are more than one way to do the same thing. So there are various functions. What I want you to do is trace it out and understand how the program is working. So how can they ask it in gate is, they might miss out one of the lines and they'll give you a blank and you are supposed to fill it. That is how the questions will be. They are not going to ask you to write the complete program, right? Even if they ask you to write the complete program in interviews, there you can write it on your own. You need not write the same one. You can just see how it works, and depending on the logic you can just get it. So let's see the logic first. Okay. So now this function is going to return a pointer and is going to take a pointer. So how will this function be called is, from the main, from wherever it is being called, it will be called like this. So reverse, we want to reverse a linked list, then head will be sent to this, which means from where you want to reverse the linked list, right? If this is the linked list, okay, then this particular pointer of this node will be sent, right? Which means you want to reverse the entire linked list pointed by this pointer, right? So reverse head. So head will be passed, and once you reverse the head, this one will become the new head. That is why it will be even saved in head, which means once you send this, you should even capture it. Why? Because now the head is going to point to the different thing, right? So if you still point to the same one as earlier after calling the reverse, then what happens is the entire list should have been modified, and now this turns out to be the last one. See, now this one becomes the first one, this one will point to this one will point to this one will point to this, and these links will no longer be there, right? And if you don't capture this, or if you don't change the head will actually be pointing to tail. So the function is going to return a pointer to this node, and you are supposed to update your head with this node, which means here head has to change here. Got it? Then it will be reversing. Initially if it is A, B, C, D in this order, then after reversing it will be D, C, B, A. Got it? Okay. Now let's see how it is going to get executed. So first one is struct node star. Okay, so let's talk about the logic first, and then I'll tell you explain you that. So the logic is this. See, if we have to reverse it, let us say the links are like this. If you have to reverse this one is going to become the last one. So this one is going to be like this, and now this link has to point backwards, right? But the problem is, if you directly go here and directly change this link to point to the back one, right, this entire list will be cut off, isn't it? Now there is no way you can again cache this list. If you simply make this point backwards, this entire list will be cut off, right? So that is why we are going to maintain three variables. One variable is going to talk about what is the current node you are working on, and the other variable is going to see what is the next node, right? Next node, and the other variable is going to see what is the previous node. Then what we do is, since we have already caught hold of the next node, we are going to now make the current next point to the previous one, so there is no danger of losing it. Then what happens, next time I'll move the current here, right? So the current node will be pointing to this, and the next node will be pointing to this, and the previous node will be pointing to this, right? So I'll use these 3 pointers so that once I have the grab of the next node, I can make the current node's next point to the previous one. So this is the logic which I am going to use. I am going to have 3 pointers, and 3 pointers are going to move along across the list in such a way that next node is always going to hold the remaining part of the linked list, and current node is going to hold the pointer to the present node, and then previous is going to hold what is the node which is exactly behind the current one. See, why should we have previous? Because if I am standing here with this, I don't know what the previous one is. I can only know this one, right? That is why previous is important. Why is next node important? Because once I make the current node point backwards, this entire list will be gone. That is why next node is important. That is why I am using all this. Okay, fine. So now we are going to use 3 variables. If I would have written the same program in recursive version, I'll show you later the recursive version, we need not have these many variables. The reason is, in recursion, the beauty of recursion is a single variable can hold can have multiple copies, and so it can hold multiple data at various times, right? Which means the same variable can be made to hold a different information. Okay, when I talk about the recursive version, it will be even more beautiful. You'll understand there. For now, just work on this. So how to trace it out? Take the example and let's trace it out. Let us say there are 4 nodes like this. One, 2, 3, 4 is the data, and the address is 100, 200, 300, 400, and head is pointing to the starting one, which means this one, and the address in this is 200, address in this is 300, address in this is 400, and address in this is null, which means this is pointing to this is pointing to this, and this is pointing to this. Okay, and now watch it. So when this function is being called, head will be sent to the current, which means the variable current, the pointer current, CUR. So current is CUR. I just use the name CUR. See, even I use the names current, previous, and next node so that it will be meaningful for you and understand. I could have used P and then TS. You will not understand it. So just understand this. Next node is used to hold the address of the next one. Previous is used to hold the address of the previous one, and the current is used to hold the address of the current one. Okay, and see, so current is going to point to this one, that is initial, right? So whenever I call this with head, then current is going to point to whatever head is going to point, which means this will contain 100. I'm just not writing the numbers. I'm just using these arrows to show you what it is currently holding. And next, previous and next node. I have one more pointer, which is previous, and I have one more pointer, which is next node, right? Fine, both are holding null initially, null and null, right? Now while current, which means current not equal to null, as current is not equal to null, current is pointing to something, then next node equal to current of next, which means you hold in this next node, you point to what the current of next is pointing to. The reason is we are going to modify the currents next. If I modify this entire thing will be gone. So just hold it as of now, hold it for some time. Okay, that is what we are doing. And then current of next equal to previous. We are now modifying this. We are modifying this to point to the previous node. Since there is no previous node for the first node, right, we are going to have previous as null, therefore it is null. Initially previous equal to null because there is no previous node to the current node. That is why previous was set to null, and now it is going to be set to null. Why? Because after I reverse the list, the first node is going to be the last node, and the last node's next pointer has to be null. Hope that you are getting it. Okay, fine. Now where are we? Yes, so current next equal to previous, and now previous equal to current. Now we have to move everything forward, right? That is why previous equal to current means previous, you just point to this, but because now this one is going to be previous, because current is going to move ahead, right? And current equal to next node, which means I want to go and work at the next one. The reason is this one is already being modified, right? Now I have to modify this one. I have to see that this one points to this. Okay, and now again I'll try to enter the loop while current. Is current not equal to null? Yes, it is not equal to null. Therefore we enter. Then next node equal to current of next, which means before you modify it, make sure that we hold the remaining of the linked list, right? Next node equal to current of next. And what about this? Current of next equal to previous. So what is current of next? Current of next is this one. It is equal to previous. What is previous? 100, which means since we are already holding this, now we can make this one point back, right? So this one is going to point backwards, which means this one is holding 100 now. Got it? This one is already over. So I'm just trying to reverse it. See the way it works. Okay, and now I just modified this, and previous equal to current. So what is previous? Again these three have to move forward, right? So previous equal to current means now you go and point this one, right? And current equal to next node, which means you two point to the next one. I want to work on this. This is over. Now I want to work on this, right? And again I'll try to enter it. So is current not equal to null? Yes, current is not equal to null. Therefore I'm supposed to work on this, right? So when I have to work on this, you make sure that you hold the next one. That is why next node equal to current of next, which means now the next node is pointing to the current of next, right? And current of next equal to previous. So we know this is the previous. So current of next means this one has to point back, right? Which means this one has to point back. Current of next is now going to hold 200, which means I'm going to point back, right? And previous equal to current, which means again I have to move everything forward. So previous equal to current means previous is going to point to this node, and current equal to next node, which means since this is done, you have to go and work in the next node. Fine, right? And again I try to enter it. So current equal to current of current is point to something, it is not equal to null. Therefore I have to still work on this. Next node equal to current of next. Make sure that if there is anything remaining, you hold the pointer of that. Since there is nothing remaining, what is current of next? Null. The next node will be made null. So this one will be made null. Got it? This one is made null, right? And now current of next equal to previous. Whatever this one is pointing, current of next, it has to point to previous one, which means what is the previous? 300, which means this one will be pointing to this, right? And previous equal to current. So this previous, everything is now again shifted. And current equal to next node. What is current equal to next node? Next node is null. Therefore current is null, which means we have modified all the nodes. Now again we try to enter the while loop. Now while loop is just trying to see if there is any more nodes to be modified, but since current equal to null, it means that all the nodes have been modified, no more nodes are remaining, right? So at this point no more nodes are remaining. Okay, so you can stop actually here. So we can stop here. That is why, see, while current means it is checking while current is not equal to null, but since current equal to null, it will return false, and therefore this while loop will break and we are going to return previous. So what is returned? The previous. What is previous here? 400. Now 400 will be returned to the calling function. Therefore the calling function is supposed to call head equal to reverse. Then in that case, since we are returning 400, that 400 will go into the head, which means 400 here. So that is how you can point to this. Now watch it. So what is the first node now? 4. What is second node? 3. What is third node? 2. What is fourth node? 1. And that is null, right? The entire list has been reversed. Initially it is 1, 2, 3, 4, and head is pointing to this. Now head is pointing to the last one, and last one is pointing to second last, third last, fourth last, like that. Got it? That is how this function is going to work. Maybe, see, I have tried to simplify this function a lot, and even I worked on the name so that it will be easy for you to understand. But then Iterative functions are sometimes, not sometimes, most of the times difficult to write and difficult to read and understand. But if I write for the same program a recursive version, it will be very easy to understand and it will be very easy to write also, and it will look really beautiful. So next we shall see the recursive version. You'll really like it. Okay. Data structures are very important to organize the data. So what is the data structure is generally, whenever we talk about any algorithm is nothing but we are trying to solve a problem. Then the problem should take some input and then the problem is going to create some output, isn't it? So the input and the output should be given in some format, right? That format is called as data structure. And depending on the format in which you give the input to the program or the algorithm, the time will vary. For example, if you are trying to search an element and if the input is given as a sorted array, then the time complexity will be lesser, isn't it? So if the input is given as an unsorted array, then the time will be more, right? So like that, depending on the data structure, your algorithm's efficiency is going to vary, right? And one of the most important and the very old data structure is stack. So initially how this stack was designed is, people have seen this drum. So earlier what used to happen is they used to have this plates made of glass, I mean the dining plates made of glass, and they used to be kept one above the other on a pile, and they used to keep them on a table. And very often it so happens that someone will try to take a plate and by mistake they'll just push it and all the plates will fall down and they get broken. So what they did is, in order to solve this problem, they came up with an idea of a drum. Okay, so they have taken a drum, and in this drum they have kept a spring, and on this spring they have kept all the plates like this, one above the other, right? And they kept the plates one above the other, and now the spring acts this way. If you pull out a plate from the top of the drum, then the spring below will push the plates so that the next plate will come on the top. And in order to sterilize these plates, what they did is they wanted to keep this drum very hot, because you know that, so when we heat them they get sterilized, right? So they used to keep this drum hot, which means you cannot put your hands down the drum, you can only take the top plate. So top plates is only reachable, right? So if you see the way it operates, we can push the plates from the top and take the plates from the top, right? So the same way stack is organized. In stack also you can push the data from one side and take the data from the same side. You cannot push the data from one side and take it from the other side. This is how stack is organized. So there are various applications of stack. I'll just list out few. There are lots of applications. You can come up with lots of applications, but I just list out a few. Okay. So one of the application is you have already seen it, recursion. So recursion is the most popular application of stack. So using stack we are going to implement recursion, and you know how this recursion has changed the way we think about programming, right? And the next one is infix to postfix conversion, isn't it? And playing with these postfix expressions. And then in parsing. So in parsing we have already seen use of this stack a lot. All the parsers are going to use this stack, and even some subclasses of parsing is like matching parenthesis, isn't it? Matching, we can do matching parenthesis, right? And we can even match tags in HTML language, right? So like this, tags, we can match them, or in general we can match the items, anything, right? Matching parenthesis, or matching if else, or whatever it is, any parsing can be done. For that we are going to use a stack, right? And maybe if you watch this browsing, in browsing also we are going to use it, right? So browsers are going to use stack. So you have seen this when we open a page, and when we want to go back, you can click on the back arrow and we go to the page which is recently visited, right? And again when we go back, when we want, if we want to go to the earlier one, again we click back, again we click back. How is it possible? Because all the pages or all the links which you have visited are arranged in a stack. Let us say this is page 1, and next if you click on a link, that will be page 2. If you click on a link, it will be page 3. If you click on the link, page 4. Now if you are in page 4, when you click back, then your browser will show page 3. If you click back, it will show page 4, like this, right? And moreover, in case of your editing also, editors will also use this, right? So if you are using notepad or any editing you are doing on your computer, generally you want to do undo, redo, all this, right? So and for undo, what we do is, your computer is going to maintain, right, a stack of activities, which means let us say you have pasted something, then it will remember pasted something, right? Or if you have typed something, then it will remember what did you type and what is his history. And whenever you try to undo it, it will go to the stack and undo, and just undo that action, again undo it. Editors are going to use it, right? So likewise, there are lots of applications you could think of, even like this. I didn't show you this set, but then I'm going to show you, don't worry. So we have something called as tree traversals, and graph traversals. So what is traversing? So when we want to visit every node, that is called as traversals. I'll show you what a traversal is, and some of the traversals are going to use stack. And some other data structures implementation, they will also take some support from stack. I'll show you all these examples. Okay, anyway, before going ahead, we have to look at the implementation of this stack. There are two popular methods or ways in which you can implement a stack. So the basic, so whatever you want to implement, whatever data structure it is, there are only two ways. Either you have to use an array which will have contiguous allocation and the size is fixed, or you can use a heap memory. So in heap you can create a structure and you can use the links, which means linked list. So either you can use a linked list or an array to implement any data structure. Whatever data structure you take, we have only two options. Either you use an array or use a linked list or use a combination of these two. These are the only two implementation methods we have. So let's see how to implement stack using array first and then the linked list. Okay. So let us say we have the problem with array implementation is we should always know what is the maximum size that you want to grow. That is always the problem, right? And once you can predict that size, which is very difficult to do in most of the cases, if you can predict that, then go with the array, right? And the advantage of using an array is, in most of the cases, implementation will be faster if you go with an array. And if you can't predict the size, then we can go with dynamic memory allocation and structures. So you can use a structure to implement the data structures. But the advantage that we get is flexibility. We can grow and shrink the data structure as you want. But the disadvantage is, in most of the cases, many cases, this linked list might take more time in order to implement the data structure. But we are lucky in case of stack. In case of stack, either you implement it using an array or a linked list, right? It is going to take same time. It is going to take constant time. I mean, all the operations. So what are the various operations that we have on stack? If you have a stack of elements, one thing is we want to push some element onto the stack. So we need pushing. And second thing is we want to take some element out of the stack. That is called pop. So we have push and pop. These are the two operations which are defined on the stack. And let's see how to implement them in case we are using this array once, and then let's see what happens in case if you are using the linked list. Okay. So let me show you what happens in case if you are using an array. Let us define a global array stack of some size, some maximum size. Okay, and you have to define this maximum depending on your need, right? Fine. And now we are going to have a variable which is going to mark the top of it, which means we'll start with a variable, and that variable will always show what is the top of the stack, because we are supposed to take the element from the stack and we are supposed to push the element at the top, isn't it? So we are going to have a variable top, which defines what is the top of the stack. Okay, so let us say int top. Okay, and assume that it is initialized with -1. So why -1? I'm assuming that our stack is going to start with 0, index 0, like this, index 0, index 1, index 2, right? So initially top will point to -1, which means nothing is there. So -1 means stack is empty. Then whenever we want to insert something onto the stack, we are going to increment the top and then put the value there. So for now, assume that we want to implement a stack of integers, which means the data which we want to insert and delete is all integers. That is why I'm defining stack to be int, right? And now initially top is pointing -1, and whenever I want to insert something, I'll increment the top and I'll insert it there. I'll increment the top and I'll insert it there, right? And whenever I want to delete something, I'll delete it and decrement the top. Therefore top is always going to point whatever is the element that is on the top of the stack. There are various ways to implement it. Implementation details doesn't matter as long as you provide with the API. API means application programmers interface, right? It is all abstract. Abstract means we don't talk about the details to the other party. Whoever wants to use our stack, we'll just tell them what are the function calls we implemented, so that they'll just without worrying about how we implemented it, either we used array or stack, that linked list, or is the top pointing the topmost element, or is it pointing one below the topmost element. All these details are unnecessary to the programmer. He will just call the functions. So that is what I'm going to implement here, right? So one thing is I want to push an element, so I want to define push. So once we push, we are not going to return anything, therefore let me define it as void push. It is going to take an integer, an item, right? So this item is going to receive some element which we want to push into the stack, right? Then before pushing something onto the stack, we should check whether we have reached the end or not, which means whether the stack is full or not. When will the stack be full? If the entire array is filled up. How many elements will be there in the array? If you have defined the array to be of size maximum, the last element in the array will be at the index max -1, isn't it? So whenever top has pointed to max -1, then we can think that the the array is full. Therefore that is a overflow. If the array or stack is full, then that is called overflow. So how can I know it? If top is equal to max -1, so it means that I have already reached the end, right? And there is no way I can push one more element, because if I have to push one more element, I have to increment the top and then push it there, but there is no element there, right? So for that reason, you have to say if top equal to max -1, then you have to hold this, you have to check this condition, printf overflow. Overflow means I cannot put it, right? So else means if this is not the case, right? So you can printf overflow and you can even return, or let's write the return at the end. Else means if this is not the case, if it is not the overflow, then we shall do this. So what is it we want to do? We want to insert the item into the stack. So how can I insert it? First, top equal to top +1, which means I increment the top, and initially if it is pointing to -1, it will now point to 0, and then stack of top, which means wherever top is pointing to now, there I'll place the item, right? This is called insertion, and with this it is over, right? And at the end you can return, or even if you don't write return also, it will simply return. Okay, so this is the code for inserting, pushing. Now if you observe this, writing these two lines is okay, but then a better programming practice will be to use that shorthand representations, which means if you can write it in a short form, it looks beautiful. So what you could do is, instead of writing these two lines, see, so you have to increment top and then place the value there, right? So what you could have done is, you can write ++ top, which means instead of these two lines, even if you write like this, stack of ++ top equal to item. This one also works, it still works and it is perfect. There is nothing wrong in writing like this. So what did you do? We incremented the top, right? And then we have plus plus means it is pre-increment. So what is incremented? Top is incremented, right? And when is it incremented? Before you perform anything, so it is so whenever you have plus plus top, it means that top will be incremented and the incremented value will be fetched. Then at that location you are going to store this, right? So just using this one line you can write it. Okay. Now let's try to see how to pop. What is popping? Popping is taking of the element. So let us assume that we'll pop a element and we'll return the element to the calling function. Then the return type of the pop function will be int pop. I want to pop it off, right? It will not take any parameter, it will just return an integer. How can you write it? So before checking whether you can, before deleting an element from the stack, it is better that you try to check whether there are elements or not, right? If there are no elements in the stack, and if you are trying to delete an element from the stack, then that condition is called as underflow. What is overflow? If all the elements or the stack is full, and if you are trying to push an element, then that is called overflow. What is underflow? If the stack is empty and if you are trying to pull an element out of it, that is called underflow. So first you should check whether the stack is empty or not. How can you check whether the stack is empty or not? If the stack is empty, then top will be -1, isn't it? So now watch it. If top equal to -1, what is the meaning of it? The stack is empty. Then what can you do? Printf underflow, which means it is an error, right? Printf underflow and return some variable -1 or something like this, which will show it is an error. Okay. Else assume that whatever you are returning is not a part of the stack that you had to agree upon earlier. So what are the members of the stack, and what are the items that you are planning to push? You have to use a number which is not there. Else means let us say it is not there. Then what we do is what is that we have to pop? So the top element, right? So wherever top is pointing to, that element I want to pop. I'll just show you how it works actually. Let us say you are pushing, initially it is -1 and you are pushing a number 1. Then 1 will be, first top will be incremented, which means top will point to this and 1 will be pushed here. Let us say next you are pushing 10. Then top will be incremented first and then 10 will be pushed. Next time if you push 20, top will be incremented and 20 will be pushed here. Got it? So top is always going to point to the top element of the stack. So what is that you have to return? Top element of the stack. And after returning the top element of the stack, you have to go back and point to the earlier element, right? So how is it done? Return. So or you can even declare a local variable and you can do it, right? So because if I do return, it will directly return. So int temp, right? Now I'm going to read that element from the top. Temp equal to stack of top. So whatever top is there, I'm going to read it. And after doing this, top equal to top -1. So what does it mean? After returning the value, after copying the value into temp, I'm just decreasing the value of the top so that it will go back. So actually popping means we are not deleting 20 from there. 20 will still remain there, but next top will be pointing to the element which is below 20, which means here. Then what happens because of this action is you will behave as if 20 is not there. Next time when you try to push an element, you will overwrite 20, right? It is not that we are erasing the element. Okay. So it is quite different from how we do it in a linked list. In linked list, whenever we delete an element, we free it, which means, right, we shall add it to the available space, we free it. But here the element is still going to remain, but we just point backwards, and later when we push an element, we overwrite on 20. Okay. So now, yeah, so what is it? Temp equal to stack. Okay, so top equal to top -1. And now finally, after either this condition or this condition, right, this is if, okay, return temp. or you can write even return term here itself in the else condition, right? Fine, got it. So if it is underflow, in if condition itself we return. If it is not underflow, we shall read the element and then we shall decrement the top and then we shall return at the end, or you can put the return condition inside it. Anyway, again, if you watch it, instead of writing these two lines, you could have even written something better. So what is it? See, now we are reading some element from stack of top, and after that we are decrementing the value of top. Instead of doing this, you could have even done the other method, right? So what is the other way, other good way? I know you could have written it like this. So you have to decrement it after the operation, right? After everything is done. That is why you can do it in the post decrement. So what is post decrement? Instead of these two lines, you could have written like this: temp equal to stack of top minus minus. So it is called post decrement. So what happens? So this decrementation will be applied to top only, but then first the actual value of top will be fetched and entire operation will finish, and after this entire expression gets over, then the decrementation will take place. So instead of writing like this in these two lines, you could have written one line. Got it? So anyway, this is the implementation of the push and pop. So what is this time complexity required for this? Either you want to push or you want to pop. Time complexity is just order of 1, which means constant amount of time. You are not, whatever the size of the stack is, you are not going to visit all the entire stack, right? So that is why this data structure is important. I mean, it is so popular because either you push element or pop element, it is going to take just order of 1 time, right? Okay, fine. Let's see the stack implementation using the linked list. The elements in the linked list have to come from a structure, isn't it? Let's define the structure first. So let's see what have to be present in the structure, and then the elements will be created from the heap memory. So what is the difference between array and linked list implementation is, we can create the elements in the linked list dynamically and then put them in the list. That is the main difference. Okay. So now let's define the structure first. So let me use this again. Assume that our this stack is going to have integer elements, therefore structure is going to have integers only. Okay, struct node integer I, and then struct node star, let's say link. So link is going to link to point to the next node. So using this structure, we dynamically create the elements, and then we keep on adding to the this linked list, so, which is also here a stack. So how do I implement this stack is, I'll just tell you the logic. See, now if I have the linked list like this, okay, let's say A, B and C are the elements in the linked list, and now we know that head already points to the first one, right? So now while implementing this linked list, I assume that the top of the stack will be present in the head of the linked list, which means in this if you see ABC like this, it actually means that the top of the stack is A, and then below the top it is B, and below that it is C. So if any element has to be added to the top, instead of adding it at the end, I'll just add it at the head here. So I'll create a new node, right? And then let us say I'll put this pointer here, and I'll move this pointer here. Therefore this head is always pointing to the top, right? So inserting is just in a constant time. I need not traverse the list and then insert it at the end. It is just inserting is a constant time operation. And what about the deletion? Deletion is simply I'll just move this pointer to point to this, and then I'll free this up. That is deletion, right? So pushing and popping is just going to take a constant amount of time. Either it is array or the linked list, right? So let's see the implementation. I think you understood the logic, right? So let's see the implementation here. Now push. Let us say they are sending you some item to push into this integer item. this is the item which you are supposed to push, which means here you are supposed to put it there. So in order to do this, first you create this entire linked list. I mean, not the entire linked list, at least one structure, one node. So how to create one node using malloc? So how can I create it? Struct node star, which means this structure I'm creating a pointer p equal to malloc. So you know that malloc is going to return the void star pointer, right? But then I want the pointer to be struct node star, so I'm going to use typecasting, which means that void star will be converted to struct node star and that will be given to p, right? So what is it? I want to call malloc. Dynamically I have to allocate the memory, and how big it should be? The memory should be at least, it should be able to hold this structure, isn't it? So that is why size of struct node star, struct node, okay, sorry. So what does it mean? First we find out the size of the structure, and then malloc will allocate the memory size which is able to hold the structure, and that memory's pointer will generally be given as void star, which we convert to struct node star, and that will be kept in the p. Now what does p hold? P hold the pointer to the newly created node. Now therefore let us say this is the newly created node. Okay, let us say this is a newly created node. Then what should I do? Now whenever you do this, you should even check if this is valid or not. Sometimes what happens is you are actually creating these nodes from the heap. Sometimes we might run out of the heap because we might have overused it, or many queues or many stacks or many data structures are continuously going to use it. Therefore it might get exhausted, which means there will be no space in the heap at all. In that case, this malloc is going to return an error, which means malloc is going to return null. So you have to check if it is not equal to null. Okay, so if this one, let us say if p equal to null, which means malloc has written an error, it cannot have any memory, then what you could do is you could say printf. Pf means printf, I'm just writing the shortcut, error, memory error of malloc. You can say malloc has written an error, and you can return simply, right? And you need not do anything. So otherwise, if it is not the case, then we go to the next statement. Then what should we do? P data. So in the p data, I'm going to put whatever the item it is, right? Whatever you wanted to push. And then what about the p link? Inside the p link, you are going to put, right, p link equal to null. As of now you put null, later we shall modify it. Okay, so now how to push it is, so now here you need not check about the overflow, because here it is not limited by this size. So earlier while implementing using the array, we are supposed to check about the overflow, right? Why? Because the size of the array is limited, but here you need not check about the overflow. In fact, this condition itself is going to check the overflow. Here the overflow will occur when the entire heap is completely full, right? So otherwise, as long as your malloc is able to allocate an element, you can still put it in the linked list. Then how can you put it? See, head has to point to this, but if you make head equal to p, this entire list will be gone. That is why before doing head equal to p, you are supposed to do this, p of link. So which means instead of this line you could write this, or instead of this line you can write like this also, p of link equal to head, which means the newly created node is going to point to this. See, this is p and this is head, isn't it? Now what about head? Head equal to p, head equal to p, right? So why am I doing like this is, why am I still including this and then still including this one is, I just want to even handle the case where this is the first element which is pushed onto the stack. So in case if this is the first element which is pushed onto the stack, then what happens is, see this, then inside this head element there will be null, right? Head will be pointing to null and there will be nothing, right? Then what happened here? So p of link equal to head, which means here I am going to put null and then head equal to p. This will be pointing to this. That is what happens, right? So this turns out to be not useful. Okay, so you can even do like this. Alright, so using this, what is the time complexity? Time complexity required is just the time required to create a node and then time required to put it in the beginning of the list. So how much time? So now head is going to point to P, right? Now how much time is it going to take? Constant time. Therefore pushing using this linked list is order of 1 time, same as pushing using array. That is the advantage here. For this data structure, for this stack, either you implement it using an array or the linked list, the time is going to be same, which is constant. Okay, now let's try to pop an element. Let us say head is pointing to some element. Alright, so now you have to pop off this head is also top here. Okay, so now you have to pop off the element which is being pointed by that. Before that you have to return it, you have to copy it somewhere and you have to return it, and after returning it, you have to make head point to the next element, this one, and you need to pop this off also, right? So one thing you should be careful is while you pop off, you should even check whether there are elements in this or not. In case if the list is empty, you cannot pop off. That is called as underflow. So first check for the underflow. So pop is going to return an element which is being popped off. So that is why return type is pop int, and then pop is being called, right? So now what is that we are going to check? First thing is you check whether okay, first let's declare this item which has to be returned int item which is going to be returned, right? And now first check if there is some element in this or not. If head equal to null, then what is that we are supposed to do? We are supposed to printf error, right? So printf underflow, isn't it? Underflow, and then what should we do? So after printing that it is an underflow, right, we are supposed to return some error code. So you agree upon some error code initially. Let us say -1 is not used in your program, in your stack. Then you can say that -1 is the error code. Then when you return -1, they will understand that it is an error, right? Otherwise, if this is not the case, then we can pop. So what we should do is we should read it somewhere. So item equal to whatever we want to actually return, item equal to head of data. So data is I, isn't it? Structure is defined as I, and now you should even be able to hold it somewhere, right? Because later you have to free it up. So declare one structure pointer also, struct node star some pointer, let us say p. Now what is the use of p? P is going to hold this item while you move the head to the next one. So you can say p equal to head, so that you are going to have a grab over this one p, and now you can, p is also pointing to this, and now you can move the head to the next one. So what is it? Head equal to head of next. So in case if there is only one element, then also since this element is going to have null, this is going to work. The reason why it works even if there is one lost element is since this element is going to be null, right, head is going to become null. That is how it works, right? And after you move the head, which means after head is pointing to this and p is pointing to this, now you can free up this space which is pointed by p. So finally you free off which is pointed by p, so that this space will be later reclaimed by other allocations. Got it? So this is how you can run the pop. So anyway, since pushing and popping are done at the beginning of the list, and since we are not traversing the entire list, the time complexity required for pushing or popping, either in case of arrays or in case of linked list, is always constant. So here also time taken is constant, some constant time. That is why I am going to write order of 1 time, right? So this is how you could implement pop function. Okay. Just like stack, queue is also a linear data structure, right? So the main difference between stack and queue is, in stack we insert the element and delete the elements from the same side, but then in queue we insert the elements from one side and we delete the elements from the other side. Okay, that is the main difference between stack and the queue. So like this, I'll just show you. See, assume that we are implementing a stack, a queue using an array like this. Then we maintain two pointers. One is called front and other is called rear. So initially front and rear will not be pointing to anything. Whenever we insert an element here, when we insert an element into the queue, either you can call it as add, right, or we can call it as insert. Like in stack, what is the terminology? Push is used to say that we are inserting an element into the stack, right? Similarly in queue, whenever we want to insert an element, we either call it as add or insert or enqueue, right? See this, enqueue means inserting, right, putting an element into the queue. So now after we insert any element, let us say we are inserting an element A here, right? Then the front and rear both will point to this, right? And whenever we want to insert any new element, what we do is we try to increment the rear and then we insert it, which means we increment rear like this and we insert the next element. If you want to insert the next one, increment the rear and then insert it. Therefore rear is the pointer which is used to point what is the latest element that has been inserted, last element, and front is the pointer which is used to say what is the last element which is inserted, or what is the first element. Let us call it that way. So the first element which is inserted is pointed by front and the last element which is inserted is pointed by rear. Okay, and the main difference between queue and a stack is, in a stack we are going to insert the elements, right? Let us say A, B, C. The first one to come out is the last one that has entered. That is why stack is also called as last in first out or first in last out, right? Stack, isn't it? The first one to insert is the last one to come out, or the last one to insert is the first one to come out. But in queue it is reverse. It is like just like this. You can think of the queue as the normal queue where we stand in many places, right? Like we stand in a queue to book any ticket, isn't it? The first one who enters the queue is going to come out, isn't it? Similarly, the first one who has entered the queue is the first one is going to be first one who will come out, and the last one who entered the queue is the last one who is going to come out, isn't it? Therefore it is also called as first in first out or last in last out data structure. Anyway, while you are implementing this stack, we need only one pointer to know what is the last one which is inserted. Therefore we are going to pull it out. But when we are implementing queue, we need two pointers. One should point to the first element and other should point to the last element, right? Why should we point to the last location? Because additions are being done at the end, isn't it? So that is how we are going to implement queue. But the problem with this kind of implementation is, see, in queue what happens is, in stack what happens is, since we are growing the array like this and we are shrinking the array like this, at any time if any space is remaining, that will always be utilized. But the problem in queue is, when we are inserting, we'll be inserting one way, right? And when we are deleting, we'll be deleting also the same way, right? Then what happens is, at some point, even though some elements are available, some free spaces are available, we'll not be able to use it. See, if I write the code in such a way that I'll increment the rear and I'll just insert it there, right? Then insertion, let us say here, rear will be incremented and D will be inserted, rear will be incremented and E will be inserted, and that's it. And there are no more insertions possible because the queue is full. Now let us say we have freed up some space. Let us say we have deleted this. So whenever we dequeue or delete an element, right, where do we delete it from? From the front. So it is deleted and front will be incremented to point to this, right? And therefore one space is available here, right? But still rear cannot increment and it cannot use it. So that is why this kind of implementation is rarely used in case of queue. So what we generally use in queue is, we take an array and we act as if the array is circular, right? So we are going to use circular representation of the array. We are not going to take any circular array. We act as if the array is circular and then we perform the insertions and deletions on the array which is which we think as circular. It is not actually circular. Okay, using that, what the advantage we get is, if there is any free space available in Q, we'll definitely take it. Okay, I'll show you how to use that circular notation, right? Now let's see how to use an array as a circular array and then implement a queue. So what is the advantage of using the circular array is, we can use up all these spaces, right? Okay, let's see this. Even though the array is normal array, I'll visualize it as if it is a circular array and I'll try to implement it that way. Okay, so even though it is a normal array, I'm just visualizing it that it is a circular array like this. Okay, now this is element 1, 2, 4 elements are there. Let's name this array as q. Then it is q of 0, it is q of 1, it is q of 2, and it is q of 3, which means I have 4 elements in the array. So if the size of the array is n, right, then I'm going to use it as if it is a n minus 1 size q, which means I'm not going to use all the elements of the array to fill up with the elements of the queue. I'll just leave one blank space. Why is that one blank space used is, since it is a circular thing, I don't know where the beginning is and where the ending is, right? So if I leave one space as the blank, then I'll be sure that at least one side it must be the beginning and other side must be the ending, right? So you see, even if it is full, I can be very sure that one side it can be beginning and other side it could be ending. If it is completely filled up, it leads to confusion, right? I'll tell you what are the reasons why we should leave that one particular cell. With example, I think it will be clear. Okay, watch it. Initially, we are going to have 2 pointers. One is front and other is rear. Initially, front and rear both will be pointing to 0th element, front and rear, and I'll initially leave 0 as blank. Okay. Now, whenever I want to insert any element, the code is always I'll increment the pointer and I'll insert it, which means I'll increment the rear and I'll insert it. Let us say I want to insert the element 10. Then what I do is I increment the rear pointer, which means R will point to this, and I'll insert 10 here, right? And if I want to insert 20, next thing is 20. Then I'll again increment the rear and I'll insert 20, which means I'll increment the rear like this and I'll insert 20. If I want to insert next element 30, then again I'll do the same thing. Again I increment the rear, right? And I'll insert 30, right? And next time when I try to increment one more, see, I already told you that if the array is having a size of 4, I'll be using only 3 elements, 3 spaces. I'll not use completely 4, and all the 3 spaces are full, isn't it? Now whenever I try to insert the next one, I have to increment R, rear, and then I have to insert it. So first thing is, from 3 if I increment R, it is not going to be 4, isn't it? Sorry, it is not going to be 0, it is going to be 4. That is the reason I use modular incrementing. Modular incrementing means I'll not do R equal to R plus 1, I'll do R equal to R plus 1 mod 4. Then 3 equal to 3 plus 1 mod 4 is 0. So when I try to increment it and do a mod with 4, then R will point to 0, isn't it? So whenever R points to 0, whenever R and F both of them points to 0, it indicates that the array is full, right? Which means the queue is full. That is used for overflow condition, right? So whenever I increment R, are you following it? Whenever I increment R and if it equals to F, which means rear equal to front, that condition is going to indicate that the entire array is full. You have taken the entire round, right? Fine. Then so if it is full, then we are not supposed to use it. Then what I do is I'll try to check it and again I set back. Okay, I'll be standing there. Let us say after some time some elements are deleted. Now if I dequeue, which means if I delete an element, where should we delete the element from? From the beginning. Where is the beginning? Always the front pointer will point to one item less than the beginning of the element, right? Which means if if the first element added is 10, front will always be pointing to one element less. Now when we delete an element, we are supposed to return 10. That is what is deleted, right? Then while deleting, I increment the front pointer and I delete it, right? Therefore I increment the front pointer and make F point to this, and then I return 10. 10 will be there only, but I act as if it has been deleted. So wherever F is pointing to, that element is deleted, right? and the next element is the next one which has to be deleted. Now if we try to insert the next element, now we shall try to increment r. Now if I increment r, it will become 0, isn't it? By 3 plus 1 mod 4, which means r will come here, right? And you know, r is not equal to f, therefore insertion can be done. Let us say element 40 is inserted. Understood this? Now again, if you want to insert one more element, then what happens is, again you try to do r equal to r plus 1 mod 4, which is 0 plus 1 mod 4 is 1. Now r plus 1 will be equal to f. Again they are equal, therefore there will be overflow. So again I cannot insert any new element. See this? So whenever there are 3 elements, I will not be able to insert one more element. So this is actually a benefit, isn't it? Because earlier, once we fill up all the elements, even though from one side it is emptied, I will not be able to use the old space. But here you will be able to use the space completely. Only one element you will not be able to use. That is the advantage of the circular. Now let's see how the underflow occurs. Underflow means how do I know that everything is empty, right? Now let us say dequeue. So next time again I want to empty the queue, then delete one element from the queue. Then how do I do it? Increment f and delete from that. So when I increment f will be pointing to this, and you return this, which means 20 is returned, right? And again delete the next one. F will be incremented from there, and next one will be deleted. And again delete the next one, which means f will be incremented from here, and f will be pointing to this, and it will be deleted, right? So whenever, now it is empty, right? So whenever q is empty, f and r both will be pointing to the same location. It need not be pointing to 0, they will be pointing to the same location, right? So there are two conditions now. Whenever you try to increment, we are going to increment r and we insert the element there. Sorry, whenever we try to insert an element or enqueue an element, we are going to increment r and we are going to insert it there. But we should check whether it is overflowing or not. What is the overflowing condition? When r equal to r plus 1, that becomes equal to f, then it means that there is overflow, right? And so once we increment the rear, if there is no overflow, we are going to insert the element there. Then the second condition is delete or dequeue. How are we going to dequeue? So we are going to increment the front, and whatever front is pointing to, we are going to delete it or return it. Got it? And what is the underflow condition? Whenever f equal to r, that is underflow condition. Got it? So depending on this circular queue is implemented using these functions. So first function is used for enqueue, right? So watch it. Enqueue means adding an item into the queue, right? So first one is rear equal to rear plus 1 mod n, which means I am trying to increment the rear pointer. Why should I increment it? Because once I increment it, then only I am going to add the element there, isn't it? Rear equal to rear plus 1 mod n, and then I'll check for the overflow condition. If after incrementing the rear, see, if rear plus 1 is equal to front, that is the condition for overflow, isn't it? That is the condition for queue is full. So after incrementing it, if it is full, which means if after incrementing the rear, front becomes equal to rear, then that is the condition for overflow, right? Then printf queue is full, right? And what about this? Then what we shall do is, in case if it is full, we should not insert the element. We should again reset the rear to where it was pointing earlier, right? Then in case if the rear was after incrementing it, in case if rear is pointing to 0, then I make it point to the earlier element. What is earlier element? N minus 1, which means in case if it is pointing to 0, I'll again take it back and I'll leave it there, N minus 1, right? Else means it is not equal to 0, then I'll just decrement it, which means after incrementing rear, after you try to insert it, after incrementing the rear, if rear ended up somewhere here, then I just decrement it, then I'll point to the earlier one, rear equal to rear minus 1, return. Else means, in case if it is not overflow, then I have already incremented the rear, I just have to put the item there, then queue of rear equal to item and return. Got it? So here one thing you should observe is, see, for checking the this overflow condition, the condition is not actually front equal to rear. The actual condition is rear plus 1 mod n equal to front. But then here I am writing the condition as if it is rear equal to front. Why did this happen? Because I have already incremented the rear and then I am testing the condition. In case if you didn't do this, what will be the actual condition to check the overflow? Rear plus 1 mod n, if that is equal to front, that is the overflow condition. Don't get confused. I didn't right away check if front equal to rear. Got it? Okay, now when I try to delete the element, so when I try to delete the element, I should check whether the queue is empty or not. So that is called underflow condition, right? So now dequeue, which means I am trying to delete an element. Now condition is if front equal to rare. So why is this one used now, if front equal to rare? Because the condition for the empty stack, empty queue is front equal to rare. I did not do anything. Directly front and rare both are equal. It means that there are no elements. But what about the overflow? If front plus 1 mod n, sorry, if rare plus 1 mod n is equal to front, then that is the condition for overflow, right? So maybe it is worth noting it. So for overflow, the condition that has to be checked is rare plus 1 mod n. If this is equal to front, this is the condition for overflow. Then what is the condition for underflow? The condition for underflow is, if front equal to rare, right? But then while writing that program, this one, I am checking this condition because incrementation has already been done here. Why am I incrementing already here? Because anyway I have to increment it later. That is why I am already doing it. So since I have already incremented it, I am directly checking it. Actual condition has to be rare plus 1 mod n, it has to be checked with front. So keep that in mind. Okay. Now if front equal to rare, what does it mean? It means that the queue is empty, then that is underflow condition, right? Then printf queue is empty and return -1. Else means there are elements in the queue. Then increment the front first. Why? Because front is always pointing one element less than the actual element, isn't it? So that gap, front will always be pointing to that gap, right? Now front equal to front plus 1 mod n. Now we are making the front point to the element which is the oldest one in the queue. Then item equal to queue of front. Now we are going to take the element from the front and then return true. Got it? So actually I have to return item. Whatever is deleted, I am going to return it. In this case, if it is false, if it is empty, I am returning -1 under the assumption that -1 is not a valid member of the queue, right? So it depends on what you agree upon, which means if you initially agreed that -1 is an element which will never occur in the queue, then maybe you can go with -1, right? That depends on what you agree upon, this return type. Okay, so one thing you should be careful about is the conditions. So now I think you understood what is the advantage of leaving that gap. I am just leaving one gap, which means even if the array is containing n elements, I'll fill it only till n-1 elements, so that one gap is going to give me two conditions. One is overflow condition and other is underflow condition. If I just fill it completely, then what happens is I'll not be able to distinguish between these two conditions. You can work out filling it completely. If you fill it completely, then what happens is both for overflow as well as underflow, front will be equal to rare. Then I will not be able to distinguish. Now if I give a gap, if I just leave one element always, then what happens is these conditions will be different. Now using these conditions, I will be able to understand whether the queue is full or it is empty. Why should I understand it? Because when you are trying to insert an element, you should never insert it if it is full, and when you are trying to delete an element, you should never delete if it is already deleted, there is no element, isn't it? So in order to understand that overflow and underflow condition, I am going to give a gap in the queue. Understood this? Okay. Binary trees have got many applications in the field of computer science, and a binary tree is like this. Any tree which is having at most 2 children is called binary tree. Okay, like this. If I have a node, this is a binary tree. At most 2 nodes, at most 2 children is called a binary tree. And many programs, how they want to access binary trees is they want to store some information in the binary tree, and later they want to see what the information is present in the binary tree. That is called as traversing. So traversing means we want to see what is the information present in every node. That is called traversing. Searching means we are searching for a particular node. The main difference between searching and traversing is traversing is done in order to see everything in the data structure. That is called traversing. Searching means once we find a desired element, we stop. That is called searching. So coming to binary trees, there are various methods in which you can traverse the information, or you could traverse a tree. There are various methods proposed, but the most important methods which are used for traversing is this. So one is in order. So in order traversing, and then pre-order traversing, and then post order. These are the most important or most popular traversing methods which are applied on binary trees. In general, these are applicable for binary trees only, but then there have been some extensions proposed in which you can extend it to any type of tree, like not just binary tree. You can extend it to trees having 3 children or 4 children or at most 5 children also. But anyway, these are the most popular methods which are applied on the binary trees. Okay. Now, one thing is, let's see with examples how each of the traversal is, and then later we shall see the programs for this, and we shall analyze the time complexity and space complexity as usual. Okay. So let us see. Let us say the nodes here are A, B, C. So what does in order traversal say is, you have to visit and traverse the complete left subtree, and then you are supposed to print the head, or let us say root. So there is a root, which means whenever you are present at a node, I call it as a root, right? Then in order says that first you finish the left subtree, and then you visit the root, and then you finish the right subtree. Okay. So this is what in order says, and pre-order says that first you finish the root, and then left, and then right, and post order says that first you finish the left subtree, and then right subtree, and at the end root. Okay. So in, pre and post really mean about the order in which we visit the root node. Okay. Which means in order applies that the root node is visited in the middle, and pre-order applies that root node is visited before everything, and post order says that root is visited after everything, right? And if you look at the order in which left child and right child are visited, they are consistent, which means here left is visited before right, here also left is visited before right, and here also left is visited before right. Now for this example tree, what does it really mean is, you visit the left child, which means visit B first, and then visit the root, which means visit A first, A next, and then visit the right. So what is right? C, right? And coming to this pre-order, again visit root, which means A will be visited, and then left, which means B, and then C, right? And coming to post order, same thing, visit left means B first, and then right C, and then A. Got it? So this is how, given a tree, these in order, pre-order and post order will be evaluated. But since it is a small example and a simple tree, I am able to do it directly. But if the tree is very big, this is going to be complex. So just to make things simple, I'll just tell you a shortcut in which you can find out in order, pre-order and post order. You use this method in the exam. Okay. So how to find out in order, pre-order and post order is this way. Watch it. Whenever any tree is given, see that every node in the tree has children. Even the leaves are B and C, they don't have any children. Even if they don't have any children, you see that you put some dummy children like this, which means I'm going to put it like this, right? And after that you start walking on the tree. So I call, what is a walk is top down, left to right, which I'll just show you. See, walk, you can imagine it this way. You can imagine as if these entire lines are some beach, and the entire everything is sea, and now walk as if you are walking on the beach. Okay. Now like this. So A. So whenever you visit A, you print it. Whenever you visit any node for the first time, you print it. Okay. And now I am going to B. Again I am visiting B for the first time, print it. And now again I walk like this. I am visiting C. I am visiting B, right? So B is now visited second time. I will not print it. And again B is visited third time. So if you watch it, every node will be visited 3 times before I finish walking entire tree and go back to the initial point. Okay. And again A is visited second time. B is and C is visited first time, so print it, right? And again C is visited second time, C is visited third time, and A is visited third time. So if I in a walk, in such a kind of walk, every node is actually visited 3 times, isn't it? Now if I print all the nodes, whenever I visit them the first time, the order I got is ABC, right? Which is nothing but pre-order. Watch it, pre-order is ABC, so the order I got is ABC, right? Therefore when you print the nodes, when I visit each node first time, right? When I visit each node for the first time, then it is called as pre-order. Now let's do the same thing. What happens, let's see, when I visit and I print the nodes when I visit it for the second time. Let us say the nodes are A, B, C, and I'm visiting them for the second time. So first time I'll not print it, first time I'll not print it, second time I'll print it. So this is the second time visiting B, therefore print it. Okay. Third time I'll not print it, second time visiting A, therefore print it. First time don't print, second time print it, right? Third time don't print, third time leave it. Now if I print it in the second time, then BAC, watch it, BAC is nothing but in order. Therefore if I print the nodes when I visit them for the second time, then the order in which I print them is exactly equal to the order in which I print them in the in order. Therefore first time if I print it, then the order is consistent with the pre-order, isn't it? And second time if I print it, the order consistent is in order, right? And let's see the third order. Obviously I think you might have guessed it. So what happens if I print it for the third time? Obviously the post order, right? So let us say this for the same example, A, B, C. Let's print the nodes when I visit them for the third time. First time, second time, third time, print it. So B is printed. Second time, first time, second time, third time, printed. C, third time, printed. A, right? So B, C, A. So it is consistent with the post order, right? So what did you understand from this? So first time when I print the elements, whenever I visit when in the walk, whenever I visit the node for the first time, it is consistent with pre-order. Second time in order, third time post order. So if you follow this order, this technique, you'll be able to answer many of the questions directly, especially when the tree is very complex. If the tree is simple, you might think that why am I doing all this, but if the tree is complex, these techniques are going to be very useful. Let's practice on one tree. Okay, now I'll give you a complex tree, not a complex tree, kind of big tree. Let us say the tree is this way: A, B, C, D, E, F, G. Okay, so what is there in this tree is A is having two children, left child and right child, but B is having only right child, C is having only left child, D is having only left child, E is having only right child. Okay, and now what I want to do is I want to print in order, pre-order and post order, all the orders for the tree, right? Then we should not follow the ordinary method because it is going to take a lot of time. So let's put that let's go in the shortcut. So what is the shortcut? You see that every node is having all the children, and then you start the walk, and whenever you visit a node for the first time, print it, and that order will be consistent with the pre-order. Second time in order, third time post order, right? So now watch it. I'm just putting the dummy nodes like this, dummy nodes, right? Don't miss out anything, all the dummy nodes have to be there. So now watch it. B has got left dummy node, D has got right dummy node, E has got left dummy node, F has got right and left dummy nodes, and G has got like this, and C has got like this. Okay, and now let's do all this. So one is I want pre-order, and then I want in order, and then I want post order also, right? So whenever I visit a node for the first time, I put it here. Then all the nodes I get here is nothing but the order consistent with pre-order. And if I visit a node for the second time, I put it here. If I visit a node for the third time, I put it here, right? So by the end of the entire traversing, I'll be able to get all the traversals, right? Fine. Now I'll start from here. So I'm visiting this for the first time. So let me print it. So what has to be printed? First time, right? So where should I put it? Here. And again B is visited for the first time, so here. See, in general in the exam they will ask you only one of them, they will not ask you all the traversal, they will ask you just one of them. But then no, I just want to do all of them because it will be easy for you to practice. Okay, now B is visited for the second time, so where should I put it? Second time is here, isn't it? D is visited for the first time, where should I put it? Here. And E is visited for F is visited for the first time, I should put it here. And F is visited for the second time, so second time I should put it here. And F is visited for the third time, so I should put it here. Now D is visited for the second time, so I should put it here. D is visited for the third time, isn't it? This is the third time, therefore I should put it here. And B is visited for the third time, right? Isn't it? B is visited for the third time, in fact it is the last time, therefore I should put it here. A is visited for the second time, I should put it here. C is visited for the first time. E is visited for the first time, put it here. E is visited for the second time, put it here. G is visited for the first time, put it here. G is visited for the second time, and G is visited for the third time. E is visited for the third time. C is visited for the second time, and C is visited for the last time. And what about this? C is visited for the last time, A is visited for the last time, therefore here. Got it? So see this, all the nodes have been visited, right? 1 2 3 4 5 6 7, 1 2 3 4 5 6 7, 1 2 3 4 5 6 7, right? Got it? So this is the pre-order, in-order and post-order of this complex tree. So any tree is given, you can do this way and you can find out what is the order, right? But then it is better to understand how the algorithm actually works, how the recursion program works, and how we are actually doing it. So for that reason, I'll write the program and we shall trace out how it really works and why should this method work first time, second time, third time, and then we shall see what is the time complexity and space complexity. It is really important that you understand how the recursion program works on this tree or any such tree, because in exam, instead of asking you, in order, pre-order and post-order, they might come up with some other order. Then still you should be able to do that. Okay, so let's see this. Now let's write the program, recursive programs, and we shall see how the recursion actually works on this in order to implement pre-order, in-order and post-order. Okay, fine. Now I'll tell you one more method of analyzing or tracing out the recursion programs on the tree. Generally I told you this, so whenever we have only less number of statements in the recursive program, I asked you to follow the tree method. But then now we already have a tree, on the tree we are doing the recursion, right? So whenever we are doing some recursive programs on the tree, one good way is to use the tree itself to find out what is happening. So I'll just show you with an example, and if you could understand this example, whatever I'm going to tell you, given any other program other than this in-order, pre-order, post-order, you will be able to still solve it very easily. And one more thing is, if you want to do only in-order, pre-order, post-order, just follow that method of visiting first time, second time, third time, that works. But given any other order visiting, or given any other program which is recursive and a tree, binary tree as input or any tree as input, you follow whatever method I'm showing you now. Okay, I'll just take an example and I'll show you with let us say in order itself. Okay, now let us say the tree is like this: A, B, C, D, E, F, G, right? A dancing tree. Okay, now what I want to do is I want to trace out how the in order works on this program. on this tree. So we already, I'm not going to write the entire program, we already know it, right? So what is that? If you have in order if it is given a t, you will check some condition, and then you will see first you do in order of t of left, we will go to left, and then we printf whatever is present there, and again we call in order of t of right, isn't it? These three statements are going to be there along with the condition checking and all. They are not important. So most important thing is there are 3 lines, okay? And now this program will be initially called at the root. So what I'll do is, now since this program has to be executed completely with this root as the input, I'll assume that we have 3 lines there, okay? So 1, 2, 3 lines are there, right? Now when we execute the first line, this line, what does it say? It is asking us to go to the left of the tree, which means when you are here and when you call this one, the program is asking us to visit the left node. So therefore from here I'll go here. Again here I have to execute 3 lines on this node, isn't it? Now I'm going to tick the lines so that I'll remember that I finished executing line number 1, so that whenever I go back I'll start with line number 2. Got it? And now I'm here, right? And what is the first line? First line is asking me to go to the left tree of this node, but then there is no left tree, right? Therefore it is as good as thinking like this: we went to the left side and we came back. Where do we come back? Again here, right? Now second line. So what does second line say? Printf. Therefore I'm going to print b. Got it? And now second line is over. So what is the third line? Third line is going to say that go to the right child. So now I'm executing third line, and therefore I'm going to the right child, right? And again in the right child of this I had execute 1, 2, 3. Now what does the first line say? First line is asking us to go to the left child, right? Therefore I'll come to the left of this. So here I have to execute 1, 2, 3. What does the first line say? Go to the left, but there is no left, right? Therefore I execute second line. What is second line? Printf, printed. What about third line? Go right, isn't it? Third line is go right, but there is no right. Therefore all the 3 lines are done. Whenever 3 lines are done, whenever you execute all the entire code on this node, we are supposed to go to the parent. Why? Parent call this function. In this stack, if you observe it, in this stack, this record for this one will be above this record. Therefore once this record is popped off, we are supposed to go there, right? So now I go here. Now we had to execute the second line. What does the second line say? Printf. What should I print? D will be printed. Now what does the third line say? It is asking us to go to the right side, but then there is no right side, right? Therefore all the 3 are over, so I have to go to the calling one. Here in the calling one, all the 3 are over, therefore I have to go here, right? And now here I have to execute line number 2. Got it? So what is line number 2? Printf. So I am supposed to print a, yes, printed. And now line number 3. What does line number 3 say? I have to go to the right child. Yes, I am going to the right child, and what should I do? I should execute 1, 2, 3. 1, 2, 3. I should execute this. Are you following it? And now you are supposed to start with line number 1. What does line number 1 say? Go to the left of it. What is left of it? Here 1, 2, 3 have to be again started, right? And again line number 1. Line number 1 says go to the left child. There is no left child. Therefore line number 2. What does line number 2 say? Printf e. Yes, printed. And now after this line number 3. What does line number 3 say? Go to the right child. So right child is here. 1, 2, 3. What does line number 1 say? Go to left child. Nothing. Line number 2, printf g. Yes, printed. Line number 3, go to the right child. Nothing, right? And now all the 3 lines are over, go back to the parent. All the 3 lines are over, go back to the parent. Now second line. What does second line say? Printf c. And third line is go to the right child. There is no right child, right? And all the 3 lines are over, go to the parent. And all the 3 lines are over, therefore function will stop. So this is the order which gets printed. So in case if you observe it, this one will be the in order. If you have any doubt, you can trace it out. See this? So how does in order work? Whenever you visit any node for the second time, you are going to print it, right? First time don't print, first time don't print, second time print. First time don't print, first time don't print, second time print. Third time, second time print. Third time, second time print. First time, second time print. First time, second time print. Third time, leave it. Third time, second time, yes, print. Third time, over, right? So if you observe it, it is nothing but the in order, right? So one other way of tracing it is this way. Now why did I show you this example with this in order is, you can apply this even if the program is not about in order or pre-order. So if in order, pre-order, post order is given, walk the tree and print it first time, second time, third time, it works. But if some other order is given, then you might get confused, right? That is why I'm doing this. Let us say they have defined some other order called as double order. Double order means I want to print every value 2 times just for fun. Okay, so now let us say the program is written like this. The program is like this, double order t. So what I try to do is I'll see if t, okay, if t, then I'll try to printf t data. I'm not writing no exact code, you just please look into the details. And then I want to go to t left, is it visible? And then I want to printf t data, right? And then I want to go to right, t right. Okay, so now what I mean to say is I am trying to do some traversal. In this traversal there are 4 steps, and moreover whenever I visit any node, I am actually printing the node 2 times, but then the printing is not directly straight away. I have some interleaving. After printing I have to execute something, which means I am actually going to some other node and again printing it, right? So whenever such a traversal is given, it will be difficult for you to do in a shortcut the number of times we have seen. I mean first time, second time, third time. So instead of doing that, I'll tell you one more method. So this method really works and it will be really helpful here. So how many statements do you have? 1, 2, 3, 4 statements you have, right? So now let me see what happens on that tree with this program. Okay, so let me write the tree B, C, D, E, F, G. Okay, so on this tree, initially at A, the function will be called, this program will be called, right, with these 4 lines, right? So you are supposed to execute 1, 2, 3, 4 lines on A, right? So first line will start with this. So what does the first line say? Printf data, which means A will be printed, right? And what does second line say? Second line says that go to the left and do the same. So go to the left side here and again do the same, 1, 2, 3, 4, right? And therefore you are no longer here, control has shifted here. Now you are supposed to execute line number 1. What does line number 1 say? Printf. So I am going to print B. Got it? And then what does the line number 2 say? Go to the left child. But then there is no left child, right? So there is no left child, so assume that it is done. And now third line says that again printed, therefore it is printed. Now what does fourth line say? Fourth line is saying go to the right child, right? So after executing fourth line, I'll go to the right child. So in the right child again I have to do 4 lines, 1, 2, 3, 4, right? What does the line number 1 say? Printf, which means D will be printed. What does line number 2 say? Line number is asking us to go to the left child, isn't it? Which means here. So again I have to start with 1, 2, 3, 4 lines. What does line number 1 say? Printf, so print. What does line number 2 say? Go to the left, but there is no left, so it is done. What about line number 3? Again printf. So I am here and I have to print F, right? Now what does line number 4 say? Go to the right, but there is no right, therefore all the lines are over. You have to go back to the parent. Now parent, line number 2 is over. Now I am supposed to do line number 3. What does line number 3 say? Printf. What should I print? D. Got it? And what does line number 4 say? Go to the right. Now there is no right, isn't it? There is no right here. So this everything is over. So you are supposed to go to the parent. Now in the parent also all the lines are over. You are supposed to go to the parent. So here, so line number 2 is over. What about line number 3? Line number 3 says printf data. So what should I print? A should be printed, right? And line number 4 says go to the right. So which means I have to go here, right? 1, 2, 3, 4. Now line number 1 here says go to the left. Oh, printf. So therefore C is printed, right? And yes, printf. And then line number 2 says go to the left. So go to the left again. Here I have to do 1, 2, 3, 4, right? And now again line number 1. So what does line number 1 say? Printf, which means E will be printed, right? And again what does line number 2 say? Go to the left, but there is no left, so consider it is done. What about line number C says, right, printf. So I have to print this. So what will be printed? E will be printed again. Now what about line number 4? Go to the right. So it is asking us to go to the right. 1 2 3 4, right? Now line number 1 says printf, which means G will be printed. Line number 2 says go to the left. There is no left. Consider it done. Line number 3 says printf, which means I have to print G, right? What about line number 4? Line number 4 says go to the right. There is no right, therefore it is done. Now go to the parent also everything done. Go to the parent, only second line is done. What is the third line? Third line says go to the right. Third line says printf, therefore printf C. Fourth line says go to the right, but there is no right, therefore everything is done. Go to the parent is also over. So this is the order in which this double order can be done. So if you follow this way, you can you can do any other big programs. Now let's see one more thing, and on one more graph, triple order. Okay, let's see this triple order traversal on the trees. See, these questions are given in that Horowitz book. From the Excel I have taken these questions. So what do they mean by triple order and double order is? Double order means they are printing every value of every node 2 times. Triple order means they are printing value of every node 3 times. So in this case, here, here and here, 3 times we are printing the value of a data, and in between we are going to visit some other nodes. See, in case if all these printings were together, then you need not do a lot of work. You can actually see which order it is, either in order, pre-order, or post order, and instead of printing it one time, you could print it 2 times or 3 times, in case if all the printings are together, right? But here the printf statements are differently located. And now if this function is called with the pointer to the root node passed to this, let's see what happens. And pf means printf. Okay, what I mean to say is, okay, let's take an example and let's watch it. See, let us say the example is like this: A, B, C, D, E, something like this. Now I want to see what happens if I call this function with pointer to the root and execute it. So whenever this kind of recursion is given, it is better that you write the numbers 1 2 3 4 5. So 5 statements are present in this code, right? So whenever it is called here, so the program is going to take this one as the input, and all the five lines have to be implemented on this node, isn't it? So 1 2 3 4 5, right? So first it will call line number 1. What is line number 1? Printf, which means A will be printed. And next it will do line number 2. What is line number 2? You have to do the same thing on the left side of the tree. So what is the left child? Again this one, right? On this one, 1 2 3 4 5 is called. Now line number 1. What does line number 1 say? Printf. So what has to be printed? B. And line number 2. What does line number 2 say? Do the same thing on the left, which means on this one, 1 2 3 4 5. Now what does line number 1 do? Printf. So printed B, right? And what about line number 2? Line number 2 is go to the left child, but there is no left child, therefore you need not worry about it, right? And what about line number 3? Line number 3 says again print. So we are here, right? So again D will be printed. And what about line number 4? Go to right child. There is no right child to D, right? So you can consider that D is a fourth line is also over. What about line number 5? Printf. So what will be printed? D will be printed, right? So after this we return back here, right? So since all the lines are over, we return back. Now here we are in line number 3. So what does line number 3 say? Printf. What has to be printed? B, right? And again line number 4. What does line number 4 say? We have to do the same thing on the right child. Since there is no right child, right, you need not worry about it. What about line number 5? Printf, right? So what has to be printed? B has to be printed. Got it? And now it is over. And now we go to the parent. Now what does it do? Line number 3. What does line number 3 say? Printf. So again you have to printf A, right? And after that line number 4. What is line number 4? Go to the right child, right? So which means here I have to write 1 2 3 4 5 and execute all of them, right? Now what is line number 1? It says printf C. Yes, this data, right? And what about line number 2? Line number 2 is again we have to go to the left child, but there is no left child, therefore again continue here. So what does line number 3 say? Printf. So what has to be printed? C. What about line number 4 do? Line number 4 is asking you to go to the right child. So here I have to call 1 2 3 4 5 and execute, right? Now here I am. Line number 1 says printf. So what should I print? E should be printed. isn't it? And line number 2 says triple order on left child, so left child is not there. And line number 3 says printf, what should I print? E, right? And line number 4 says again triple order on right child, but there is no right child. What about line number 4? Line number 4 says, oh, line number 3 is or S. Now line number 4 says right child, there is no right child. What about line number 5? Line number 5 says again printf, therefore E will be printed, right? Everything is over, so go to the parent. So in the parent, 4 lines are already over. Now it is 5th line. What is 5th line? Just printf, C will be printed. All the 5 lines are over, go to the parent. What is the 5th line? Printf, what will be printed? A will be printed. So this is the output when you run this on this. Got it? So this is how you should be analyzing it. Okay. Now there will be some kinds of questions on trees, like how many trees are possible with these many nodes. Okay. Now let's explore that kind of question. Let us say we have one node. If I have one node, then how many binary trees are possible? So if I have one node, the number of binary trees possible is obviously 1, isn't it? The node itself, which is nothing but the root. And if I have two nodes, how many binary trees are possible? So in case if I have two nodes, the number of binary trees possible will be 2, isn't it? One will be like this or the other will be like this. There is no other way you can put it, right? And if I have 3 nodes, how many binary trees will be possible? So in case of 3 nodes, the number of binary trees possible will be, one is like this, right? And other is like this, left skewed. It is also called a left skewed. It is called skew, okay? Which means left side completely, right? And the other one is right skewed, okay? And the other one is like this, zigzag, right? And the other one is like this. So if I have 3 nodes, the number of binary trees possible will be 5. And just remember one thing here. So whatever we are talking about here in this case, I'm talking about the unlabeled trees. Unlabeled trees means I'm not talking about the specific node name. In case if you name the nodes, then the number of trees possible will be even more, right? So I'm talking about the structure. So how many structures are possible? With 3 nodes, number of structures possible is 5. So likewise we can go on. 1 node, 2 node, 3 nodes, right? So in general, if you want to see how many nodes are possible or how many binary trees are possible with n nodes, the formula is this. You can prove it with induction. I'm not going to do the proof. You can prove it. 2n cn divided by n plus 1. This is the number of nodes, number of binary trees possible with n nodes. For example, if you want to see how many did we get here, 1, 2, 3, 4, 5. So with number of nodes equal to 3, we got 5 trees, isn't it? Now if I put n equal to 3, then what do I get? 6c3 divided by 4, isn't it? Then what is this? 6 into 5 into 4 divided by 3 into 2 into 1 into 4, right? Then what is this? It is 5, right? Therefore the number of trees possible with 3 nodes is 5, right? And this is for unlabeled, right? So you can write it somewhere. The number of binary trees possible with 3 unlabeled nodes is this much. Now what about labeled nodes? If I try to extend this concept to labeled nodes, then what happens is, labeled nodes means I'm going to give the names to the nodes, right? Then every tree is now, it can be represented as 3 factorial trees. In this sense, let us say this structure, if I take only that structure, this particular structure, right? This one is actually, if I label the nodes, it is as good as, or it represents nearly 6 trees, exactly 6 trees. How? See this, in one of the tree A can be root, isn't it? In one of the tree B can be root, right? And in one of the tree C can be root, right? So you can imagine it like this. There are 3 blank spaces, 3 nodes, and I have 3 names A, B, C. How many ways can we fill these blank spaces with these 3 objects? First one can be filled with three combinations, and once you fill one blank space, then the number of combinations available for the second one is 2, and once you fill it up, the number of combinations available for the third one is just 1. Therefore 3 into 2 into 1, which is nothing but 3 factorial ways you can fill up these spaces. That is what I am showing you here, right? So the root can either be A, can either be B, can either be C. Therefore 3 possibilities, right? And now the remaining, they also can be of 2, right? Which means here I can have B, here I can have C, or root can be A, and here I can have C, and here I can have B, right? Or here also same thing, right? Here I can have A, here I can have C, right? Or here I can have B, here I can have C, and here I can have A, right? Or here I have C, isn't it? Now here I can have A, here I can have B, here I can have B, here I can have A, right? Therefore, in case if I go with labeled nodes, right, every structure is capable of generating n factorial trees. So if these many structures are possible and every structure is able to generate n factorial trees, then in case of labeled nodes, the number of binary trees possible with n nodes will be, you have to multiply this with n factorial. That will be total number of binary trees possible, right? So the number of binary trees possible without labeling, which means unlabeled nodes, with unlabeled n nodes is 2n cn divided by n plus 1. The number of binary trees possible with labeled n nodes is this much. Got it? So this is the formula which you can remember it, right? So there will be some questions like this: how many number of nodes will be possible? Now the next thing is, it is not just about the number of nodes. They will even give you the number of nodes, and then they will say that this is the particular order we have. Okay, I'll just show you in the next video. Okay. Binary tree is a special kind of binary search tree is a special kind of binary tree. The main problem with binary tree is, if you have to search for a node, there is no particular direction. You might have to end up searching everywhere. So if you can insert the elements in some proper order, in some order, then what happens is searching an element will be easier. So the trees which will help us in searching an element, they are called as binary search trees. These trees have special property which will be very useful for us while we search. And in general, if you have a binary tree, if I have to search for an element, it is a normal binary tree, right? If I have to search for an element, then I might have to go through every node. Therefore, time complexity taken may be order of n, isn't it? If I have to visit every node, then the time complexity is either pre-order or post-order or in-order. It is going to be order of n, isn't it? Now, with some good implementation, we can produce binary search trees, which if we could balance, then they are called as balanced binary search trees, which could generate a good performance. In this sense, search time can be order of log n. So that is the advantage of binary search trees. Binary search trees are going to help us search better, and in order to have log n complexity, we do balanced binary search trees. We shall see all of this. Let us first start with the binary search tree. So in coming to GATE, in GATE exam, they are generally asking you small questions about this. Insert these elements into the binary search tree, delete this element, maybe what is the in order, pre-order, like that. Okay, let's see this one. Now, so it is asked in GATE 1996. The question is, insert all these elements into the binary search tree. So binary search tree operates this way. If you have a root, okay, now if you have an element at this node, then all the elements to the left of it will be less than this, and all the elements to the right of it will be greater than this. In general, whenever we talk about a binary search tree, we assume that the nodes are not repeated, because if the nodes are repeated, then it will be meaningless. In the sense, binary search tree is applied for storing the keys, K-E-Y-S, keys. Now these keys are going to point to some record. Now two records are not supposed to have the same key. So that is the reason in binary search tree we assume that always the numbers are distinct. In case if the numbers are same, maybe you could compromise and you can put it this way, which means the number, if a number is something is here, then all the numbers less than or equal to that number will be in the left subtree, okay, and all the numbers which are greater than that will be in the right subtree. Got it? So this is a compromise, that's it. So in general, this is strictly binary search tree is supposed to have distinct keys, and all the elements which are less than this will be present in left subtree, and all the elements which are greater than this will be present in the right subtree. Okay, now let's try to insert these elements into the binary search tree. Okay, now first one is 50. Then what is inserted? 15. Is 15 less than or greater than 50? It is less than 50, right? Therefore it is inserted in the left. Are you following this? If element is less than this element, I am inserting it in the left, right? And what about 62? First compare with the root and then follow the flow, right? So compare with the root. What about 62? 62 is greater than 50. Therefore it is supposed to be inserted in the right of the root, right? And what is the next one? 5. So 5 is less than 50 and less than 15. Therefore 5 is inserted in the left. What about 20? 20 is less than 50 and 20 is greater than 15. Therefore 20 is going to be present here, right? What about 58? 58 is greater than 50 and less than 62, which means 58 is going to be here, right? What about 91? 91 is greater than 50 and greater than 62. Therefore 91 is going to be here, right? Next one is 3. 3 is less than 50, less than 15 and then less than 5. Therefore 3 is going to be here. What about 8? 8 is less than 50, less than 15 but greater than 5, which means 8 is going to be here. Next one is 37. 37 is less than 50, greater than 15 and greater than 20. Therefore 37 is going to fall here, right? And what about 60? 60 is greater than 50, less than this but greater than 58. Therefore 60 is going to be here, right? What about 24? Less than 50, greater than this and greater than this and less than this. Got it? That is how you can organize it. So in case if you have any doubt whether we did it right or wrong, I'll tell you how to check it. So whenever you do any modifications like insertion or deletion into the binary search tree, you can check it this way. You can directly check by going to every node, which means every subtree is, if a tree is a binary search tree, then every subtree is also a binary search tree, which means you can take any subtree. See this, 5 less is here, greater is here, fine. And what about 20? 20 and 37, it is greater, and then 37 and 24 lesser, and this is also a binary tree. So you can go to any subtree, which means the subtree containing only these two nodes, and you can see that is also a binary search tree. It is a binary search tree, right? And what about this binary? Yes, it is a binary search tree. So you can check everywhere that it is going to follow the binary search tree properties. That is one checkpoint. Second checkpoint is, if you try to do the in-order traversal of a binary search tree, then you are going to get all the nodes in the increasing order. It is very important. The in-order traversal of a binary search tree is going to give you sorted order of the elements, which means you can insert the elements into the tree in a binary search tree, and then you can print them in order. Then you are going to get the sorted list of the binary search tree, sorted list of all the elements. Okay, now see the in order of this. So before going to in order, put the dummy nodes in place so that you can know when we are visiting a node for the second time. Okay, first time, first time, first time, first time, second time. So 3 is printed. So if you observe it, the first element which is printed is the leftmost element, right? And leftmost element is the least element in the binary search tree. It is also important. So if you want to see the leftmost element, that is least element of the binary tree, that will be in the leftmost. So how to find it out? Maybe if given a pointer to the tree, and if you are asked whether to find out the the smallest element, then you have to you have to keep coming down left, and the one which is in the leftmost position is the least element. Now how to traverse it? You can do it this way: t equal to t of left while t. So while t means you will keep on going until t becomes null, right? Or while t of next. Okay, I'll show you how to write the code later. Anyway, let's finish this off. Now I'm talking about the in order. Second time when I visit it, I'm going to print it. It is the third time. Second time when I visit it, I'm going to print it, right? First time, second time, print it. third time, right? Third time, second time, print it. First time, second time, print it. First time, second time, print it. Third time, second time, print it. Third time, second time, print it. First time, second time, print it. First time, second time, print it. Third time, leave it. Third time, second time, print it. First time, second time, print it. Third time, right? So if you observe it, right? So all the elements which we get in order by traversing in order in a binary search tree are now in the ascending order. Got it? In exam what they'll ask you is, they'll say that a binary search tree has so and so post order, then what is the pre-order? They'll ask you such question. So let's solve one question like that, then you'll understand what I mean to say. Okay. Now let's see how to delete an element from the binary search tree. So this is a binary search tree. Okay. Now I want to delete an element. So whenever you want to delete an element in binary search tree, you are supposed to see what kind of element you are trying to delete. There are three kinds of elements. I mean, in general, you can classify the elements to be of three types when it comes to the deletion. So one is we are trying to delete a leaf. What is the property of a leaf? It will not have any children, right? And the second one is you might try to delete a non-leaf. Okay. Now a non-leaf can be of two types. One is non-leaf means it is having children, right? So one is it is having only one child, and the other type is it is having two children. Right? Now we have to distinguish between these three cases, and the deletion depends on which case we are dealing with. Are we dealing with the leaf case, or are we dealing with a non-leaf with one child, or are we dealing with a non-leaf with two children? We have to deal with all these three, right? Okay. Now whenever you are trying to delete a leaf, then you need not do anything much. See this? Let us say I want to delete node number 40. So if I delete node number 40, nothing gets affected. The tree will be intact, right? You are not going to break it apart. So therefore, you can directly delete it without worrying about anything, right? So when you are deleting a leaf, you need not worry about anything. Next one is when you are deleting a non-leaf, yes, then you should be careful. There are two conditions. One is that non-leaf might be having one child, and other is it might be having two children. Let's talk about one child. Let us say I want to delete node number 25, right? This one. Now how can I delete it? If I delete node number 25, there is a chance that even 27 will go off, right? Which means the tree will get disconnected. So we have to protect 27. Therefore, the rule is whenever we have only one child, if a node is having one child, and if you are going to delete that node, then make that child point to the grandparent, which means make this 27 connect to this 30, and then you can delete it, which means when you are going to delete this one, you connect this 27 here, so you can delete this, but you have to connect this 27 here, and then you can leave it. So in case if 27 is having even more links, then they all will come here. Got it? And next one is deleting a node with two children. So which means if you want to delete this node 15, it is having two children, right? Then how are you going to do this? See, unlike one child, if it had only one child, then I could have taken this entire link and I could have attached it to the 20, right? But then now by deleting it, I have to deal with two children, isn't it? So, and these two children cannot directly go and connect to the grandparent. Okay. Now there are two methods. One method says that whatever node you wanted to delete, go to the right subtree and you take the least element of the right subtree and you put it there. Okay, which means one algorithm will say go to the right subtree. One method, you can use any of these two methods. Okay, go to the right subtree, which means this one. Okay, and now take the least element. What is the least element? 16, and you replace it here, right? Why should this method work is, see, already every element in the right subtree is greater than this, isn't it? Now if you take the least element and you place it here, the remaining elements will be greater than that least element. Therefore still it will be a binary search tree. Are you following it? See, if I replace this element with the least element from the right subtree, that is also called as in order successor. Why? If you sort the elements in order, which means if you find out the in order, 15 will be succeeded by 16. That is called in order successor. So if you replace it with in order successor, which means if 15 is replaced with 16, then still the binary search tree property holds. The reason is this. See, already all the nodes in the right subtree are greater than 15, and now if I take the least element from here and if I put it there, right, the remaining elements are still greater than this least element. That is why it works. I hope that you are getting it. Or the other method is, you go to the left subtree and you take the greatest element, which means you have to take 12 and you have to substitute here. Why do you think that this method will also work fine? Because already all the elements here are less than this, right? Now by taking the greatest element and putting it there, the remaining elements will be less than this, and all these elements will be greater than this, which means again the binary search tree property follows, right? So what I mean to say is, you can delete either 16 from here and you put it here in place of 15, it works. Check this. All these elements are less than 16 because we are replacing the root with a greater element. Therefore, if earlier 15 is greater than all this, then a greater element will be greater than all this, isn't it? And now these elements are all greater than 15. Now I have taken the least element among them, therefore the remaining element will be greater than this. Therefore again it is a binary search tree. Or instead of 16, you could have taken the greatest element from the left side, right? Which means you could have taken 12 and you could have replaced it here. Got it? And now what happens because of this? See this. Now all the elements in the left side will be less than this. The reason is I have taken the greatest element and I kept it there. And all the elements here will be greater than this. Why? Anyway, 15 was greater than this, and now these all elements were greater than 15 and 12 is less than 15. Got it? So that is why any of these methods will work. Either you can follow this method or this method. Got it? Now whatever you do, whenever you delete the element, the height of the tree will either be the same or it will decrease by 1. It will not increase. By doing deletions, we should never increase the height of the tree. By doing insertions, the height of the tree might increase. Okay. Now let's say I'm taking the 12 element number 12 and I'm substituting it here. Then what happens here? 16 and 12 will be deleted. Why do you think that 12 will be deleted? Right? So because 12 is a leaf and you can delete it directly. In case if 12 is not a leaf, then it will have only one child. It will not have two children. Okay, my question is this. See, now when you are trying to delete either the predecessor of the in-order predecessor, which means the largest node from the left side, or you are trying to delete the smallest node from the right subtree, I am saying that it will not have two children. It will either be a leaf or it will have only one child. Why is that so? Can you think about it? My question is this. See, either you are trying to delete this element which was 12 earlier, right? So it is 15, right? Either you try to delete the largest element in the right subtree, or you are trying to delete the smallest element in the largest element in the left subtree, or the smallest element in the right subtree. I am saying that either these two nodes will be leaves or they will have only one child. Why is that true? Can you think about it? The reason is simple. In case if it is having two children, then it means that it is having both the left child as well as the right child, right? Then this one cannot be the greatest element. Why? Because it is having a right child. Since it is the greatest element, it is not supposed to have any greater element, which means it is not supposed to have any right child. Therefore, in case if it is not a leaf, it could have only one child which will be less than this, which means left subtree. Then when you are trying to delete it, you can follow that case, isn't it? What is the case? you take the child and attach to the grandparent. Got it? Similarly, here also on the other side, now if this is the smallest element, then it will not have any left child, because if it has any left child, then it means that there are even smaller elements than this, which is a contradiction, isn't it? If there are any smaller elements than this, then the smallest element will be this. I would have picked up this. Got it? Therefore, when you are talking about the smallest element in the right subtree, it will either be a leaf or it will have only the right child, which means it will have elements greater than this, but it will not have any elements less than this, right? Therefore, in any case, either it will have 0 children or only 1 child, right? In case if it is having only 1 child, you can follow this case, right? So 1 child case, what is it? You can delete this and you can attach this and you can take it there. Got it? That is how deletion happens. Now let's fix up to one thing and we can do it. So what do you want to fix up? Let's say I want to delete the in-order successor. So what is in-order successor? The greatest element in the right subtree is in-order successor. What is in-order predecessor? In-order predecessor means the least element in the right subtree is called as in-order successor, and the in-order predecessor is the greatest element in the left subtree. Okay. Now, which one do you want to delete? Let's go with in-order predecessor. In-order predecessor means the greatest element in the left subtree. What is the greatest element in left subtree? 12. So let's do this. Now 12 will be there, 15 is deleted, right? And next time let us say I want to delete node number 10. So if I want to delete node number 10, what is the case? It is having only 1 child, and when a node is having only 1 child, we directly connect it to the grandparent, isn't it? Therefore 2 will be connected to 12 directly, which means 10 will be deleted and 2 will be connected. Got it? Now let's say I want to delete 2. Yes, you can directly delete it because it is a leaf, isn't it? Let's say I want to delete 16. Yes, you can directly delete it. Okay. And let's say I want to delete 30. So how can I delete 30? Right? Since it is having only 1 child, I have to connect the to the grandparent, this one 27. Got it? And now assume that I want to delete 27. So you can directly delete it since it is a leaf, right? Okay. Now let us assume that I want to delete 12 now. This is interesting case. See, now there is only 1 child. Now it doesn't mean that you have to take only 1 child and connect it. The entire link will go and get connected, right? So when you delete this 12, this entire link has to be connected to 20, which means 17 will go here and 19 will go here. Got it? That is how it happens. Now let us say I want to delete 20. If I want to delete 20, right, then it is the root and it is not having any right child. Therefore 17 will become the new root. Got it? Now if I want to delete 17, then 19 will become the new root. Then finally 19 will be deleted. That is how the deletion works. Okay, fine. Now while we are deleting a node from the binary search tree, we have to sometimes find out what is in-order successor and what is the in-order predecessor, either in-order predecessor or in-order successor. We are supposed to find it out, right? So the problem boils down to this. Now given any pointer to any node, right, or given any pointer to the root of a subtree or the root of a tree, how can you find out the least element in this, or how can you find out the greatest element in this? See, okay, what I mean to say is this one. Let us say I have a tree like this. Less than 15, greater than 15, less than 16. Okay. Now what I wanted to do is, see, the problem is this way. whenever you want to delete the node 15, you are supposed to find out either the in-order predecessor. In-order predecessor means the least value in the left, the greatest, in-order predecessor means the greatest value in the left subtree, which means this one, or you are supposed to find out the in-order successor. In-order successor means the greatest value in the right sub, the least value in the right subtree, which means this one, right? So now given any pointer to a node, right, how can you find out the smallest element in the subtree, right, or largest element in the subtree? Given any pointer to a root of the subtree, how can you find out either the smallest element in that subtree or greatest element in the subtree? Now that is the main problem, right? Let us say if I have here 40 and I have here 60, right? So now let's generalize this. So if you can write a function in such a way that given any pointer to the root of a subtree or a tree, if you can find out the greatest element or the smallest element in that particular binary search tree rooted at that pointer, right, then that can be extended to find out any question like this. Okay, so now what I wanted to do is, given pointer to this one, I want you to find out what is the least element in the binary search tree or what is the greatest element in the binary search tree. Let's now find out the least element in the binary search tree. Why? Because once you find out the least element in the binary search tree rooted at this point, I mean if I give you this point, this pointer, then you can find out the least element if I give you this pointer, right? Which means if the function is going to work, if the header pointer is given to this, then the function will also work if the head, if the pointer is starting at this point, isn't it? So now let's try to solve any of this. Now what I want to do is, given the pointer to this node, the root node, I want you to find the least element in the binary search tree. For that I want you to write a function. Now what are the properties that you would like to see in the least element? So whenever you have the binary search tree, right, the least element will be to the left of it. Therefore I come down to the left, and again the least element will be to the left of this, and again the least element will be left of this, again the least element will be the left of this. In case if it doesn't have any left, then definitely it is the least element, right? So given any pointer to the root, I keep traversing down to the left side, and if I can't go any longer, then that particular node is the least one, right? So in this case I keep on traversing to the left, to the left, to the left, until I find a node in which the left pointer is null, right? So finally the least element will have the left pointer as null, right? All the other elements will not have, will have the left pointer some point into something, isn't it? The left pointer here will be pointing to this. Got it? So now how can you write the iterative function? Now let us say the function is find in order predecessor, right, of, you are given a node pointer t, struct node star t, which means you are given a pointer t, and now you are supposed to find out what is the least element in the subtree pointed by t. Either that subtree could be this, the entire tree, or the subtree could be this, right, or the subtree could be this, starting with this, right? Whatever it is, I wanted to find the least element in that subtree. Okay, now the least element will not have the left pointer, isn't it? Therefore what I will write is while t left. So what does it mean? As long as t left is not equal to null, right? So if I write like this, while t left, it means that as long as t left is not equal to null, which means t left is pointing to something, then you keep traveling left side, right? T equal to t left. So what is the meaning of it? As long as you are pointing to something in the left, or your node is having some left side children, you keep going down. And when are you going to stop it? So you are going to stop it whenever you don't have any left child, right? Which means if you are calling on this, now the left is not equal to null, isn't it? T left is not equal to null. Therefore if you start from here, your t will go here, right? T equal to t of left, and again t of left is not equal to null, therefore you will go here, right? And again t of left is not equal to null, you will go here, right? And finally, since t of left is equal to null, you are going to stop here. Got it? So this function can be used to find out the in-order predecessor, or you can say find out the min in this subtree, right? So it can be used like this: find min. And you can if you want to use this function in order to find out the in-order predecessor while you are deleting the node, then what you do is you go to the right, you are going to find the in-order successor using this. Okay, so you go to the right. If you want to delete 15, you pass to this function the node to the right of it. Then when you pass this pointer, this function is going to find out the least element in this subtree. Then once you find out the least element in this subtree, you can swap it. Got it? So that is how this works, right? So next one is, let's say I want to find out the maximum element of the tree. Then find max. I have to find the maximum. So what is that the maximum element will have? So when you are seeing this, in order to find out the maximum element from here, you go to the right, because maximum element will be present in the right subtree, right? Then again you go right, again you go right. Now you keep on going right until it is possible, and you are going to stop when it is not possible. So how do you know that the right subtree, the right pointer of the greatest element will be null, right? Then how can I find it? Oh, this is find min, right? This is find min function. Okay, now I want to find max. So don't by heart them. See, using your intuition you can write them. So what I mean to say is, don't by heart all these functions. If you have to by heart all these functions, there will be hundreds of functions you might have to by heart. So just use your logic, intuition, and with these practice questions, with these many questions which we practice, it will be easy. Okay. Now find max, which means you have to go right, and you are supposed to find this. So you will be given a pointer struct node star t, and you are supposed to find max of this, right? And before this you had to even check whether it is null or not, right? So sometimes if t might be null, right, in that case you had to even check this. If t equal to null, return. You had to keep that checking condition also in place. Anyway, let's look at the main logic here. So while, what should I do? As long as I could go right, right? How can I know whether I could go right or not? The t of right will be not null. As long as t of right is not null, you keep on moving right. So what is it? T equal to t right. Okay. This is how you could apply the logic. Now what happens? Initially, if t is pointed here, if t of the right is not equal to null, we go to the t right, which means t equal to t right means we will be here. And again we go right, t equal to t of right means here, right? And again we go right. And from here t of right is not is null, therefore this one will be broken, and we stop here, right? So we will stop whenever we find the maximum element. Now how could you use this function in deleting an element is, you can go to the left subtree and find out the max. That is also called as in-order predecessor, right? So find max can be substituted in the place of in-order predecessor, finding in-order predecessor given the appropriate pointer, and find min can be substituted for in-order successor, which means give it to the pointer to the right subtree, right? Then it is going to find out the in-order successor, and give it the pointer to the left subtree, and it is going to find out the in-order predecessor. Okay, that is how I could use this. The main intention of binary search tree, the building binary search tree is to make the searching efficient. If you put all the nodes or all the elements in a linked list, then the problem is search time may be as big as order of n, right? So in order to reduce this search time, we are going to use the tree. So we thought that just by using binary search tree, this search time will decrease, and in many of the cases it is going to decrease, most of the cases. But then the problem is, sometimes the input sequence might be in such a way that even though it is a tree, it might look like a linked list, and therefore the search time will be again order of n. The main intention of binary search tree is to decrease the search time from order of n, and in most of the cases it is true, it is going to decrease, right? I'll tell you some examples in which a binary search tree will look exactly like a linked list, and the time complexity is going to be very, very high. Let's say this. Let us say I have a binary search tree and I want to insert into the binary search tree the elements like this: 1, 2, 3, 4, 5, 6, so on, right? Then first 1 will be inserted, and when 2 has to be inserted, it will be inserted in the right? And when 3 has to be inserted, 3 is greater than this, and it will be inserted here. And when 4 has to be inserted, 4 will be inserted here, right? 5 will be inserted here, right? So on, right? Now if you look at it, even though it is a tree, it is looking like a linked list, isn't it? Now in order to reach any node, we have to traverse the entire list, which is going to make the time taken to search a node is going to be order of n, even for insertion. Right? So if the insertion is in this sequence, so time complexity for this searching is order of n, right? But then what is the advantage of using a tree? If it is going to be exactly like a list, then there is no use of using the tree, isn't it? Therefore what people thought is, let's rebalance it. So whenever we insert a node into a tree, then it is going to become skewed means it is going to grow on only one side, right? Or it is going to be imbalanced, right? Then what people trying to do is they'll trying to balance it. So for that reason, there are various balanced binary search trees proposed. So one such popular tree is AVL tree. AVL, okay? So AVL tree means it is named after 3 Russian scientists who discovered it. So AVL tree is the algorithm. AVL tree is a balanced binary search tree in which if you have n nodes, the height of the tree will be always order of log n. That is what is balanced binary search tree mean. So what is the main difference between binary search tree and balanced binary search tree? Every balanced binary search tree is also a binary search tree, but then the order of height or the height of the balanced binary search tree will always be order of log n. But in case of ordinary binary search tree, if it is not balanced, then the height could be as big as order of n, right? And when the height is order of n, then the search time is also going to be order of n. If the height is order of log n, then the search time is going to come down to order of log n, right? So AVL is one example of balanced binary search tree. Like this, we have red-black trees, and we have 2-3 trees, right? And we have Fibonacci heaps and many things, right? But then these are all the data structures which are generally used to help us in searching the data very fast, right, in log n time. And AVL is the most popular method. So let's talk about AVL now, okay? So what does AVL say is, AVL is based on something called as balance factor. So balance factor of a node is like this. If a node is here and if it is having some left subtree, right, and if it is having some right subtree, left subtree and right subtree, then balance factor of this node is generally taken like this: height of left subtree minus height of right subtree. So we find the height of left subtree, and from that we decrease the height of right subtree. So in case if the balance factor of this node is either -1 or 0 or 1, then these three are allowed in AVL trees. Anything other than this, which means whenever any balance factor of the node reaches -2 or 2, it means that the tree is going to be unbalanced. Then in this case we are going to balance it, okay? So how are we going to balance it is, I'll take examples and explain you how to balance it and all this. I'll just show you. See, now assume that we are going to insert nodes like this: 1, 2, 3, and it is inserted like this: 1, here is 3, and here is 2. What is the balance factor of this? Leaf is 0, right? Now what about the balance factor of this? Height of left subtree minus height of right subtree, which is 0 minus 0, so it is 0. So it is valid, no problem with this, right? And now assume that 1, 2 and 3, okay? So now let's define the height of the subtree like this. In order to define this height, okay, in this problem let's define the height this way: height of the leaf is 1, let's start from there. Height of the leaf is 1. Okay, let's do it that way. So height of the leaf is 1, then the height of this one is 2. Okay, for this problem, see, for every problem they are going to define what the height is. So for this problem I am defining the height to be starting from 1. So most of the problems they define the height to be starting from 0. That is fine, but you know, here I want the height to be defined this way. Height of a node, of a leaf node, is 1, and the next one is 2, and next one is 3, like that. Okay, the reason is you'll understand it now. Okay, now let us say 3 is the root, 2 is left, and 1 is left. So this is the binary search tree. Now let's see what is the balance factor of this. So balance factor of this is 0 because there is no left child, no right child. What about the balance factor of this? Height of the left subtree minus height of the right subtree. What is the height of the left subtree? It is 1, minus height of the right subtree is no right subtree, therefore 0. So balance factor of this node is 1. What about the balance factor of this? Height of the left subtree minus height of the right subtree. What is the height of the left subtree? You know, this one, height of this one is 1, and height of this one is 2. Therefore height of the left subtree is 2, and minus height of right subtree is 0. Therefore height of balance factor of this one is 2, this one is 1, and this one is 0. Now if you observe it, the balance factor of this node, this particular node, is not 0 or 1 or minus 1. Therefore if it is not these three numbers, we are supposed to balance it. So it is called as L imbalance, right? Left imbalance. So whenever we have LL imbalance, we try to rotate it clockwise. That is called as rotation. Alright, so whenever we have LL imbalance, then we are going to rotate it, right? Rotate it clockwise. So when I rotate it clockwise, right, by having 2 as the center, see, how do you know that 2 should be the center? With practice you will be able to understand it. I'll do a lot of practice questions here. Okay, now hold this and tilt it. Then what happens? 2 will become the root, and 1 will become the left child, and 3 will become the right child, right? That is called balancing. Now you check it. The balance factor of this is 0, and the balance factor of this is 0. Why? 1 minus 1 is 0. Got it? So this is how you settle down the unbalanced nodes. Now whenever you try to insert a node, we are always going to see that the nodes which are going to be inserted into the tree are always balanced, which means after every insertion we are going to check if the nodes are imbalanced, right? In case if they are not balanced, then we are going to balance them. That is how AVL insertions work. In any balanced binary search tree, how is it different from binary search tree is, in binary search tree we simply insert and leave there. But in case of balanced binary search tree, after every insertion we are going to check whether there is a imbalance there. Alright, in case of any imbalance, then we are going to balance it and then leave it. Okay, so insertion in binary search tree, balanced binary search tree, is insertion plus balancing. Okay, now this is one way of imbalance. Let's see if there is any other way of imbalance. Let us say 1 is inserted, and then 2 is inserted, and now 3 is inserted. Okay, so after inserting the last element, we are supposed to traverse from that last element till the root. On the way we should check if there is any imbalance, right? So how do you check for imbalancing? After inserting an element, you start from that newly inserted node towards the root node. On the way you see if there is any imbalance. In case of any imbalance, you are supposed to level it out. Okay, now what about the balance factor of this? It is 0. Why? Left side, right side, there is nothing. What about the balance factor of this? Left side, there is nothing, therefore height of the left subtree is 0. And what about the height of the right subtree? I told you that leaf is at height 1, right? Then 0 minus 1 is minus 1. Then what about this one? Left side there is nothing, right side there are 2. Therefore 0 minus 2 is minus 2, right? Now again there is a balance, right? So imbalance here. So in order to balance it, you have to tilt it anti-clockwise. Got it? So how do you know which way to tilt? With experience you will be able to understand it, or you can by heart this, right? So it is called as RR imbalance, right? And in order to level RR imbalance, you are supposed to tilt it left side. Okay, now I am going to rotate it. I am going to rotate it like this. So it is anti-clockwise, right? I am going to rotate it this way. Then what do we get? 2, 1, 3. See, after doing practice, you will not need to by heart it. You will understand it and you will be able to do it fast. Don't worry about it. Initially, it might be difficult. So, balance factor of this is 0, this is 0, and what about this? This one is 0. So, it is balanced. Now, one other kind of imbalance may be like this. Let us say an element is inserted like this 3, and then an element is inserted like this 2, and then an element is inserted like this 1, right? So now what happened? See, the order in which I inserted the elements is 3 is inserted first, and then 2 is inserted next, and then 1, right? Why should I insert in only this way? Graham's law, right? If something is possible, it will definitely be. Therefore, I have to definitely handle all the cases, right? Now, watch it. So, what about the balance factor of this? 0. What about the balance factor of this? Height of the left subtree is 1, right subtree is 0. Therefore, 1 minus 0 is 1. What about the balance factor of this? Left subtree is 0, right subtree is 2. Therefore, it is minus 2. Again, there is an imbalance, right? So, what kind of imbalance is it? It is right left imbalance. How to find it out? See, after inserting any element, newly added element, you have to travel from that newly added node towards the leaf, towards the root, and on the way you should check every node for imbalancing, right? If you find any imbalance, then you have to balance out there, right? So now, how do I know that it is right left imbalance? Because from the node where we got the first imbalance, again you try to travel towards the newly added node. So it is saying you have to go to the right and then left. That is why it is oral imbalance. So whenever you have oral imbalance, you are supposed to do 2 rotations. Okay, one rotation is clockwise. Rotate clockwise, right? So if I rotate clockwise, I have to hold this and rotate it like this, tilt it like this. Then what I get is 3 here, and I'm holding it and tilting it like this, 1 here and 2 here, right? Now what is it? It is RR imbalance, right? Now again, this is also not balanced, so one more time I have to rotate it. So now rotate it anti-clockwise. Now if I rotate it anti-clockwise, I have to hold this and rotate it this way. Then what do I get? Oh, this is actually I went wrong here, sorry. So it has to be 1, and it has to be 3, and it has to be 2. Okay, now it will make sense. It has to be 1, and it has to be 2, and it has to be 3. I got involved in the algorithm that I forgot to see whether the tree is a binary search tree or not. Sorry for that. Okay, and now you have to do it again clockwise. So again I have to do it anti-clockwise. Then what do I get? 2 here, 1 here, and 3 here. Got it? So now, after doing everything, you should check the balance factors, and also you should check that the resulting tree is again binary search tree. See this? Is the resulting tree binary search tree? Yes. Why? It is less and it is greater. Is it binary search tree? Yes. Less, greater. Is it binary search tree? Yes. So after inserting any element, you are supposed to even check, after balancing out, you are supposed to check the balance factors. Yes, they are zeros, but along with that, if you did everything right, then the result will also be a binary search tree. In case if the result didn't turn out to be a binary search tree, then you should understand that you did something wrong there. Okay. Now let's see one more type of imbalancing. Now let us say initially I inserted the node 3, and then I inserted node 1, and then I inserted 2. Where will I insert 2? 2 is less than this and greater than this, which means 2 will be falling here, right? Now let's see the balance factors. So what about whenever you insert any new node, you should check for every node. But then since I know that it is not an imbalance, I didn't check it. But in general, you should check whenever you insert any node. From that node, you should go till the root. Now from here, the balance factor of this one is 0. The balance factor of this one is 0 minus 1, which is minus 1. Why? Left subtree is 0, right subtree height is 1. That is why minus 1. What about the balance factor of this? Height of left subtree. Height of left subtree is 2, and the right subtree is 0. Therefore, the balance factor is 2. So I have to balance it. Now, what type of imbalance is it? So in order to find out what type of imbalance it is, you have to travel from the imbalanced node to the newly inserted node. So this is the imbalanced node, and I have to go from here to the newly added node. So how can I reach there? L R, right? Therefore it is LR imbalance, right? Now what do we do in LR imbalance is, we have to again see either it is RL or LR. I have to do two rotations. In case of RR and LL, only one rotation is enough, right? So now I have to do here two rotations. So one rotation is, I have to hold it and turn it anti-clockwise. So initially I have to rotate anti-clockwise. Okay, so I'm going to hold it and rotate it this way. Then what happens? 3 will be here, 2 will be here, and 1 will be here. Are you understanding it? I'll hold this and rotate it this way. Don't worry, with practice it will be easy. I'm holding this and rotating it anti-clockwise, which means this one will come like this, this one will come like this, 2 will come here and 1 will come here, right? Then what is it? It is LL imbalance. Now we know how to level out LL imbalance. We have to rotate it clockwise, right? So again I'm going to rotate it clockwise. So if I rotate it clockwise, I can hold it like this and pull it down, which means 2 will be here, 3 will be here, and 1 will be here. Balance factor is 0, 0, 0. That is how we balanced out. Got it? See, one thing here, after rotations, we got all the balance factors to be zeros. But even if you don't get all the balance factors to be zeros, even if you get them to be 1 or -1, it is okay. You can leave it there. But only thing is 2 is not allowed. As long as we have a node with 2, we keep on rotating. Right? So a few things that you should observe is, whenever I insert any node, only one node is going to be imbalanced, and once you balance it out, it is enough, right? And after inserting a node, you should always travel from the newly inserted node towards the root to see on the path if there is any imbalance. If there is any imbalance, you are supposed to level it out. How? Start from that imbalanced node and then start going towards the newly added node. Then you will understand what type of imbalance it is. Either it is LL or RR or RL or like this. Okay, and then you could rotate them according to your wish, and you will get the answer, right? So let's now practice some questions about how to do this balancing. Okay, we have seen some abstract binary trees, in case of abstract syntax trees, in case of compiler design, if you remember them, right? So there are two types of parse trees. One is abstract and other is concrete. So normal parse trees are also called as concrete syntax trees, and there is something called as abstract syntax trees. I'll just show you what I mean by that. And these trees have got some significance when we are trying to travel or do some traversal on them. For example, if I have A plus B, right, the tree can be written like this, the syntax tree. This is also called as expression tree because we are writing the expression in form of a tree, isn't it? Mathematical expression is written like a tree. Now this has got some significance in terms of traversals, in the sense, if you try to do let's see in order, pre-order and post-order traversal of this tree. I want to see in order, pre-order and post-order, right? So what is pre-order? First time visiting, right? So first time when you visit, write it plus first time, A, second time, A, third time, A, second time, plus first time, B, second time, B, third time, B, third time, plus, right? So if you see this on the expression tree, if you perform in order pre-order traversal, it is going to give you prefix expression. If you perform in order traversal, it is going to give you infix expression. And if you do a post-order traversal, then it is going to give you a postfix expression. That is the significance of it. Okay, understood this? Maybe we can do one more example. Let us say I have A plus B into C. Now what is the expression tree for this? Now which one has got highest precedence? Star. So first you had to execute B into C, and then you have to add A to this, right? Then let's see what is pre-order, in order and post order for this. Okay, now pre-order is first time, so first time, second time, third time, second time, first time, first time, second time, second time, first time, second time, third time, third time. Okay, here B has been visited third time, right? So I missed it out, right? So third time plus, got it? So this is the prefix expression and this is the infix expression and it is the postfix expression, got it? So only thing you should be careful is about is with unary operators. With unary operators, when you try to write the this expression tree, just see that the traversal, the infix traversal gives whatever you wanted. For example, if I have minus a unary expression, right? So definitely operator has to be at the root. Should the operand be here or should the operand be here? That is what I don't know, right? So should I put it here or here? So if you want to decide it, try with both of them and then see which one the infix is giving you the actual answer. So if you travel in infix, you are supposed to get minus a. So what is infix? Second time, right? So first time, second time, which means a will be printed first, therefore, and then second time, right? Therefore it is not the infix expression which we required. So this might not be the actual one. So actual one must be like this, isn't it? Why? Now see, I'm just trying it, that's it. Now if I see first time, no, second time, print it, first time, no, second time, print it. Therefore infix expression is going to give me minus a. Therefore this must be the expression tree representation of this expression. If you have any doubt, you have to see the infix, the in-order traversal. That in-order traversal should match up with the given expression. For example, if you have a factorial, right, you know that factorial has to be always, operator has to be at the root, I mean at a higher level compared to the operands. Now I don't know whether I should put it here, a here, or I don't know whether I should put a here. So I don't know where to put a. Then what I'll try to do is I'll try to traverse it. So first time, no, first time, no, second time, yes, so a is printed, third time, second time, a factorial. Therefore a factorial is printed whenever I visit second time, and this must be the actual tree for this expression, got it? Let us say you have log. So now log a. Now log a is similar to minus a. So where should I put? So log should be here, right? And a should be here, got it? What if I have log a factorial, right? Now you can combine these two. So first I have to apply a factorial. A factorial is having higher precedence, right? So a factorial means it is kind of this, right? Therefore you have to write like this, factorial and then a. This is going to give you a factorial and then log a, which means you can consider this entire thing to be log a. You can consider this entire thing to be x. Then it is as good as writing log x. Then what should we do? Log should be at the root, right? Isn't it? And a should be in the left. Yeah. Log should be at the root like this. Log factorial a. Is it? I think minus a, this one is right. Okay. A factorial, this one is right. Okay. And log a, I think this is log a has to be this one, right? See again, log a is, this one is not right, I feel. Log a, this one is right, because it is similar to minus a, right? So just check this. First time don't print, yes. Second time log, yes. First time don't print, second time a. So this is log a. Therefore a factorial is this. First if I have log a factorial, I should find out a factorial. So let me put a factorial like this. So which means factorial here and a here. This is a factorial. Got it? Now after putting this a factorial, I should apply log. So log a is like this, right? So if I have log x, then whatever you want to apply log, that should be as the right subtree. Now I want to apply the log a factorial, right? So this entire thing should be the right subtree to log. Log here and here, right? So now you try to traverse it in order, and you are supposed to get log a factorial. Watch it. First time, second time, therefore log will be printed. First time, second time, therefore a will be printed. Third time, second time, therefore factorial will be printed. Log a factorial. Got it? So if you don't know how to put this unary operators, you try with all possibilities and see that in order is supposed to give you that particular tree, and always see that operators are present at a higher level compared to operands. Operands should be present at the leaves, and operators should be internal nodes. So once you have internal node as the operator, then you don't know whether to put it here or here. That depends on the traversal. Try to traverse it in order and find out whether it should be present here or here. Got it? And when you have a combination of operators, then you build it step by step. For example, here if you have log a factorial, you know that a factorial has to be executed first. That is why you construct the tree for a factorial, and then you try to apply log as if this entire a factorial is x, right? So now you construct this for a factorial. Now this is what I got. Now act as if this is a single node, and you try to apply log to that. This is what we got. Okay, fine. There are various ways to represent the trees. One popular way which we have seen is the structure representation. Every node is represented by a structure, and there are pointers which are pointing to the other nodes, right? That is the most popular representation, which means you have already seen like this. If I have a tree, the root is represented like this, right? And then the left child and right child, isn't it? So this way of representation works well for the binary trees, but there is a problem with this representation. Sometimes what happens is, the tree might not be binary, in the sense the number of children might be more than 2. Let us say the number of children is as big as 10. So the number of children is more than 2, and moreover all the nodes might not have all the 10 children. So declaring or having 10 pointers in every node is actually a waste of space, isn't it? See, in this case it is fine, but I am saying that in some cases what happens is, in some trees the children can be not 2, it can be 10. In that case, it is representing it 10 pointers inside one node is actually waste of space, given that all the nodes might not use up all the space even though you are declaring it, right? In that case, the best thing to do is, there is one more representation called as left child right sibling representation. Left child right sibling. So what is left child right sibling is, if you have a child, a tree like this, 4 children there, and then 3 children, and then 2 children like this, then instead of having 4 pointers in one node, every node will have only 2 pointers. One pointer will point to the leftmost child, and the other pointer will point to the right sibling. For example, the root is having 4 children, right? Then one of the pointer of the root will point to the leftmost child, and even every node will have right sibling, right? So right sibling pointer, right sibling pointer, right sibling pointer. Therefore, just by pointing to this child, it can get all the children, right? How? It is having the right children pointer, right? Now the right child pointer of the root node, and the right sibling pointer of the root node, and the right sibling pointer of the rightmost sibling will be null. Why? Because they don't have any right sibling there, right? And the same representation is used for this also. So this node has pointed what its right sibling is, and it will even say what its left child is, which means this one. It will point to this, and that left child will point to its right siblings, right? This is the right sibling, and this one's right sibling is this one, right? So that is how everything is represented. If it is also having some child, it is also going to represent like this, right? This is called as leftmost child right sibling representation, which is used to save the pointers. So it is going to be useful for not for binary trees. See, anyway for binary trees we need only 2 pointers, right? But if you have more than 2 children, which means if you have 10 children, 20 children like that in your trees, then it is going to be very, very useful, this representation, right? It is commonly used to represent arbitrary trees like 10 children, 20 children like that. It is not used for binary trees where we have only at most 2 children, right? And the other representation is Array representation. Array representation of binary trees is quite popular. I'm talking about binary trees, okay? So coming to binary trees, one more representation, popular representation is array representation. So what we do is, if we have a tree like this, right, let us say the nodes are A, B, C, D, E, like this, then we represent all the nodes in an array in such a way that searching for a particular element is easy. Searching for a particular element in the sense, searching for what is the left child, what is the right child, what is the parent. Such kind of searchings can be done easily if I represent it like this. So how is it possible is, watch it. Now we place the root in the first index. Let us say this array is represented by some A, then this one is going to be placed in A of 1, right, and left child is going to be placed in 2, and it is going to be placed in 3. So how does it work is, if a node is at index I, then its left child is going to be at the index 2i, and the right child is going to be index 2i plus 1. So what is the advantage of using this 2i and 2i plus 1 representation is, multiplying with 2 in a binary system is nothing but left shifting the number by 1, which means if I have the number 1 0, what is the value of it? It is 2, right? Multiply with 2, which is nothing but 4. So multiplying by 2 is nothing but left shifting it by 1. So 2i computing is straightforward, just left shift it, you are not multiplying, right? And what about 2i plus 1? 2i plus 1 is left shift it if it is the number. If I want to find 2i plus 1, if this is the I, left shift it and then OR it with 1, then I get this, isn't it? Therefore it is very simple to find out the left child and right child if I use this representation, right? And moreover, finding out the parent, if I have a node x at point x, then parent of the x is simply x by 2, which means if this is the location of a node, then its parent will be present at by 2. By 2 is nothing but right shift by 1. So division is nothing but right shift by 1. Even here also the parent of this one will be right shift by 1. If you right shift it, we get 1 0, right? Which means the least significant bit, either it is 1 or 0, will go away, and the remaining part is going to be the the parent. Got it? So finding out the parent is easy, and finding out the left child and right child is easy using the array. So according to these rules defined, if root is at location 1 like A, then where is the left child? Left child is going to be 2 into 1, which means here, and right child is going to be 2 into 1 plus 1, which means here, right? And again, if 2 is here, then the left child of 2, D, where it will be? 2 into 2 is 4, right? Therefore D is here. And where should we place E? See this, parent is at 2, therefore 2 into 2 plus 1, which means 5. Got it? And where are we going to place F? So parent is at 3, then F will be in 2 into 3, which means 6. And where are you going to place G? G will be in 2 into 3 plus 1, which means 7. Like this we can fill it up. So binary tree, this array representation is going to be useful, especially when we have to go down to our children as well as go up to the parent. See, in this kind of representation we can only go down, right? And going up is not very straightforward. Once you are here, going up is not straightforward unless you have saved the pointer to the parent, right? So here traversing is easy, and that is why it is widely used in the implementation of heaps. And in a heap we might have to go down as well as go up, and moreover it is beneficial for heap because heap is a almost complete binary tree, and it is also almost full binary tree, which means if you look at the order in which you fill up the nodes in the heap, right, we fill up the nodes like this way, right, which means this one will be filled first and then this one. And even if you write the indices, they will be indexed like this only, right? 1 2 3 4 5 6 7 8 9. So next one which has to be inserted will be here, right? Therefore the way in which the indices are growing and the way in which we are performing the inserts are consistent, right? Therefore representing a heap as a array is very beneficial because of the way it is growing, isn't it? You are growing it like this, and even you are inserting it at the corresponding places, right? So representing an array like a binary tree as an array in terms of in place of that in the implementation of heap is beneficial. But the disadvantage coming to this array representation is if the tree is skewed like this, right? So where are you going to place this one? This one will be placed in 1. What about this 2 into 1 plus 1, which means 3? What about this 2 into 3 plus 1, which means 7? What about next one 2 into 7 plus 1, which means 15? Even if I have only 4 elements, the array should contain as many as 15 indices, which means the size of the array is 15. So in worst case, if the entire tree is skewed and if it has got n elements, right, then the size of the array required is going to be 2 power n minus 1. This big array you should require, isn't it? See this? So for 2 power 1 minus 1, which is 1. So for 2 elements, 2 power 2 minus 1, which is 3. For 3 elements, 2 power 3 minus 1. This is the disadvantage. In array representation, as the tree grows skewed, the number of the array size becomes exponential, which means even if I have to store n elements, I might have to have an array as big as 2 power n. This is the worst case. So for all normal trees, using this array representation is not advisable. Only when you know that tree is going to be almost complete like this and it is going to grow in the level order, right? Then it is better that you go with this kind of representation. So especially heaps are perfectly suited for this representation. That is why heaps use array representation of trees, right? And next one is one more representation is there, which is not very popular, but then still it is in use. Sometimes people will use it, but then it is not widely used. They say that if you have A, B, C like this, you can represent it in a nested form. Nested form means you can use a parenthesis to represent every subtree. So they say that you can either write like this B, A, C, and you can say that this one is leftmost child, left child, and this one is root, and this one is right child. Or you can even represent like this. You can represent it as root, left, right, which means this one is root, and this one is left, and this one is right. So whatever way you decide upon, you can represent it using the nested form, right? Let's see an example how to represent in nested form a tree. So one representation of nested form is if I have A, B, C, D, E, F, G. Let us say I want to represent it in nested form in the form of root, left, right. Okay. Now what is the root? A is the root. Fine. What is the left? Left is a subtree, right is a subtree. Therefore left is a subtree and right is a subtree. Now let's go into left subtree. What is the root? B. Then what is the left of it? D. And what is the right of it? E. Right. What about this one? Root is C. What is the left of it? F. What is the right of it? G. Got it? So this is how we can use the nested representation. So we have mainly 4 representations. One is the normal representation where we use the 2 pointers to represent left child and right child in case of binary trees, right? Normal representation using structures, right? Pointers. Using pointers and structures, right? And this second one is also using pointers and structures, which is going to use left child, right sibling representation, right? And this is used for not for binary trees if the number of children are very high, which means generally for n-ary trees where n is very high, n is very high compared to 2, then we are going to use left child, right sibling method. Here also we use pointers and structures. And the third representation of the tree is array representation, and array representation is very useful in case of heaps, right? And it is very useful whenever your application contains almost complete binary trees or almost full binary trees. Okay, so if the binary tree is containing lots of nodes, then you go for it. In case if your tree is going to be skewed, then this representation is not very useful. And the next one is this nested representation, whatever I shown you. It is not widely popular. Okay, These are all the various representations, and you can choose the representation depending on your algorithm. So if your algorithm requires what kind of data, depending on that you can choose one of them, whichever gives you better performance. Got it? Okay. Graphs and graph theory have been of great interest for computer science students as well as the researchers in the recent past. See, earlier graph theory was not considered a part of computer science. It was completely not all studied by computer science engineers or anyone from computer science. They have been kept aside. But then with the advent of internet, right, since 1980s, there has been a great interest in this area, especially by people from computer science. The first, the one thing is, with the advent of this internet, what happened is they represented the entire World Wide Web as a graph, right? So every web page is now a node, and if there is a link from one web page to the other web page, then that is an edge. Therefore, entire World Wide Web can now be modeled as a graph, and we are interested in knowing various properties of these graphs, exploring various properties. Based on this, search is going to be relevant, and search times and everything can be improved, right? And moreover, with the advent of these social networks, especially this Facebook and other social networking sites, what happened is they started representing this entire social network also as a graph. If you are a person, you are a node in a graph, right? And if you are having your friends, right, all your friends are also nodes in the graph, and you will have a link like this. See, I'll just show you what I mean to say is this. See, generally a graph is represented like a set of vertices and the set of edges, isn't it? A graph is represented like a set of vertices and edges, right? Now, there are various applications of graphs. One is in the World Wide Web, where every node is a web page, and if there is a link between from one web page to the other web page, then we can represent it as an edge, right? So, and then in social networks, what is happening is, if you are a person in a if you are having a profile in the networking site, social network site, then your profile will be represented as a node in the graph. Excuse me. Which means, let us say you are here, this is you, and all your friends in the networking site are going to be the nodes in the network, in the graph, and there will be a edge between you and your friends. Which means, if you are friend with, let us say, A, B, C, D, right, then you are having edges between you and all of them, right? And you are not a friend with, let us say, E, F, right, and you don't have an edge. Got it? So, and if he is friends with someone, right, then they will have this edge, right? And now there are various properties you might want to see. For example, in Facebook, you might see this friend suggestions. They might show you, this person might be your friend, right? So how is that possible? They will do some traversals. So there is, till now we have seen some traversals, in like pre-order, in order, post order, in that particular trees, right? So while coming to trees, the main difference between a tree and a graph is, in tree it is connected, which means from one particular node you will be able to reach all other nodes. But in graph, it may not be connected, right? Then what happens is, in tree, if you start walking from one node, you will be able to reach all the other nodes. That is why it is called as traversal. Traversal means you will be able to get to every node possible, and such a kind of traversal might not be always possible on a graph. The reason is, if you start from one node, there is no guarantee that you will be able to reach all the other nodes in the graph, because the graph may not be connected. So which means this will be one component, and you might have some other component in the graph, right? And these two components might not be connected. So if you start from a node here, you will be able to reach all the nodes which are connected to this, but you will never be able to reach these nodes, right? In such case, it is called as search, right? So traversal techniques mean that we want to visit every node, that is traversal. Search techniques mean that we may not be able to visit every node, therefore we are interested in visiting only the nodes which are reachable. And using this search, we can implement traversal. How? Once we start searching from one particular node, we'll visit all the nodes which can be reached from this, and then out of the remaining nodes which are not yet visited, again we'll start this search. Got it? So traversal means visiting everything. Search means visiting only the nodes which are reachable from some particular node if you are starting this search from that particular node. Okay? And why am I talking about this traversal and searching is the most important problems on the graph are all about traversals and search. See, now the information is present in the graph and now we have to get that information out. So how do we read the information? Just by traversing or searching, isn't it? And let's go back to that Facebook problem. Let us say in Facebook you are going to have this problem as your friend suggestion. So is he your friend? Is she your friend? They'll ask you these questions, right? Now how is that done? Now watch it. See, if you are here, all your friends are nothing but the nodes which are adjacent to you. What is adjacency is, if there is an edge between you and between one node and the other node, then these two nodes are said to be adjacent, right? For example, let's say this node is R. Okay. Now what is the adjacency? What are the nodes which are adjacent to R? All the nodes which are adjacent to R are nothing but, one is D, other is C, other is B, other is A, right? These are all the nodes which are adjacent to R. Therefore, if I represent every profile as a node in the social network, then what is the friend list? Friend list is nothing but the adjacency list. So adjacency list in a graph is equal to friend list in the Facebook. Got it? And now see, if you are standing here, then there is a probability that you may know a person whom your friend might know, right? Therefore, we start from a particular node and we try to search. So how do we search is, we search in a breadth first manner. Breadth first manner means we search for all the elements which are at a distance 1, right, first. These are nothing but all your friends. And then we search for all elements which are at distance 2 from you. So what can you say about the nodes which are at distance 2 from you? They are they are friends of your friends, isn't it? See, if a node is at distance 2, then definitely you have to go through a node which is at distance 1, right? Now if this node is at distance 2 from you, you have to go through your friend, isn't it? Therefore he is a friend of your friend. Therefore all the vertices which are at distance 2, isn't it? This one, and in fact if we have someone here, right, all these vertices, right, in fact if you have someone here, these are all friends of your friends. Got it? Therefore when we search it this way, breadth wise, which means we search for all the elements who are at distance 1 and then we search for all the elements who are at distance 2, then you are going to get friends of your friends, isn't it? Now the chances are that if a person is a friend of your friend, then you might be knowing him, right? Therefore they are going to use a search, breadth first search, exactly not breadth first search. They are even going to do some modifications, like if a person is going to be in mutual friend list of many, for example, if this person knows him and this person knows him, then the chances that this person this person is going to be high rather than this person. If there is if he is only a friend of one person, right, he might not be a well-known person to you compared to this person. So they are going to modify it anyway. But then if you apply breadth first search, I'm just giving an example of an application. If you apply breadth first search, if you start from a node here, right, and if you try exploring your friends and then friends of your friends and then friends of your friends like that, then you might get people whom you might know. So that is how Facebook will give you the suggestions, a modified version of this. Now what about depth first search? Depth first search says that you go as deep as possible, as far as possible, and now you find the value, some person there. Then what does it mean? If you apply the depth first search here, then how does it work is, first your friend will be explored and then his friend will be explored. In case if he is having any friends, he will keep on explore, right? Now it will go and stop at somewhere in US. If you are in India, right, it might stop at some person in the US and you might not know him at all. Therefore depth first search fails here, right? But then both breadth first search and depth first search are equally popular and there are various applications for both of them, right? So these two such techniques have to be discussed. And before discussing about any of the algorithms like search or traversal, we should discuss about the data structures which are used to represent the graphs. Okay, so there are various ways to represent the graphs. We shall see the graph representations and then these algorithms. Okay. There are two popular representations of graphs. I'll show you both of them. Just watch it. See, let us say a graph is like this. We have four nodes. Okay, A, B, C, D. So generally what we do is we number them with some indices, which means we assume that A is 1, B is 2, C is 3, D is 4, like that, and then we go ahead. But then to make the thing simple, I'll just have the names themselves and I'll show you the representation, and the conversion is very straightforward. Okay, so now what I mean to say is we want to represent this graph. Obviously we are not going to draw this diagram and store it in the computer and then use paint or something to store it, right? We have to represent it in some other representation in terms of some data structure, right? So one popular representation is like adjacency matrix, right? It is called as adjacency matrix. So what is adjacency matrix is, I'm going to have number of rows and number of columns equal to the number of nodes, which means every node is going to have a row and a column. For example, since there are four nodes, I'm going to have four rows, each one dedicated for one node, and four columns, each one dedicated for one node, right? For example, A, B, C, D. A, B, C, D, right? Now what about A to A? A to A there is no edge, right? What about A to B? There is an edge, right? What about A to C? There is no edge. What about A to D? There is an edge, right? What about B to A? Yes, there is an edge. What about B to B? No edge. B to C? There is an edge. B to D? No edge. What about C to A? C to A? No edge. What about C to B? Edge. What about C to C? No edge. What about C to D? Edge. What about D to A? Edge. D to B? No edge. D to C? Edge. D to D? No edge, right? So this is how we can represent it. In case if it is a weighted graph, which means if the graph is having some weights, then we are going to represent even weights there, right? This is one popular representation, and the other popular representation is having a linked list. So we can have an array of pointers, and this array will contain the number of elements which are equal to the number of nodes there, and each element will be corresponding to one node. If I have four nodes, then I have an array of four pointers, right? And now each pointer is going to point to a linked list. So this linked list will contain set of all nodes which A is adjacent to. Now what about the A is adjacent to B, right? A is adjacent to B and A is adjacent to D. Got it? It is a linked list. And what about this? B is adjacent to A and B is adjacent to C, right? What about C? C is adjacent to A and C is adjacent to D. What about D? D is adjacent to A, D is adjacent to A and D is adjacent to C. Got it? So this is a linked list representation of the graph, right? So we can even either represent the graph as this adjacency matrix or the linked list representation. Now which one to use? What really makes sense? That depends on the type of the graph. If the graph is dense means if the number of edges are very high, right, then it is better that you go with the matrix, right? So which means for the dense graphs, so let's define the density now. So dense graphs means if the order of edges, if the number of edges in a graph is equal to order of vertices, which means if the graph is almost complete, I'm not saying that it is complete, but if the graph is almost complete, right? If the number of edges is equal to order of v square, then in this case it is better that you go for adjacency matrix, because we are going to use up most of the cells, right? So otherwise, if it is sparse graphs means if the order of edges is equal to order of vertices, which means if I have very few edges, then having this big matrix and then having only ones here and there and completely zeros is a waste of space, right? So in case if the graph is sparse, you go with adjacency list, right? In case if the graph is dense, go with adjacency matrix. For example, in Facebook, right, I told you that everyone is going to be represented as a node, and now your friend list is nothing but the adjacency list. Now in that representation, should I represent the entire Facebook as a adjacency matrix or adjacency graph, adjacency list? Which one makes sense? Adjacency list makes sense because a person is not going to be a friend to everyone, right? There are nearly 6 million users. I don't know exactly how many number recently, but there are millions of users in the Facebook, right? I don't know exactly how many million. So with these, these many million vertices are there, but how many edges are there? Which means how many people really know all others, right? Or how many people is one person adjacent to, is one person friend to, right? They are having a limitation that 5,000, isn't it? So a person cannot have more than 5,000 friends, right? Then in that case, if deciding or dedicating a matrix, see, let us say there are few millions, right? So if I have to represent the entire Facebook as a adjacency matrix, then what happens is I need to have the graph as big as million by million dimensions, right? And out, which means every node will get million entries here, right? But then if you see their limitation, they are limiting the number of friends that a person can have to only 5,000 members, right? Which means out of this 1 million entries given to you, you will be using only 5,000 ones, isn't it? And all the remaining are going to be zeros. Out of few million entries you are given, you are going to use only 5,000 and remaining are all going to be zeros, right? And many people are not even going to use 5,000 members, right? Most of the people will have only 100 or 200 friends or 300 odd, right? But 5,000 is a very big number. Even if you go for 5,000, most of the spaces are going to be zeros, right? So in this case, representing the entire Facebook as the adjacency matrix is waste of space. So what is the best thing? Go with the adjacency list, right? So every person will have a pointer, and that pointer will indicate who is the friends to him, right? For example, if you are having 10 friends, then your pointer to the friend list will contain 10 elements, right? So whenever you load that page, you are going to retrieve the data from this. Got it? So depending on the type of the graph, we are going to go with this. And one more interesting point about this is how many entries will be there here in this. In case of undirected graph, which means like this, in case of undirected graph, the number of entries in the list completely will be 2 into E. The reason is every edge is going to contribute to one element, right? If there is an edge from A to B, that will be present here as an element, and then B to A, right? Therefore every edge is represented 2 times in this list. Therefore the number of elements that will be present in this linked list, the elements, is going to be 2 into E in case of undirected graph like this, right? What about directed graph? In directed graph, what happens is we have directions like this, okay? Then we have a edge from A to B but not from B to A. In that case, every edge is going to be represented only one time. Therefore in this space, for every edge we get one representation. So in case of directed graph, we have E number of nodes in this list completely. Got it? So just remember it, that the size of this one is, see, in this one, what about the total size? The total size is going to be order of n square. The space required is order of n square. What about the space required here? So for n nodes, n elements are required. For every node, one pointer is required. Therefore n plus, and how many elements are required here? E, 2E. But then let us say this is V. N means number of vertices. These pointers will depend on number of vertices there are in the graph, and then this entire total number of list contains 2E in case of undirected graph, right? So you can write it as the space required is order of V plus E. You can remove that constant, and you can write it as order of V plus E. Now in this case of adjacency matrix, the space required is order of V square, right? So order of V square is required in adjacency matrix, and order of V plus E space is required in adjacency list, right? Now depending on which representation we are going to use, that will have impact on the time complexity of the algorithms on these graphs. Okay, we shall see the algorithms on the graphs, and then we shall analyze what happens to the time when graph is represented as an adjacency list or graph is represented as adjacency matrix. Okay, fine. Now let's see how to traverse a graph. So rather than traversing, let's call it search. Okay, how to search the elements which are going to be in nodes, which are going to be reachable from a particular node. I'll take an example and explain you how it actually works. Let us say the graph is given like this: node 1, 2, 3. The nodes are numbered just for the convenience. You could even have names and then later map them to some numbers, not an issue, but then taking with the numbers is going to be much more convenient when I'm working with the algorithms, these algorithms. Okay, so these are 8 nodes we have, and now I want to start from 1 and I want to search all the nodes which are reachable from 1 in some order. Okay, there are 2 popular methods. One is called as breadth first search and other is called as depth first search, right? So I'll just give you the overview of both the algorithms, how they work, and then we shall get into the internal details later. Okay, so what I mean to say is, see, now when we want to search, there are searching is nothing but searching for all the nodes which are reachable from the node 1, that is the search. That is why I'm calling it as search, right? And in this process, we can classify the vertices to be of 3 types, right? So some vertices have already been visited, some vertices are not visited, and some vertices are explored. Okay, I'm going to use 2 words. One is visited and other is explored, like this: visited and explored. So these algorithms are based on these 2 words. Okay, so visited means I have already seen that vertex, which means I discovered it or I found it, right? Or I printed it. So visited means I have seen it, okay, kind of it. And explored means I have seen it as well as I have seen all the vertices which are adjacent to this. That is called explored. So visited means if I see a vertex, then that is called the vertex is visited. And explored means if I have seen a vertex and if I have seen all the vertices which are adjacent to that vertex, then it is called explored. So in general we can have various classifications. So one is a vertex might not be visited. So if it is not visited, obviously it cannot be explored. Why? Before exploring a vertex you have to visit it. Unless you know what that vertex is, how can you know its neighbors? See, explored means visiting all the neighbors. Visited means visiting only that neighbor, right? So a vertex might not be visited, or and moreover its neighbors might not be explored. That is one case. And the other case is a vertex might be visited and its neighbors might not have been visited. Then this is called as visited but not explored. And the third category is a vertex is visited as well as all its neighbors are explored. So we start off this algorithm, these 2 searches, either BFS or DFS, with every node being unvisited and being unexplored. And by the time we end the algorithms, we are supposed to visit all the nodes and explore all the nodes, right? Or by the time we end it, we are supposed to visit all the nodes. And obviously if all the nodes are visited, they are always going to be explored, isn't it? So now in order to keep track of these 2 things, these algorithms do various techniques. So in order to know whether a node is visited or not, both the algorithms are going to maintain an array. So one array is going to be maintained, an array, right? And this array, in this array, for every vertex like 1, 2, 3, 4, 5, 6, 7, 8, for every vertex one cell will be dedicated and this array is called visited, right? And this array will keep track of what are the vertices which have been visited. We initially start with one vertex which is visited. We assume that one vertex is visited, and from there we keep on visiting all the nodes in some order, right? So if this array is containing, initially it will contain all zeros, isn't it? So if this array is containing a 0 for an element, it means that it is not yet visited. If it is containing 1, it means that it is visited, right? And how to keep track of either a node is explored or not is, if a node is not explored, which means if a node is still having some neighbors which are not yet discovered or which are not yet visited, that is called unexplored, right? If a node is not explored, then they go in 2 ways. One algorithm will use a queue. One algorithm will use a queue to keep track of all the nodes which are not visited, not explored. and the other algorithm will use a stack to keep track of all nodes which are not yet explored, right? The algorithm which uses the queue to keep track of all unexplored all unexplored vertices is called as BFS, breadth first search, and the algorithm which uses a stack to keep track of all the unexplored nodes is called as depth first search. So BFS and DFS are two popular known algorithms and they work this way. See, both of them have to keep track of various things. One is whether it is visited or not and whether it is unexplored or not. To keep track of visited or not, they are going to use this array, one array, right? And but then in order to keep track of explored or not, they are going to use different data structures. So BFS is going to use queue, DFS is going to use stack, right? And anyway, since both of them are going to at least use this array, right? Now you can understand that the space complexity has to be at least greater than n. Why? If there are n elements, n nodes in the graph, right? Then how many elements should be there? How big should be this array size? It should be at least n, right? Therefore, to keep track of visited or not, at least n elements are required. So the space complexity is going to be at least n, right? So big O of n. Let's see if more space is required or not, but then just for this array order of n space is required, right? And now at any time the maximum number of nodes which can be unexplored is nearly n, order of n, right? Except the first node, all of them may be unexplored, right? And all of them might come and sit in the queue in one go. In that case, what happens is for this space taken will be order of n, where n is number of vertices, right? And here also unexplored nodes may grow to order of n. Therefore, both these algorithms are going to take space complexity of order of n. So in order to understand the time complexity and how it works, we shall take the algorithms and we shall work on it. But basic concept is this, right? So why is the name breadth first search and why is the name depth first search is given is breadth first search goes in the breadth, which means it will first cover the nodes at the first level and then visit the nodes at the second level and then visit the nodes at the third level and then visit the nodes at the fourth level. This is how breadth first search works. Then you can apply permutations and combinations to find out what is the odd, how many possible sequences can be possible, which means see, after 1 you are supposed to visit either 2 or 3, therefore we have two combinations, right? And after 2 and 3 we are supposed to visit all these 4, therefore 4 combinations. So you can bring that permutations and combinations into picture and you can even find out how many possible sequences are possible if I follow breadth first search. Similarly, depth first search also produces the results which might not be unique. In the sense, you might get more than one order. See, in depth first search what happens is we go in the depth like this, right? Breadth first search we go breadth wise, level by level. In depth first search we start at a node and we gradually go deep, right? This is depth first search. And this is not the only way possible. So there can be various ways possible, isn't it? I can go like this and I can come back, or I can go like this and again come back, or I can go like this and again come back, right? Therefore, there can be more than one sequence possible, either if you follow BFS or DFS. Then how many sequences are possible? In order to calculate it, you have to look at the structure of the graph, one thing, and second thing is you have to apply permutations and combinations. So various questions are possible like this. So one kind of question is, they'll say that on this given graph BFS is applied, what are the sequences which are possible? And sometimes they'll say DFS is applied, what are the sequences which are possible and which are not possible, right? But before going to that, let's take the algorithm and we shall analyze the time complexity and how it works. Then we shall go to the questions. Okay, fine. Now this is the BFS algorithm. I'll explain you the algorithm and then take the graph and explain you. See this. First thing is BFS is called with a vertex B, which means we are always going to start this search starting from a vertex, and that vertex is given, right? And along with that, we assume that the graph G means any representation, either the adjacency matrix or the adjacency list, any of the representations which is used, the graph capital G and the array visited. So I told you why visited is used. Just to mark whether a node is visited or not, I am going to use an array, and the graph and the visited are both global and both are initialized to 0, which means initially we start with the visited as 0, which means we assume that no node is visited and that is where we are going to start. and the algorithm is going to take a local variable u is going to be assigned a value v, right? So what does it mean? So we are going to start from whatever the vertex it is that is going to be assigned to u. So why did I do this is, I'll tell you later, okay? For now keep it that way. So we are going to assume that every node that we are going to explore now is always going to be u, right? Why? We shall see later. Repeat, for all vertices w adjacent to u, which means whatever vertex you are examining now, which means whatever vertex you are going to explore now. What is exploring? We want to see that see all the vertices which are reachable from it. What are all the vertices which are adjacent to this? That is what exploration is, right? Now for all the vertices w adjacent to u, which means we are trying to explore u, right? So now while exploring u, these are all the, let us assume that w is the set, and w is nothing but one of the vertices which is adjacent to u, right? If it is already visited, which means if the adjacent node is already visited, then if it is not visited, equal to 0 means if it is not visited, then I am going to add it to the queue. Why? If it is not yet visited, then the chances are that it is not yet explored, isn't it? Therefore I have to add it to the queue for later exploration. But now since I have visited it, I am going to make visited of w equal to 1. Are you getting this? See, I am going to take a vertex and I am going to explore it. And how do I explore? I just look at all the vertices which are adjacent to this, and if they are not visited, then I am going to keep them in the queue for later exploration. And moreover, I have to mark that they are now currently visited. That is why I am going to add it to the queue for later exploration, and even I am going to mark them as visited currently, right? And if queue is empty, then return, which means in case if you have explored all the elements, then queue will be empty, right? Then you can return, because if you have explored all the elements, it really means that you have visited all the elements, isn't it? Then if it is not the case, which means if queue is not empty, then we come here, right? Then what we do is we delete the next element from queue and we call it as u. That is why I am taking u equal to v, so that this entire loop will be consistent. Otherwise what I should do is, I should call this entire loop once for v and then once for u. So instead of that, I am just maintaining a value u, and always one element is going to come into u from the queue. Okay, so I'll take an example and explain you, right? So if you didn't understand it, don't worry, we shall see an example. Let us say this is the graph which we are trying to search, and the search is going to start from 1. So if I start searching for all the nodes which are reachable from 1, let us see what is the order in which I visit the nodes, right? That is called as BFS order, right? So breadth first search order. So we shall call this algorithm with v equal to 1. So initially we are going to have the vertex visited, right? The vertex visited, which is all initialized to 0. Okay, so visited of 1, visited of 2, 3, 4, 5, 6, 7, 8. So all these 8 values are initially initialized to 0. Now when you call the first one, right? Oh, there has to be a step here. Let us say visited of v equal to 1. Why? So once I call v, on v is definitely that is going to be visited, isn't it? So initially we are going to call this function with 1, and now u equal to 1 and visited of v equal to 1, which means the first node is visited. That is what I am going to remember, right? And now I am going to get into this, right? So what is u? U is now 1. Okay, for all vertices w adjacent to u. So what are all the vertices w adjacent to u now? What are the vertices which are adjacent to 1? So 2 and 3, right? 2 and 3 I have to do for each of them, right? I'm going inside this, and this entire thing has to be repeated for each w, which means for 2 and 3. Now first thing is, if visited of w equal to 0, is visited of 2 0? Yes, which means it is not yet visited, right? Then we are supposed to have a queue also, right? So initially queue will be there. then what happens is inside the queue, this is the queue, right? So if a node is not visited, yes, I am talking about 2, w equal to 2 first. If it is not visited, then add w to queue. Why? Because since it is not visited, it is not explored also, and later I have to explore it. That is why I am going to add it to the queue. Yes, it is added. Add it to the queue. And what is next statement? Visit of w equal to 1. So since we have visited 2 now, from 1 we have visited 2, right? I am going to mark it as visited. So 2 is visited, but it is not yet explored. That is why it is present in the queue. Got it? And now again I have to come here. So for loop is over, right? So just hold on here. So for loop, delete the element from the queue. We should delete the element from the queue after it. So let's put one more parenthesis here and one more parenthesis here. Okay, so which means this has to happen, the for loop has to happen. Okay, the for loop closing is here. So for loop has to happen for all the vertices, right? And now I am going to do it for the second vertex also, w. Now w is visited of w0. Check this. Is visited of w0? Yes. Therefore what should I do? It is not yet visited. Therefore I have to add it to explore it, and then I have to mark that it is visited. So I have to add that it has to be explored later, and I have to mark that it is visited. Okay, fine. Now for all the vertices w adjacent to 1, they are all over. Therefore you come out of this for loop. So what is this? If q is empty, is q empty? When will q be empty? If there are no more nodes which have to be explored, then q will be empty. But since there are more nodes which have to be explored, so q is not empty. Delete a node from the delete a next node and add it to u, which means I have to delete the next node and I have to add it to here. So the next node which has to be explored is 2. Got it? Now watch it. Again everything has to be repeated. For all the vertices w adjacent to u. So what are all the vertices adjacent to 2? The vertices which are adjacent to 2 are 1, 4 and 5. Isn't it? 1, 4 and 5. And one more thing, if you observe it, I am writing w equal to 1, 4 and 5 in this order, but it could be any order in general. The order which we get here, that depends on the representation. In the representation, if you are having adjacency list representation and in which the list is containing 1, 4, 5, then they will be visited in that order. Therefore the visiting order generally depends on the representation. See, even though I am taking 1, 4, 5 here, it need not be always 1, 4, 5, right? It depends on the way you represent it. Got it? Therefore depending on various representations, they might sometimes take 5 here, 4 here, 1 here, right? Then the first one which will be visited next will be 5 instead of this. Are you getting this? Okay, let me write even the visiting order also. 1 is visited, and next 2 is visited, and next 3 is visited, isn't it? And now I'm going to do next one. So I'm going to export 2. When I'm exploring 2, I found out that the adjacent values of 2 are 1, 4 and 5, right? And what does this for loop do? For each one, right? For all the vertices w adjacent to u, we are going to do this, right? So now I'm going to pick first one, 1. If visited of w equal to 0, is it visited? 1 is visited? Yes, it is already visited. It is not equal to 0, therefore this one will not happen. Again we come back into the for loop, right? And we take the next one. If visited of w equal to 0, is visited of w 0? Yes. Therefore it is unvisited. Therefore what is that we are supposed to do? Add it to queue and mark it as visited. So next one which is added to the queue is 4. Why? Because I am considering 4 as the next element. In case if you have considered 5 here, right, if your implementation has given you 5 first, then you would have added 5 first and we would have made visited of 5 first. But then here I am considering that my implementation is taking 4 first. Depending on that I got 4, right? And earlier also I have taken 2 first and 3 first. It need not be the order, right? It can be 3 first and 2 first depending on the implementation that you are following. Got it? So now 4 is added to this, and 4 is added to this and 4 is marked as visited. Fine. And again I have to take the next one, which means 5. And again we check it. So is visited of 5 true? Check this. Is visited of 5 equal to 0? Yes, it is 0. Therefore what is that we are supposed to do? Add it to the queue and mark it as visited, right? So therefore what is the next one which is visited? Visited 5. Got it? Fine, all of them are visited, therefore for loop will be over. After for loop, again we go into this if statement will fail, again we delete the next element from the queue. What is next element to be explored? 3. Therefore u is going to take 3, right? And again what happens, all the elements which are adjacent to 3, we have to examine them. So what are all the elements which are adjacent to 3? 1, 6 and 7. 1, 6 and 7. Even though 1 is visited, we still don't know that, right? That is why I have to visit it again. So I have to consider it again. Now I'll consider 1 first. Now we find out that visited of 1 is true, therefore it will not be done in, this if will not be executed. Next one is 6 will be considered. So visited of 6 equal to 0, therefore 6 will be added to unexplored nodes and visited of 6 will be made as 1. So what is the next one which is visited? 6. Got it? And next one is 7 will be considered, and since visited of 7 is 0, it will be added to the unexplored nodes, right? And visited of 7 will be made 1, therefore 7. Got it? And next one is 7 is over, right? So 1, 6, 7 are over, all of them are visited, right? All the vertices are explored, therefore we are going to go for the next element from the queue. So what is next element from the queue? 4. So 4 is picked up for exploration. 4 is picked up, right? Now what are all the vertices adjacent to 4 are 2 and 8, right? Now 2 and 8 will be explored. See this, first 2 will be taken, and since visited of 2 is 1, right, it is already visited, we will not do anything for it, which means this if loop will not, if that if condition will not get executed. Now what about this 8? Visited of 8 equal to 0, therefore 8 will be added to the unexplored nodes and it will be made visited of 8 equal to 1, which means 8 is marked as already visited, right? And now both all the vertices are already over, so we need not do anything for this, right? So we are going to come out of this for loop and again pick the next element. So 8 is the next one which is visited. Now what is the next element which will be picked up? 5, right? So when 5 is considered, right, 5 is considered, what are all the nodes which are adjacent to 5? 2 and 8. But if you look at 2 is already visited, 8 is already visited, therefore all the adjacent nodes are already visited, you need not explore it further. So nothing will happen for it in this for loop, right? So next element will be considered, which is 6. So what are all the vertices which are adjacent to 6? 3 and 8, right? But then instead of 3 is visited and then 8 is visited, therefore nothing will happen here, and again we pick up the next element. What is next element? 7. So you will be made 7, right? What are the vertices which are adjacent to 7? 3 and 8. Again we find out that 3 and 8 are already visited, therefore nothing will be done, right? So what is next one which will be taken out? 8. So what are the vertices adjacent to 8? Vertices which are adjacent to 8 are 4, 5, 6 and 7, right? And you see that 4, 5, 6, 7 are already visited, therefore nothing will happen in the if loop, so we are going to come out, right? And finally q is going to be already empty, therefore we are going to come out of it, return, right? So if you observe it, the way we did it is we started from 1 and then 1 is marked as visited and all the vertices adjacent to this are visited next, which means 2 and 3 are visited, and this can be in any order, which means either you can write 2, 3 or you can write 3, 2, right? Depending on the order we add them to the queue, the next element will depend on it, right? If the next element picked up is 2 for exploration, then 4 and 5 are explored, 4 and 5 are visited, right? And if the next element which is picked up is 3, then 6 and 7 are visited, right? If the next element which is picked up is 4, then 8 is visited, right? And it can be any other order. In case if we have visited from 1, visited 3 first and added 3 to the queue first and then 2 to the queue next, then what happens, because of this 3 which is going to be explored next, I visit 6 and 7 first, right? Or it could even be 7 and 6, right? And after that, when I take 2 for exploration, then I will visit 4 and 5, right? Or 5 and 4 also. Then when I take 6 for the exploration next, then I will visit 8. Therefore, more than one order is possible here. Are you following it? So the way we visit the nodes may be more than one. It need not always be a unique, right? It depends on the implementation. So in your adjacency list for 1, right, in case you are using adjacency list, in the adjacency list for 1, if you are having 2, 3 like this, right? Then 2 will be added to the queue first, and then 3 will be added to the queue next. Then in that case you are going to get 2, 3 here, right? And then depending on what is stored at 2, we'll get 4, 5 or 5, 4. Therefore it is completely dependent on implementation. We might get more than one order, but ultimately what we should observe is all the nodes which are reachable from 1 will definitely be printed. Will definitely be visited. So why am I trying to print? I'm just trying to show you wherever we are saying visited, I'm just saying that I'm just putting a printf line also. Then you will know what is the order in which they are printed. See, after this you can even put printf statement, printf, let us say w. Then what happens is you will get this order. This order is important. Got it? Let's now analyze the time complexity, time taken to run this program, and then the space complexity. Okay. Now let's see DFS, depth first search. The main difference between breadth first search and depth first search is, in breadth first search, when we take an element for exploration, we take it and we visit all the elements which are adjacent to it, and we completely explore it and we leave it. But in depth first search, what happens is, here depth first search, we take an element for exploration and we start exploring it, and as and when we find a new element which is unexplored, we leave this element and we start with that. And again that element also we do the same. We try to explore it, and as and when we find a new element which is unexplored from that element, we go to that. Okay, I'll just take the example and I'll show you, that will explain you. Anyway, just see the algorithm. See, now BFS of V, which means we are calling that, DFS of V, which means we are calling the DFS starting from a vertex. That is why it is again a search, because we are starting only from one vertex, right? Visited of V equal to 1. So initially we are going to make visited of V equal to 1. See, one more thing you should observe is, either in BFS or in DFS, before we start, one basic assumption is visited array is global and visited array is initialized to 0. But then in this code we are not initializing it. Where are we initializing it? See, we intentionally didn't keep that initialization of visited inside this code, because this function might be called by other functions like traversal functions. For example, depth first search may be called by depth first traversal. So traversal, while before calling in DFS on any node, it will initialize it. So initialization is done by other program which is going to call this program. Therefore I am going to take the time taken to initialize the array also into time complexity analysis, but then I am not showing you that part here, because that is done by the calling function, right? And even though that has to be done in here only, that is true, but then I want this to be reusable later. That is why I am just putting it aside. See, what happens if every time when you call this BFS or DFS, if you try to initialize visited array is, in case of that traversal, right, whenever we visited some of the nodes and again we call the BFS or DFS for unvisited nodes, again that entire array will be flushed away. That is why I don't want to put it in the code, right? But if you are going to call this independently, individually, only on one vertex, then you are supposed to initialize it to 0 before you start. That is why in time complexity analysis I am taking even the time taken to initialize visited. Okay, fine. So anyway, let's see this. So visited of V is 1, which means I am considering that whenever I take a vertex V, that is I'm visiting it, right? And then the exploration starts. Now for each vertex W adjacent to V, which means I am going to visit all the vertices which are adjacent to W, right? If it is not visited, then the problem here is I'll start visiting that, which means I'll start exploring that node. See, DFS is nothing but the function DFS itself will be used for exploring a node, exploring a vertex, right? Now initially when we started exploring a vertex, we say that it is visited, and then we take up all the nodes which are adjacent to that particular vertex, and then if you find any vertex which is not visited, then we leave this vertex and we start exploring the other vertex, right? So it is better I'll take the example and explain you. There is a lot of difference. You might think that it is not different from BFS, but actually there is a lot of difference between BFS and DFS. In BFS, we take a vertex, explore it completely and throw it away. But in DFS, we take a vertex, and then try exploring it, start exploring it, and whenever we find the first unexplored vertex, we again go to exploring that, and again we come back, right? I'll just show you how it works. Watch it. Let's take this example, the same example which we used for even BFS also. Okay, and one more thing, I'm intentionally taking all the graphs to be undirected, but you could use the same algorithm on directed also. Only thing is, if one, A is adjacent to B, in directed B might not be adjacent to A, but here it is adjacent. Therefore the main difference between directed and undirected will be when you are trying to analyze the time complexity. So in case of time complexity analysis in adjacency list, right, we might encounter a node 2 times, which means the time taken might be doubled by a factor of 2, but the asymptotic analysis saves the same time, right? So just remember that these two algorithms can be even applied for directed as well as undirected graphs. Okay, now let us say I'm calling DFS on 1. So this is we are going to have a visited array, right? 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. We are going to have visited array, and which is initialized to 0 initially. All are initialized to zeros only, right? So this is not initialized inside either BFS or DFS. Any function which is calling these functions is supposed to initialize it, right? And now let me show what happens in this stack. This is the stack, right? Fine. So first thing is V is going to be 1. So it is going to be, we are going to call DFS with vertex 1 as the starting node, the seed, right? That is also sometimes called as the seed, right? And now from V, visited of V equal to 1, which means 1 is visited. I made this visited as 1, right? It is no longer 0, it is 1, right? And now for all vertices, for each vertex W adjacent to V. So what are the vertices which are adjacent to 1? So W can have 2 vertices. What are they? 2 and 3, isn't it? For each vertex. Now we take each one by one. Let us say I'm taking first W to be 2. See, even though I'm writing W as a set, actually W as is an element. So this is the adjacency set. So the set of all elements which are adjacent to 1, from that W is going to pick one of them. Either it could pick 2 or it could pick 3, depending on how we have implemented it. In the implementation, if 2 comes ahead of 3, then we pick up 3, right? So first thing is, we are going to take visit of 1 is visited, and now we are going to take 2, and again we are going to call DFS on W, which means we are going to call DFS on 2. So what happens? Again one more DFS will be called, and for this DFS, what will be the V? V will become 2. Got it? And again the entire thing has to be executed. So what is it? Visited of V equal to 1. So visited of 2 equal to 1. So this one will be made 1, which means 2 is the next visited node. Got it? Next thing is, for all for each vertex W adjacent to V. So what are all the vertices adjacent to 2? If you look at 2, the adjacent vertices are 1, 4 and 5. 1, 4 and 5, right? Now we are going to take one by one. W is going to be initially 1. Let's assume that it is 1. Then what happens? So if visited of W equal to 0, is visited of W 0, which means is visited of 1 0? No, it is 1. Therefore the function calling will not happen. And next 4 will be considered. Again it will check, is visited of 4 0? Yes, 4 is 0. Therefore again we are going to call DFS on 4. DFS on 4, which means V equal to 4. Are you observing it? See this. First V is taken for exploration, and whenever it has found one unexplored node, we have left the exploration of V here, which means we are not going to explore all the adjacent vertices. We are going to 2, and whenever 2 has found one unexplored node, we are going to 4. Right? So in BFS, what happened is, whenever we are taken a node for exploration, all its adjacent nodes will be visited, then only we move on to the next one. But here, whenever we find any new node, we are directly jumping to that. And later we come back and then explore the remaining vertices. Right? You'll understand it, don't worry. Now coming to 4. So what are all the vertices? So what is the first line? Visited of 4 equal to 1, which means this one will be made 1. Right? And the next one is, for each vertex 4 is visited, right? For each vertex W adjacent to V do. So now what are all the vertices which are adjacent to 4? 2 and 8. So W can be one of either 2 or 8, isn't it? Now 2 will be considered. Let us assume 2 is the head of 8 in the implementation, and when 2 is considered, now what is the check it will make? If visited of 2 equal to 0, is visited of 2 equal to 0? No, therefore nothing will happen to this, which means DFS will not be called again. Why? Because it is already called, and now 8 will be seen. Now again we are going to see 8. So if DFS of 8, sorry, visited of 8 equal to 0, yes, it is unvisited, therefore this will be taken for exploration. Got it? Again DFS will be called. In this DFS, what is V equal to 8, right? Now what happens? Visited of 8 equal to 1, so this one will be made 1, and then for each vertex W adjacent to V, so what are all the vertices W adjacent to, what are all the vertices adjacent to 8? 4, 5, 6, 7, right? All these vertices are adjacent to 8. Got it? Now we are going to take one of them. Is visited of W equal to 0? Is visited of 4 equal to 0? No, it is 1, therefore nothing will be done for this. Why? Already 4 has been taken up for exploration, it will not be taken up for exploration again, right? Exploration again. Now what about 5? Is visited of 5 equal to 1? Is 0? Yes, it is 0, therefore again 5 will be picked up for exploration, which means again DFS will be called with V equal to 5, right? Now what happens? So visited of 5 equal to 1, which means this one will be made 1, and now all the nodes which are adjacent to 5 will be examined for each node W adjacent to 5. So what are all the nodes which are adjacent to 5? 2 and 8. 2 and 8, right? And now we are going to take first one 2. Now we shall examine whether it is already visited or not. Is visited of 2 equal to 0? No, it is equal to 1, therefore nothing will be done to this. What about visited of 8? Is visited of 8 equal to 0? No, visited of 8 equal to 1, therefore this for loop is over for this DFS calling. So what is it? It is supposed to return. So this is the first return, right? So if you observe it, we are going like this, and we are going like this, and we have gone like this, right? And then we have gone like this, and there is nothing to be explored, therefore again we are coming back to 8, isn't it? Are you observing it? Again we are coming back to 8. So if you observe this, we are starting from 1, and we went to 2, and then we went to 4, and then we went to 8, and then we went to 5, and 5 is useless anymore, therefore we came back, and again we came back to 8. Got it? So what is visited in the order? 8 is visited, right? And then 5 is visited. If you observe it, 1 is visited first, next 2, next 4, next 8, next 5. This is the order in which we visited. Got it? Now next one is 6 is considered. Is visited of 6 0? Yes, therefore again DFS is called with V equal to 6. Got it? So this one is made 1, and DFS is called with V equal to 6. Then what happens here? So visited of 6 equal to 1, which means 6 is next visited, and moreover for all vertices which are adjacent to 6. What are all the vertices which are adjacent to 6? So one is 3 and other is 8. So first 3 will be considered. Is visited of 3 equal to 0? Yes, visited of 3 equal to 0. Therefore we are going to call again DFS on 3. So V equal to 3. Got it? So what happens? Visited of 3 equal to 1. So next one to be visited is 3. Got it? So visited of 3 equal to 1. And what are all the vertices which are adjacent to 3? Check this. What are all the vertices which are adjacent to 3? 7 and 1. So 1 comma 7. Now 1 will be considered, but visited of 1 is already 1, so it will not happen anything. And again 7 will be considered, and visited of 7 equal to 0. Therefore we are going to call DFS again on 7. DFS on again vertex 7, right? So when vertex 7, when DFS is called, again we are going to do visited of 7 equal to 1, which means this one will be made 1, right? And for all vertices which are adjacent to 7, so 7 is visited. What are all the vertices which are adjacent to 7? We are going to take one by one. Now 3 and 8. So initially 3 will be considered as W, right? But then we see that 3 is already visited, right? And nothing will happen. and 8 is also already visited, nothing will happen. Therefore this one will be popped off, right? Because this for loop is over, so this one comes out. Now again we are here, so this one is already over, right? 1 and 7 are already explored, so this one also comes out, and here it will try to explore 8. So it will see if 8 is unvisited or not, but then it turns out that 8 is already visited. Therefore for this function also the for loop gets completed. It one gets, this one also gets popped off, right? And this one is over, and here it will try to see if 6 is remaining, right? It will try to see if 6 is unvisited, but then 6 is already visited, and then it will try to see if 7 is unvisited, but 7 is also visited. Therefore this one also will pop off. Next 8 is already over, popped off. Next it will try to see if 5 is unvisited, but 5 is visited, popped off. And then it will try to see if 3 is unvisited, but 3 is visited, therefore popped off, right? So this is the order in which we are going to explore, right? So if you watch it, how this happened, from 1 we went to 2, and from 2 we went to 4, and from 4 we visited 8, and from 8 we visited 5, and again we came back to 8 and we visited 6, and from 6 we visited 7, and from 6 we visited 3, and from 3 we visited 7, right? So this is the order in which we visited. Got it? So what is the time complexity and space complexity analysis? We shall see the analysis now. Okay. See, in most of the data structures, the main operations that we would like to do is, one is, the main reason why we use data structures is to store data, either to give it as an input to an algorithm, or to take the output from an algorithm. So data structures main intention is, to help us store the data. And whenever we have a data structure, any data structure in general, the most common operations that we perform on a data structure is, one is insert an element into the data structure, right? So we do insertion, and after inserting the elements, we might want to search for a particular element, right? So searching an element, and then we might want to delete an element, right? Delete. And very often it's, at practice what happens is, many of the data sets, data set means the data, okay? Many of the data, let me call it data set, don't get confused, data set is nothing but the data, okay? So data sets are generally static in the sense, once you create the data, it rarely changes. We insert the elements and then we leave them like that without any changes or modifications. That is what happens at many of the practical cases. Then in those cases, the main operation on data set turns out to be search. Search is the very dominant operation that will be generally performed on any data structure, right? So many of the data structures are mainly designed with this in mind, this searching. So we want to search the data faster, right? So now if you watch various data structures, they really don't have very good time for searching. For example, if you see an array, in an array, let us say it is an unsorted array and I want to search an element. How much time is it going to take? I'm just listing out some of the data structures we have. One is unsorted array, right? In unsorted array, if you want to search for an element, we might have to compare it with all the elements, and the time taken might be as big as order of n. Now if you use a sorted array, right? So how much time does it take to search an element? We might apply binary search, and it turns out that we can search for an element in logarithmic time, order of log n, right? Or in case if you use a linked list, right? If you have a linked list, in this case, if you want to search for an element, again you might have to search the entire list, right? Then the time complexity is going to be order of n, right? Or if you use a binary tree, then we might have to do that traversal. Time taken is order of n, right? Or if you use a binary search tree, so we have seen that there is a binary search tree, right? So in binary search tree, it is mainly designed in such a way that it helps us in the searching operation, right? But in worst case, a binary search tree might become a linked list, right? In that case, the time taken is going to be order of n. Normal binary search tree, the height of the tree can go as big as order of n. In that case, searching is going to take order of n time. And in case of balanced binary search trees like AVL trees, 2, 3 trees, red, black trees, wherever we try to balance. So if it is a height balanced binary search tree like AVL tree, then the time taken is going to be order of log n, because height of the tree is going to be log n, isn't it? And there is something called as priority. So we don't want to search for any element, we want to search for the minimum element or maximum element. They are called as priority queues, right? So if I have priority queues like min heap and max heap, right? In this, searching for a particular element, searching for min and max is going to be order of 1 time, but then searching for a particular element is again going to be order of n time. Okay, so if you see any of the any of the data structures, always the least search possible on most of the data structures is going to be order of log n, the best search, right? Then what people thought is, if search is so frequently used on some data structures, then why don't we minimize the time as much as possible? And the solution comes in terms of hashing. So hashing is the solution for the search time, to minimize the search time. If you use the hashing technique, then on average the time taken to search an element is going to be order of 1, which is constant time, right? We shall see how this constant time is possible, right? And earlier, before using this hashing technique, people used one more technique which is called as, just like array, okay, which is also called as direct address tables. So what is direct address table is, it is just similar to arrays. Let us say you have to store 100 elements, okay, so or we have to store 100 records in such a way that each record is having a unique key, and that key is ranging from 1, 2, 3, so on 100. So if you know that 100 elements will be inserted into your data structure, and each element is going to have a key value, and that key is going to be unique and it is going to be in the range of 1 to 100, then the best thing to save it is in terms of an array, right? So we can define an array of size 100, and whenever you want to insert an element, you insert it into the corresponding spot, which means every element that has to be inserted is going to have a slot in the array, right? So if, let us say, you want to insert an element which is having key 10, then I go into the array, into the index 10, and I'll insert it there, right? Later, if I want to search whether that element is present in the data structure or not, then I can simply go to that element directly and I can find it out. How? Because since array is a this random access data structure, we can directly get into any index easily. So if the key itself is going to be the index, then search time is going to be order of 1. So the first data structure which has supported this searching in order of 1 time is called as direct address table. In this table, we are going to have an array, and we are going to place an element according to the key value, right? And this method is useful only when you know the number of keys which are going to be in a small range, and if the number of keys which are inserted is very less. In case, let us say, key values, because I am directly going to use the key values into the in array indexes, therefore there has to be a linear relationship between directly proportionality between number of keys used and the size of the array. In case if the keys used are very big, very large in number, but the total number of keys are less in number, let us assume that totally there are 10 elements going to be inserted, but each element is going to be of size 1 million. Let us say the keys inserted are like this, okay, and something like this. I'm just randomly taking the examples, okay. Now if the keys inserted are like this, but only 10 keys are inserted, then even to put these keys, I have to define an array which is having as big index as this key, right? And this key itself is 1 million. Therefore, the array size might have to be 1 million just to store 10 values, right? In such cases, this direct address table is going to fail. So direct address table was used very early when and it is useful in the case when the key size and the number of elements are actually close to each other, which means if the key size is in hundreds and the number of elements which are going to be stored is also in hundreds, then maybe defining one slot for each element is useful in such a way. If the key size is very large and the total number of keys which might be inserted into the array is very small, then having such a architecture is a waste of space. So there we are going to use hashing. So I'll talk about hashing in next video. Okay, fine. The problem with direct address table is the size of the array, the table, is going to be as big as the key sizes, isn't it? And many times we might end up declaring an array of very big size even though the numbers inserted have to be very less, right? In order to solve this problem, we use hashing. So hashing says this: see, even though the number of possible keys that have to be inserted into our data structure are very large, let's call it a universal set U, okay, but at any time the number of elements which will be present in our actual data structure, okay, are small, which means the potential candidates which might have to be placed in our data structure are very large, but then not all of them will be present in our data structure at the same time. Only few elements are going to be present in our data structure at some time, right? Then instead of declaring a data structure whose size is as big as the universal set, we just declare the data structure just enough to hold all the elements which might be present at any time, right? Then what happens is, now this data structure is very small, or the number of slots that are available in this table are small compared to the number of potential elements which might compete for these slots, right? Which means, to say it in simple words, let us say the value of keys ranges from 0 to 1000, okay, or let us say 0 to 999. This is the value of keys, and any of these keys may be present in our data. But at any time, if we have to put only, if I say that if at any time only 10 elements will be present in our data structure, not more than that, then declaring a data structure which is having 1000 slots is a waste of space. Instead of that, what we could do is we could declare a space of just 10 elements, right? And then we could try to map. So whenever any element is given, we could try to map it into one of these slots, right? The mapping function which we are going to use is called hash function. Okay, so what I mean to say is, if at any time you are sure that our data is not going to go beyond 10 elements, just for example, okay, then you can declare a table or array of size 10, and whenever any input is given, you apply some function on it, so that that function itself will say where to put that element in a constant time. And later when you search for that element, again you apply the function on that element and go to that particular spot which is located by the hash function. In case if that element is present, we can say it is present. In case if it is not present, we can say it is not present. Therefore search time is going to take order of 1 time. I'll just take a small example and explain you. Let us say we have to insert keys like this: 121, 145, 132, 999, right? These are the keys which have to be inserted into a table, right? And the table size is, let us say, 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now all these elements have to be inserted into this table in such a way that insertion should take place in constant time and searching should take place in constant time. Then what I will try to do is, I'll come up with a function which will take any of these keys and which will give as output some indices here, right? In case, how many indices are here? 0 to 9. Let us say 10 elements are there, 0 to 9 indices are there. And what are the possible key values? Let us say the possible key values are 0 to 199. Then what is a 0 to 999? Then what is a hash function is? Hash function is any function which will take the values from 0 to 999, in the range 0 to 999, and it will map them to one of the values in 0 to 9. So this is called as a hash function, simple words, right? So in the meaning of this, let us say the table size is 0 to m minus 1, right? Then hash function is any function which will take a key from u and it will map it to one of the values from 0 to m minus 1. This is the hash function. Got it? So in this case, I can define a simple hash function to be mod 10. Right? Then what happens is, whenever you want to insert any element, you just take the mod 10 value and you go to that particular element and you put it there. For example, if I want to insert 121, then I'll find out what is 121 mod 10. What is that value? 1. Therefore, I'm going to put 121 here, right? Or a pointer here which will point to 121, whatever it is. If you say that directly key is the data which has to be inserted, I will directly put the data there. If you say that key indicates the record in which and the record is present at some other point, then I'll place the record there corresponding to 121, the pointer to the record. Okay, so anyway, let's just put the data itself. Okay, now where are you going to place this 145? 121 is over, so mod 10 gives 145, which means I'm going to place it here. Where are you going to place 132? Mod 10 gives 2, therefore 132 is placed here. Where are you going to place 999? It is going to be placed in 999. Got it? And all the other elements are initially, the table is initially initialized to null. So all the other elements are going to contain null, right? Then insertion is simply done in order of one time. And now let's talk about the searching. If I say, let's say I want to search for element 150, then what I do is I'll find out 150 mod 10. Why should I find it out? Because in case if 150 is present in this table, then definitely 150 would have been present in 150 mod 10. So what do I get? 0. Then I go into this table and search in the 0. It says that the element is not present, right? It says that it is null, therefore the element is not present. Therefore I can declare that the required element is not present in the table, right? So searching goes in that way. For example, if you want 145, right? If you want to see whether 145 is present or not, then I'll find out 145 mod 10 and it turns out to be 5. Then I'll go into the table, into the element 5, and then I'll see this 145. Yes, then I'll say it is present. Therefore, search time is nothing but time taken to run that hash function and directly access the table, which is going to be constant. So insertion and searching is going to take constant time by using the hashing technique. Got it? So this entire thing is called as hashing. Hashing is simply taking a set of very large numbers and then mapping it to a set of small numbers, and this set of small numbers correspond to the indices of our data structure or the table which we are going to use. That is also called as hash table. Got it? And now once we do this mapping, insertion is going to take place in constant time, just the time taken to compute the array in that index, and searching is also going to take constant time, and even deletion is also going to take constant time, right? But the problem is, there is a problem called as collision. Collision is whatever function you come up with, when we have to map such a large numbers, large amount of numbers into a smaller element set, smaller set. It is a bigger set and it is a smaller set. When we do such a mapping, then obviously more than one element might map to the same cell. For example, here, after inserting all these numbers, let us say I want to insert 131. Then where should I insert it? Then I'll find out 131 mod 10. Then it says that you have to insert it in location number 1. Then I'll try to insert it in location number 1, in which already 121 is present. Now 131 also wants to go to the same slot. When two elements or two keys are being hashed into the same value, right, into the same cell, same slot, then that condition is called as collision. So what is collision? When more than one value, if they actually map into the same cell in the hash table, then that is called as collision. So disadvantage of hashing is collision, or I don't say disadvantage, the challenge, right? The problem with hashing is we might definitely have collisions, right? Then there are various solutions proposed in order to deal with these collisions. So one solution is they ask us to come up with a better hashing function in such a way that collisions can be minimized. But however good your hashing function is, see, They, like, just like mod 10, maybe using a prime number might give us less number of collisions. See, using mod 10 is nothing but I'm just using only the least significant one bit of the number. I'm not taking into picture the entire number, right? So if you come up with better hash functions, then maybe the numbers will be distributed well, right? So one solution to this solving this collision problem is coming up with better hashing functions. Better hash functions, right? But the problem with this better hash functions is you could come up with better hash functions which is going to decrease the number of collisions, but then the total number of collisions will never be zero, which means you will definitely be able to decrease the number of collisions, but you can never say there are no collisions at all. That is the problem with this. So even if you come up with a good hash function, still the problem of collision is there, right? So in order to solve the collisions, the next solution is chaining. So chaining says this, in the hash table, instead of putting one element in that slot right away, you maintain a linked list, and whenever you want to place an element, you try to place it in this linked list. Let us say you want to place, three elements are mapping into this same cell, then all these three elements will be placed in this linked list. In case if one more element maps onto this same cell, then that element will also be inserted here. So collision resolution techniques are of various types. The first collision resolution technique is chaining. So using chaining, what we could do is we can place the elements in such a way that even if more than one element maps to the same slot, they will be accommodated inside the linked list. So in this way, actually the slots in the hash table are actually now pointers to a linked list, and the linked list will contain all the elements which have mapped to that particular cell, right? We shall see the examples, don't worry about it, I'll explain you later. I'm just telling you the collision resolution techniques, right? So first collision resolution technique is chaining, and the next collision resolution technique is called as open addressing, right? So what open addressing says is, in case if you have a collision, which means if you are trying to put an element at some point, and if that cell is automatically already occupied, then you again recompute the hash value. And then find out where that element can be placed. If you are lucky, then next time when you recompute the hash value with some minor modifications to the input, right? I'll tell you what are the modifications. Then again the next recomputation of the hash value might lead you to some other empty vacant space. In case if that space is also already occupied, again you compute it, right? You keep on doing this until you probe all the values. Probing is nothing but searching for a empty space in which you want to insert an element. That is called probing, okay? So open addressing says that whenever you come across any cell in which already an element is present, and now your present element also wants to go into the same cell, then you keep on recomputing the hash function with changes in the input. I'll tell you what the changes are, right? Then that is called as probing, and this open addressing is implemented in various ways. One is called as linear probing, and other is quadratic probing, and the other is double hashing, right? So in general, the main difference between chaining and open addressing is, in chaining elements have to be stored outside the table, but in open addressing elements are stored inside the table, right? And in chaining we are wasting some space for the pointers, and in open addressing, since we are not using the pointers, we can effectively use the memory and we can increase the size of the table more than this chaining technique. And once I increase the size of the table, the number of collisions will decrease, as well as the space will be utilized better way just to accommodate the keys, right? So when do we go for open addressing and when do we go for chaining is advantageous in case if you want to delete the elements also. If you want to insert, and if you want to delete, and if you want to search for an element, chaining is better. And if you want to insert an element, and if you want to just search, which means if you don't want to do any deletions, then this one is better. So if you want to go for deletions, chaining is going to be better. If you don't want to go for any deletions, then open addressing is better. So depending on your need, you can choose one of them. So just to summarize it, what I'm trying to say is, see, hashing is mapping a set of elements from a larger set to a smaller set, right? And the problem with this is, whenever I give such a mapping, the chances are that two elements might map to the same element. Got it? Now that is called as collision. So in order to decrease the collisions, you can come up with better hash functions, right? For example, mod 10 is going to use only part of the number. You can come up with various hash functions which might use better, which might give you a good distribution of the keys, right? But still, even then, if you have large number of elements which are to be mapped onto a small number, definitely there will be collisions. I can never say that collisions will become zero, right? Then what is that we are going to do? We have to resolve the collisions. Then these are the collision resolution techniques. So one collision resolution technique is chaining. What we do is, we'll never save the elements in the table itself, hash table. We'll save them outside in the linked list. So since we are having a linked list, which is a dynamic data structure, even if more than one element maps onto the this table, I can place them happily inside the linked list, any number of elements. Therefore, I need not worry about collisions, right? And in open addressing, we are going to save all the elements in the table itself. Now, what is the main difference between open addressing and chaining is, in open addressing, the number of elements which can be present in the hash table can never exceed the size of the hash table. But then in chaining, the number of elements which can be present in the hash table can be even can grow beyond the size of the hash table. Let us say if the hash table size is 10, then you could even insert 1000 elements in the hash table by using the chains, right? But here, since all the elements have to be present in the hash table itself, right? If the size of the hash table is 10, I can only put 10 elements. So after 10 elements, you will get an overflow error, which means even if you try to put one more element, it will say that there is no space. Got it? So which one is better? That depends. Okay. So just remember this: if insertion, deletion, and search are all to be performed, then chaining is better. But if only insertion and search has to be performed, then open addressing is better because it uses this space efficiently. Here it is going to take a lot of space. Obviously there is trade-off. If you can afford more space, then you could get better deletion performance also. But if you don't have a lot of space, then deletion is going to take more time. Got it? The only difference is in terms of deletion. So what we shall do is, we shall see each technique and the advantages, disadvantages along with the problems. Okay. In chaining, we have a hash function and a hash table like this. Okay. So we'll have a hash table of some size, right? And then some hash function h, let's call it h. Now what happens is, if we want to insert any key k into this hash table, then what we do is, we compute the hash function h of k, and now we go into this table. Let us say this table is represented by an array t. Then we go into this table into that particular location. Observe this. We want to insert an element with key k. Then we are going to find out the hash value of that key, and it is going to give us some index. Now using that index, we'll get into that table, right? For example, this particular index is this one. Then we get into this index, but instead of placing that element in this index, we are going to put the element in the list. If the list pointed by this particular entry is already existing, then what we do is, we create a new node and then we place it in the beginning. How do we put it? It is just like inserting an element at the beginning of a linked list, single linked list, right? So how do you put it? In the whatever element is newly created, we make the next of that to point to the head of the list, and then we make the head of it point to this. That is how we insert it. Therefore, in order to insert the element into the list or into this table, hash table, how much time does it take? the time taken to compute the hash function, and then the time taken to insert it at the beginning of the head. So anyway, it is going to be constant time. Why? Because we design the hash function in such a way that it is a mathematical function, and the time taken to compute the hash function is always going to be the constant, right? And then inserting an element at the beginning of a list is constant time. So insertion in case of chaining is going to take order of 1 time. Got it? And what about the other operation? Let us say searching. So in worst case, what could happen is, if you have n elements inserted into this table, all these n elements might map, even in worst case that could happen, right? So all these elements might map to a single entry, and the list of this entry might contain as many as n elements. Then in worst case, I am talking about the worst case. In worst case, a search could take as much as order of n time. So what is that worst case? All the elements are just present in one list, right, in the table, and is not evenly distributed. Then what happens is, in order to search for an element, you might have to search the entire list before declaring that the particular element is not there. See, again, searching an element, let us say all the elements are now mapped to one particular list, and now we wanted to search an element which also maps to that particular list, right? Then what happens, in that list we might have to, in worst case, if it is not present, we might have to search all the elements in the list. So time taken will be order of n. That is the worst case. Okay. And what about the worst case deletion? So worst case deletion is, you have to search for the element and then delete it, right? So it is also going to take order of n time in worst case, right? But then it turns out that if you are careful and if you use some uniform hash functions, uniform distribution hash functions means the hash functions which will not put all the elements into one slot. If somehow if you could distribute the elements, then in average case you could see that if there are n elements, right, if you try to have a uniform distribution function for the hashing, right, then it turns out that each slot might get n by m elements. Are you following this? See, what is that I am trying to say is, in case if all these n elements didn't happen to be mapping to a particular one slot, if they are very well distributed and every slot is going to get equal share of the elements, then every list on average is going to be as big as n by m, right? So in this case, on average, this is called average, right? In this case, average search time is going to be theta of how much? 1 plus n by m, right? And this particular n by m is also called as load factor. So this has a name which is called as load factor. Load factor is how many elements are present in the list, in the hash table, divided by total size of the hash table. If the hash table size is m slots and the total elements present in the hash table is n, then the balance factor is n by m. A load factor is n by m, right? So in this case, the average search time is going to be theta of 1 plus alpha, where alpha is the load factor, right? And if you see that the number of elements which are present here, right, if this one is some constant into m, which means if I always see that I maintain some constant into m elements only to be inserted into the table, then what happens to alpha? Alpha becomes some constant k, right? In that case, if alpha becomes a constant, then I can say that on average constant time is taken to search the element. Are you understanding this? So what I mean to say is, it is not always going to happen in such a way that all the elements will map to a single slot, which means all the elements will not be present in one list. In general, in average, they will be distributed over all the list. If it is distributed over all the list, how many elements? N elements are distributed over m list, then how many elements does each list get? N by m, right? In that case, if each list is going to get n by m elements, right, then search time is going to be 1 plus n by m. So 1 time is taken to compute the hash function, and then n by m time is taken to search the list, right? And n by m is also called as load factor. Then 1 plus load factor. if you maintain this load factor to be a constant, which means if you never exceed some particular load factor, which means let us say if the size of the array is this table is 10, and if you say that I'll never exceed 20 elements, then that is load factor is 2. In that case, search is going to be constant. Got it? And if this is the case for search, deletion is also the same time, isn't it? Then in this case, average deletion time can also be analyzed in the same way, right? And average deletion is also going to be of constant time, right? Therefore, using chaining, I can perform insertion, deletion as well as search, everything in a constant time on average, in average case. But anyway, in worst case, obviously you cannot miss it out. Got it? Fine. Then what is the other advantage of using this chaining is deletion is easy, because when you delete one element, you need not affect all the other elements. But in case of open addressing, if you delete one element, you are supposed to rearrange all the remaining elements, or at least you are supposed to do a lot of changes, right? Then because of that, because deletions are simple in this chaining. Got it? So what is the disadvantage of this chaining? Advantage is deletion is easy, and most of the operations are going to be on a constant time, fine, on average. Then what is the disadvantage of this chaining? Obviously you can see this, the elements are not stored in the table, they are stored outside the table, for which extra space is given, and moreover extra space is given for the pointers also, right? So disadvantage of this method is pointers. Why pointers is a disadvantage? Because space is wasted, right? So here space is wasted, right? There are both advantages and disadvantages of chaining. So this is all about the chaining. Okay, fine. So in quadratic probing, it is exactly like linear probing only, which means whenever there is collision, we are again going to probe next time. But then when we probe the second time, or the next sequence of probes, they are going to follow a different kind of hash function like this. So for example, this in linear probing, if the actual hash function is h of k, right, then next time when we are going to probe, we are going to take I into consideration, h of k plus I, right, mod m. This is what we used when we are doing this linear probing. So why was it called linear? Because whenever there is a collision at some location, let us say h of k, then the next the location which is going to be probed is at a linear distance from the initial probe position, right? That is why it was called linear probing, which means if we are probing at a location, if the initial probe position happens to be some location, then the next probe position is going to be at a linear distance, and in this case the distance turned out to be 1, right? So you can even do a modifications to this. What if you do like this, 2i, right? Then the next probe position will be at a distance of 2, isn't it? But then you should be careful that if you do m successful probes, they should all give all the locations in the hash table examined. Okay, what I mean to say is, whatever function you are using for probing, right, either it is linear or quadratic, whenever you do m successive probes, they all should make sure that you have visited all the slots in the hash table before you declare that the element is not present or the hash table is full, something like that. Okay, so in linear probing, what happened is we are actually probing at a distance linear to the initial probe position. If the initial probe position happened to be this, the next probe position will be at a distance of 1, and the next probe position will be at a distance of 1, right? Therefore the displacement of probing is actually linear. That is why it was called linear probing, right? Now what does this quadratic probing say is, whenever you are going to have a collision in the first probe position, then the consequent probes have to be at quadratic distances, which means it says that the next one has to be like this, c1 into I plus c2 into I square. That is what quadratic probing says. Okay, I square. So it means that If your initial probing is somewhere here, initial probe position, then the next probe position will not be linear, it will be quadratic, right? And the next probe position will not be linear, it will be quadratic. Got it? So that is the main difference between linear probing and quadratic probing. The distances between every probe will increases, quadratically, not linearly, right? So if you follow this, it is called as quadratic probing. Now, what is the advantage of quadratic probing compared to linear probing is, I told you that there are two types of clustering. One is primary clustering and other is secondary clustering. Primary clustering arises because when there is a row of, or when there is a run of occupied locations, let us say we have few occupied locations like this. When we have a run of occupied locations, right, then the probability that the next slot gets filled is going to be increased, because if the next key which has to be inserted happens to hash to any of these values, definitely according to linear probing, that will definitely be filled, taking up this position. Either if it hashes directly to this location or it hashes to any of these locations, that element will be inserted at this location, right? That is the problem with primary clustering. That is what is primary clustering, and linear probing suffers from primary clustering, right? But this problem will not arise with the quadratic clustering. The reason is, if any if your initial probe position happens to hash into any of these values, right, then the next probe will definitely be not this one. It might go to some other location, with a quadratic displacement. Got it? Therefore, the probability that we get a continuous run of clusters is going to be reduced because of quadratic clustering, right? So are you observing this? What I mean to say is, if we are going to start here, right, then the next one is not just this one, right? The next one is not just this one. Next one is not like this one. In case of linear probing, it was like that, right? But in case of quadratic probing, the next probe sequence will be at a distance quadratic from your initial probe. Therefore, the chances of building up a run of occupied cells or primary clusters is going to be reduced. So it doesn't suffer from primary clustering. But then secondary clustering is definitely possible. What is secondary clustering is, if initial probe position of two keys happen to be the same value, then the probe sequence they are going to follow is going to be same. Which means, if h of k is same for two keys, then anyway this is going to be same for the for whatever key it is. So since this factor is independent of the key and this factor is depending on the key, therefore depending on the initial probe position, the consequent probe sequences will depend on that. Which means, let's take an example. See this. Let us say C1 equal to 1. Okay, let's not take that example. Why I don't want to take any such example is, before going to secondary probing, that secondary clustering problem, let me explain you what is the problem with these parameters. No, there is C1, there is C2 and there is M, right? The problem is, I told you that any probing that you consider, either it is quadratic probing or linear probing, you should see that by making M successive probes, you should be able to examine all the elements of the hash table, and it happens in the linear probing. Which means, see, if linear probing starts here, right, initial probe, then in successive M probes, if I do successive M probes, then we are definitely going to examine all the positions of the hash table before we declare that an element is present or an element is not present, or there is free space or there is no free space. Which means, just by doing M probe sequences, we should be able to examine the entire table. But if you are not very careful, if you choose this C1, C2 and M randomly, it might not work that way. I'll just take a small example and show you what is the problem with these parameters. Let us say the size of the table is 10, and so M value is 10, and the indices are from 0 to 9, the hash table indices, and C1 equal to 1 and C2 equal to 1. Okay, and h of k, let's say h of k is, it doesn't matter, k mod 10, right? So now assume that when you try to put an element in some when you try to initially insert an element, the initial probe sequence 0 1 2 3 5 6 7 8 9, assume that when you try to insert an element into the hash table, the initial probe position happened to be 1, which means you are trying to put an element k1, then h of k1 turned out to be 1, right? And let us say that value is already occupied. Then what I do is I am going to again go and probe like this, is h dash, right? H dash of k1 comma 1. I'll probe it for the next time. Then what happens if c1 equal to 1 and c2 equal to 1, then if you substitute in that value everything, we already know that h of k1 happened to be 1, therefore it is 1 plus, right? In c1 if you put 1 and I is 1, I is this one, right? c1 is this one, and then c2 you put 1 and I equal to in 1 square, I square, then you are going to get a value of 3. Therefore the next probe will be at 3. Let us say 3 is also occupied. Then where will be the next probe? H dash of k1 comma 2, isn't it? The next probe will be at 1 plus 2 square. Then what is this? 4 5 6, right? So the next probe is equal to here, right? Then again we are going to examine it, and let us say it is also occupied. Then where is the next probe going to be? H dash of k1 comma 3, which is 1 plus 9. So what is it? 11. So the next probe is actually, again we are probing the same location which you have already probed. Are you getting this? Already it has been probed once. Now I am going to again probe the same location, right? Because of which one computation is wasted. And I told you that by making the next 10 computations, you are supposed to visit all the 10 locations. See, if initial combination, see, if h dash of k comma 0 is giving you some location, then I am going to go till h dash of k1 comma 1, h dash of k1 comma 2, so on, h dash of k1 comma 9, right? I am going to make 10 probes to find out a location in which I insert the element, and all these 10 probes have to give me 10 different sequences or 10 distinct elements or 10 distinct indices. But then we have seen that h dash of k1 comma 0 and h dash of probably k1 comma 3, these two are actually giving me the same value, which means by examining all the 10 probes, I might not be able to examine all the locations of the hash table. Then what happens? Then I'll examine all the 10 locations or whatever is given by this hash probing sequence. Then I'll find out that the table is completely full even without examining some of the locations. That is the problem with this, right? So you should choose this C1, C2 and M in such a way that whatever the initial probe position is, if you make M probes, you should be able to examine the entire table. That is the problem, and coming up with such a numbers is a challenge, right? And you can find it out, you can randomly choose various numbers and you can observe it, but then you have to do a lot of work on that. So generally people don't go for this quadratic probing. Most commonly used method is linear probing for its simplicity, and there is one more method we shall see it later. But anyway this quadratic probing has this disadvantage that if you are not careful, we might not end up examining all the locations. We might end up examining only few of the locations, right? If you want to continue this, see this. I'll just tell you what the problem it is. Now h dash of k1 comma 4, then what is it? 1 plus 16, I square is 16, isn't it? Then 8 will be examined and 8 is already full, right? And again h dash of k1 comma 5, then what is it? 1 plus 25. So how much is it? 7 will be examined. Let us say 7 is full. Then h dash of k1 comma 6, then what is it? 1 plus 36. So what will be examined? Again 8 will be examined, right? 8 is already examined here and again 8 is being examined. Therefore that is what is the problem is, right? So out of the 10 probes, many of the probes are actually leading to the same location, which means we are not able to examine all the locations by using 10 probes. Even though there are only 10 locations, we are not able to examining them, right? So that is the problem with this quadratic probing. You are supposed to choose the C1, C2 and M very well, otherwise it is going to lead to problems, right? And now how is this leading to secondary clustering? Secondary clustering is somehow like this. See, if two values here, in this case, let's take this one. If the initial value happened to be 1, initial probe position, then what is the next probe position? 3, right? And what is the next probe position? Next probe position happened to be, I think, 6, right? And the next probe position happened to be, I think, 1. And the next probe position happened to be 8. And next one happened to be 7. And next one happened to be 8. So on, right? Now, if initial probe sequence happened to be 1, these are the probe sequences possible, right? And similarly, if some other key, let us say this is for K1. For K1, the initial probe position happened to be 1, therefore the probe sequence happened to be this one. Let us say there is some other key K2 for which the initial probe position also happened to be 1. Then what will be the sequence of the probe sequence? It will be same, 3, 6, 1, 8, 7, 8, so on. This problem is called as secondary clustering. So secondary clustering means if two keys happen to have the same initial probe location, right, then they are going to have the probe sequence, the similar probe sequence. The reason is this one. See, only the initial probe sequence depends on the initial probe position depends on the key, and the later probe sequence is independent of the key. Therefore, even for when two different keys, if they are having the same initial probe position, they will have the subsequent probe sequences to be same. That is called as secondary clustering. So how will it lead to secondary clustering is, watch it. Now, some cluster will form here, right? And what happens is, if any of the keys lead to this particular cell which is already occupied, then all such keys will go to some other location and they all form a cluster here, right? And again, if any of the keys map to this one, again they all will form a cluster here, and again they all will form some cluster there, right? So likewise, the clusters will be formed not contiguously, but then at some distance, and the distances between the clusters will be quadratic. Anyway, there is clustering possible because of this problem. What is the problem? The probe sequences are going to be same, right, whenever the initial probe is same. Okay. And now the next question is, how many different probe sequences are possible by using quadratic probing? The number of different probe sequences possible is, every probe sequence depends on, what your initial probe position is. And how many initial probe positions can be there? Exactly, m initial probe positions can be there, isn't it? Because every probe sequence is going to start with one number, and how many numbers can be there? M numbers can be there if the size of the hash table is m. Therefore, how many different probe sequences can be totally possible because of quadratic probing? Exactly, m probe sequences are possible. Getting this? So this is same as linear probing, which means quadratic probing didn't give us any new probe sequences. So it is also going to give me the same probe sequences as there were in linear probing. Unless I have lot of probe sequences, I cannot actually reduce the number of collisions. There is a relationship, isn't it? If you are always trying to insert some keys in some order, then definitely if there is a collision first time, then again there might be a collision second time, again there might be a collision third time, right? So if I have lots of probe sequences, then somehow the table can be used effectively in such a way that collisions will be reduced, right? So the problem with either linear probing or quadratic probing is only the initial probe position is depending on the key, and the subsequent probe positions are independent of the key, which means either we are going to probe the next time at Ci, which means high in case of linear, or in case of quadratic C1i plus C2i square, right? And these two functions, this one or this one, is not depending on the key, which means only the first position will be depending on k, and the remaining positions will not depend on k. If you can somehow make these two positions also, these two functions also depend on the key, or for a given initial probe position, if we can if the remaining probe sequence differs depending on the value of the key, that will be a better function, isn't it? So that is what is the next strategy, we shall see it. Okay, so anyway, quadratic is better than this linear probing, right? But then it is not too good, or it is not too efficient to implement. The reason is, choosing C1, C2 and this one is difficult, and moreover it is not going to give us more probe sequences compared to the linear probing, right? So we go for the next kind of probing. Okay, fine.